It's 9 a.m., so we'll get started. Welcome everyone here, person and online, to this joint winter working group meeting of the Earth System Prediction and Climate Change working groups. We had the plenary session yesterday when we gave the working group updates. Yeah, can you hear me now? All right. Sorry for the technical glitches. I was just saying welcome and reminding everyone that we had the plenary session yesterday when we gave working group updates. So if you missed those, they should be available online. Just wanted to give you an overview of the plan for the day here. We're going to start off with remote speakers. These will be Earth System Prediction Working Group talks up through lunchtime, and we'll resume at 1 p.m. With a few more talks, and then go into Earth System Prediction Working Group discussion, have a break, and then transition to climate variability and change in the afternoon with a discussion right before we adjourn at 5. So without further ado, we'll have our first speaker, Xian Wu from the University of Texas at Dallas.
I will now share my screen. Can you see my presentation?
Yes, we can see your presentation.
Okay. Hi, everyone. Thank you for the opportunity to share our research on predictability of tropical Pacific decadal variability. This work was mainly conducted during my ASP postdoc at NCAR 2 years ago with Steve and Clara, and was published in NPJ Climate and Atmospheric Science last December. Recently, I joined UT Dallas as an assistant professor. As many of you know, decadal predictions provide important information for decision makers in many economic sectors and bridge the gap between seasonal forecasts and centennial climate projections. However, the prediction scale on decadal timescales remains very low for the internal climate over the tropical Pacific. Here, I'm showing you the correlation scale of CMIP models in predicting near surface air temperature averaged over forecast year 229. And if we consider the total decadal variations of surface air temperature, the correlation scale is very high almost everywhere, except for the North and Central Pacific and Southern Ocean. This is because the model can well capture the anthropogenic climate change, particularly the global warming trend associated with greenhouse gas increases. However, if we remove the effect of forced climate change, the residual correlation scale for internal decadal variability declines significantly, leaving no scale over the tropical Pacific. A key question remains, is this low prediction scale in the tropical Pacific due to intrinsic predictability limits which requires a better understanding of how predictable tropical Pacific decadal variability is and what affects the predictability. All this is a consequence of deficiencies in the forecast system, for example, model errors or or the uncertainties in the initial conditions. As we focus on the internal decadal climate mode in the tropical Pacific called TPDV, we define it use the leading EOF mode of 10-year running mean and quadratically detrended SST anomalies in the tropical Pacific. In observations during 1955 to 2022, TPDV shows some basin-wide SST anomalies in the tropical Pacific, fluctuating between warm and cold phases on decadal timescales. During the positive phase of TPDV, the equatorial Pacific thermocline deepens in the eastern equatorial Pacific, but shows in the western part. These temporal and spatial patterns associated with TPDV are well reproduced by the forced ocean sea ice simulation, FOSSI. It is the ocean and sea ice initial conditions used for the CESM1 decadal prediction large ensemble I will introduce in this slide. CESM1 DPLE consists of 40 forecast members initialized with FOSSI initial conditions on November 1st of each year during 1954 to 2015, with each initialization forecasts integrated for 10 years. They are conducted under the CIMIP-5 radiative forcing, including the historical volcanic forcing. We also make use of parallel set that excludes historical volcanic forcing to isolate the influence of volcanic forcing on decadal predictions. Additionally, we compare those initialized decadal forecasts with uninitialized simulations, CESM1 large ensemble, to investigate the influence of ocean initialization on decadal predictions. Now we apply the EOF analysis to the decadal hindcasts, including DPLE and DPLE NOVOC. DPLE NOVOC shows a pretty good skill in predicting the observed PC1 time series of TPDV. This suggests that over 30% of the variance in the PC1 time series is predictable. However, the DPLE shows a lower prediction scale. This is mainly due to the excessive cooling response in the tropical Pacific to the major volcanic eruptions, El Chichen and Pinatubo, during this period, while the observations show warming. More details about how volcanic forcing influenced decadal predictions can be found in our published paper in 2023. If we look into the uninitialized simulations, we can see there is no scale at all. This further confirms the importance of ocean initialization for TPDV prediction. Consistent with the EOF analysis, the anomaly correlation coefficient analysis shows similar results. The ACC score for SST in the tropical Pacific and subsurface equatorial Pacific temperature is highest in DPLE NOVOC. The degradation of scale in DPLE relative to DPLE NOVOC is limited to the sea surface temperature and also confined to the upper 100 meters in the equatorial Pacific. This is because the sea surface temperature and the mixed layer temperature are strongly influenced by the shortwave processes induced by volcanic aerosol forcings, while the subsurface ocean temperature scale are very comparable between DPLE and NOVOC. This suggests that the same oceanic processes may operate between DPLE and DPLE NOVOC, but they cannot provide a source of predictability for surface temperature when the volcanic forcing perturbs the system due to model errors. Also, the uninitialized large ensemble show no scale for SST or subsurface temperature. This brings us to the key question of this talk. What are the oceanic processes affect the predictability of TPDV? Many previous studies have investigated the origins and mechanisms of TPDV. Some studies argue that the origin of TPDV is just a residual of random ENSO variability, but others say that they are originated from the stochastic forcing from extratropical Pacific. Those random processes do not have any preferred timescale and are not predictable on decadal timescales, but they can initiate some slow oceanic processes that may provide a source of predictability for TPDV. Those oceanic mechanisms, including off-equatorial Rossby waves, Pacific subtropical sails, spiciness advection. Recent studies also suggest other ocean basins play an important role in affecting decadal climate in the tropical Pacific. In our paper, we investigate those mechanisms using observations, foci, and decadal hindcasts. Here, I will focus on the Rossby wave reflection mechanism, which we find is the most important source of predictability for TPDV. I will also briefly discuss the influence from other ocean basins using regional initialization experiments. Previous studies suggest that the Rossby wave reflection at the western boundary of the Pacific can provide on decadal timescales can provide a delayed negative feedback for TPDV by influencing the equatorial thermocline depth. This is similar to the dynamics driving ENSO phase transitions on interannual timescales. We characterize the signatures of Rossby wave reflection using the depth of isopycnal with the density equal to 25.5 kilogram per cubic meter. Here, I'm showing you the isopycnal depth variability along the waveguide from off-equatorial Pacific, western boundary, and equatorial Pacific. We apply the 10-year rounding mean filter to all the fields to focus on the decadal variations. So during the positive phase of TPDV, indicated by the red solid contours here in the equatorial Pacific, it will generate the positive wind stress curl in the off-equatorial Pacific in the north, and also negative wind stress curl in the south. I didn't include the southern part analysis here, both of which induce the upwelling Rossby waves propagate westward, and then they propagate equatorward along the western boundary and reflect into the upwelling equatorial Kelvin waves that can show the thermocline in the equatorial Pacific and leading to the transition from positive to negative phase of TPDV. Then we calculate the lead edge correlations of the equatorial decadal Pacific SST in year 0 with itself and isopycnal variability in equatorial Pacific, north equatorial Pacific and South equatorial Pacific in the western part. We find that the decadal equatorial Pacific SST is correlated with the isopycnal depth anomalies occur over 7 years in the equatorial part, but even earlier in the off-equatorial Pacific. To further confirm the importance of Rossby wave reflection, we look into the correlations of equatorial Pacific SST in forecast year 1 to 10 of DPLE NOVOC with its concurrent predictions during forecast year 1 to 10, but also with the initial conditions in the previous November during 1954 to 2015. We find that the predicted TPDV index doesn't show any correlations with initial SST conditions in tropical Pacific, but shows significant correlations with the subsurface temperature and also the isopycnal depth, not only in equatorial Pacific, but also the off-equatorial Pacific. This further confirms the importance of Rossby wave reflection in providing the source of predictability for TPDV. Finally, we look into how the other ocean basins influence the prediction for TPDV by using the regional initialization experiments. We focus on the period of 1999 to 2018, where we have the tropical Pacific decadal cooling. This is well captured by the DPLE NOVOC. So we wonder which part of the ocean basin initialization is more important to getting these tropical Pacific decadal anomalies. We conduct a set of regional initialization experiments, tropical Pacific, North Atlantic, and Southern Hemisphere ocean experiments. I will skip the methodologies here and show you the results. We found that the tropical Pacific initialization is important to the prediction of tropical Pacific decadal cooling during this period, while the North Atlantic initialization doesn't show much influence on the tropical Pacific. The Southern Hemisphere initialization, in contrast, generate tropical Pacific warming, but we know that this is a prediction error in the Southern Hemisphere, so that may cause an underestimation of tropical Pacific cooling in the DPLE NOVOC forecasts. In summary, we find that the isopycnal variability associated with Rossby wave reflection provides the most important source of predictability for TPDV. We investigate their influence in our DPLE and DPLE NOVOC systems. We also use regional initialization experiments to isolate the impact of different ocean basins on TPDV, and we find that the tropical Pacific initialization is most important. I will stop here and take any questions.
Go ahead, Jerry.
Hi, Sean. That was really interesting. But I was curious on your Hobbylo diagram where you're showing the Rossby waves coming across and then reflecting, and then the Kelvin waves going across. Yeah, that one. I mean, the Rossby waves are slow, right? But the Kelvin waves should be really fast. But it looks like the Kelvin waves are actually. Am I reading that right? The Kelvin waves are going slower than the Rossby waves.
I think it's relatively faster based on this plot.
So the time is going up.
Yes, time is going up. And I'm also doing like 10-year running filter to all the fields. So it's not an one Rossby wave or one Kelvin wave. It's the like the average effect of many sequences of waves.
Okay. All right. Thanks.
Thank you.
Just wondering about the volcanoes degrading. Do you know, are we getting like the forcing itself wrong, or is it how the model is responding to the forcing? Do you have any sense of which?
I think, yes, I think both of them contribute to the errors. We know that we do not have good observation constraints to the historical volcanic forcing, especially before the satellite era. And also, the CESM1 use CAM5 model, which doesn't have a good representation of the stratosphere. I think there are some ongoing work using Wacken. They find the response in the model to volcanic forcing might be weaker than the CAM5 or 6 models.
Okay, thanks. I think we'll move on now to our next speaker, Yu Yang.
Yes.
Yeah, I will share my screen. Wait, let me see. I have never used this outreach in the. What? Let me see. How can I do this? Wait.
First time you have to change the security settings.
So I choose to allow to share screen, right?
Yes.
And then it present to overlay. Share this screen. Okay. Can people see my screen now?
Yes, we can, and it's coming on. And if you don't mind, just put it there. You go.
Okay, awesome. Oh, sorry for the kind of a little hassle here. It's really my first time to use this Google Meet. So today, the talk is about some springtime precursors of ANSO. In particular, I would like to compare the role of the meridional oscillation with the North Pacific meridional mode induced by extratropical atmospheric circulations. So this is a work in collaboration with Shangping, Alexei, and Steve in NCA. So this work is really motivated by extreme El Nino events and and their impacts. So we know like extreme El Nino events like the 1997-98 can cause a widespread kind of devastating natural hazards, including drought and wildfire in the maritime continent, intensified tropical cyclone activity in the western North Pacific, as well as like a post El Nino summer Yangtze River flooding event in the southeastern China. And previous studies really suggest that early season west wind bursts are critical for the formation of those extreme El Nino events. And here I take the 1997-98 El Nino event as an example. And on the left is the Hofmann-Muller diagram of equatorially averaged zonal wind anomalies. The x-axis runs from 140 degree east to 100 degree west, covering the entire equatorial Pacific, and the time goes from top to bottom, from September 1996 to May 1998. And here we would like to emphasize this sequence of westerly wind bursts, which are episodes of strong westerly wind anomalies observed in the western central equatorial Pacific. And they really kickstart this extreme El Nino event by pushing the warm pool eastern edge eastwards, and in the meantime, excite those downwelling oceanic Kelvin waves. So this sequence of west wind bursts laid the foundation of this extreme El Nino events according to some numerical experiments. And one of our studies back in 2021 showed that about 80% of west wind bursts during the El Nino onset are associated with the meta-Julian oscillation. And the meta-Julian oscillation is the dominant atmospheric mode on the seasonal timescale in the tropics. It can be characterized by this precipitation dipole occurring every 30 to 60 days. So every 30 to 60 days, you basically will see the MJO initiated on the tropical Indian Ocean, gradually propagates eastward across the maritime continent. When it reaches the Western Pacific, it can sometimes induce the westerly winds, strong westerly wind anomalies on the equator. In some cases, cause westerly wind bursts. And the March 1997 is a good example. So here you can see this precipitation dipole with enhanced precipitation in the Western Pacific while reduced precipitation in the maritime continent. And this MJO event caused this strong west wind burst we observed in March 1997. And in the meantime, we also observe this warm SST anomalies in the Western Central Equatorial Pacific and some warm SST anomalies north of the equator, similar to what people call like Pacific meridional mode. So we can say that both the Pacific meridional mode and the meta-Julian oscillation, they contribute to the formation of this strong March 1997 westerly wind burst. And one question I want to address is like which one has has larger influence on the subsequent El Nino evolution? Answering this question is important because it points us to different sources of predictability for the extreme El Nino events. And I would like to start by addressing this question: how does the springtime MJO, for example, in March, affect the subsequent ENSO evolution? And the data set we are going to use is CSM2, seasonal to multi-year large ensemble initialized hindcasts, and we used February 1st initialized hindcasts from 1970 to 2019. So this set of experiment consists of 20 ensemble members and integrated for 2 years. And we will need to first isolate the March MJO events. And we isolate the MJO events through a UF analysis of the atmospheric spread of these 20 ensemble members in all 50 years. And then we will quantify its impact on ENSO by computing the correlation coefficient between the March MJO amplitude and the December Nino 3.4 spread. We choose December is because ENSO usually peaks in December. And to illustrate this method further, we can look at the ensemble forecast initialized on February 2nd, 2025, provided by the CFS version 2, which is the dynamic model hosted in NCEP. So the setting of CFS version 2 is quite similar to the CSM2 SMILE we've just mentioned. So they are both they both simulated the observation into the model and then start the ensemble forecast. And normally when people look at this ensemble forecast, they focus on the ensemble mean because they think, the spread is the noise. But it is this spread that we really care about in this study. For example, for this February 2nd initialized forecast, we know that among this around 40 ensemble members, the ocean state at the beginning, they are all the same. The only difference is some initial random atmospheric perturbations. And we can see that the forecast for the Nino 3.4 SST anomaly, they really start to diverge in March and April, when the atmospheric noises like the meta-Julian oscillation, they behave really differently after 1 month. So because the ocean has a relatively long memory, especially in the tropics, they have a memory of say a few months. while atmospheric processes like the methane oscillation, they only have a memory of about 3 to 4 weeks. So for the hindcasts or forecasts initialized on early February, the MGO in each ensemble member is really different starting in March. So those MGO events in March, they can really be regarded as stochastic atmospheric processes. And it is those stochastic atmospheric processes that cause the ensemble spread of the Niño 3.4 SST anomalies. And then we will try to isolate the March MGO by conducting the UF analysis of the 20-member ensemble spread of precipitation and surface winds in this tropical Indo-Pacific region. And we get this true UF1 and UF2. And we suggest that this UF1 represents the average MGO amplitude in March when it's in its phases 6 to 8, meaning that MGO, the enhanced precipitation pole, reaches the Western Pacific and induce the westerly wind anomalies on the equator. And we do not really look at this UF2 because the westerly wind projections on the equator is very weak. And in a paper published last December, we discussed why UF1 explained more variance than the UF2. And to quantify the March MGO's impact on the subsequent answer evolution, we compute the correlation between the principal component 1, PC1, and the Niño 3.4 spread in December. And surprisingly, we find that the correlation between the two is 0. Suggesting that this March MGO event doesn't really do much to enhance the likelihood of El Nino occurrence, for example. And looking into deeper, we can regress the ensemble spread of SST, precipitation and winds in the following months onto this March PC1 and see what this March MGO event does to the subsequent ASC interaction processes. And we find that in April, this westerly wind anomalies associated with this MGO indeed helped to push the warm pool eastern edge eastward, indicated by these warm SST anomalies in the far western equatorial Pacific. In the meantime, it also induced a downwelling oceanic Kelvin waves that propagate eastward, manifesting itself as the warm SST anomaly in the central eastern equatorial Pacific. However, you may notice that the coupling between the ocean and atmosphere is really weak because you can see that the westerly wind anomalies associated with this warm SST and the atmospheric processes like the precipitation is also very weak in May. As a result, by July, if we look at the Niño 3.4 region, like in the central eastern equatorial Pacific, the warm SST anomalies are really weak now, like almost gone. And in the atmosphere, there's basically no signal. Therefore, like we can see that this March MGO event doesn't have a significant influence on the December ENSO amplitude. And one possibility is that the MGO based on this 50-year kind of EOF analysis has really weak westerly wind anomalies on the far western equatorial Pacific. And this is because in reality, or say in nature, some MGO events, they generate west wind bursts on the equator, while others, they do not. And the one favorable conditions based on one of our previous studies is the presence of a warm SST anomalies in the western central equatorial Pacific, which will help to attract MGO convection and the westerly winds from south of the equator closer to the equator, therefore enhancing the westerly wind anomalies on the equator. And we conducted an extra 30 ensemble hindcasts initiated on February 1st, 1997, and again conducted the UF analysis of this 50-member ensemble spread now. And here's the results, the MGO in March 1997. And by comparing this MGO structure to this so-called climatological MGO structure, we see that in March 1997, the MGO indeed has a much stronger westerly wind anomalies on the equator. And we can, again, compute the correlation between this March MGO PC and the Oceanic Nino Index spread in December 1997. And we find that the correlation is now positive, suggesting that the MGO is playing kind of some role here. But although like the correlation is still not significant, therefore really suggesting their limited impact. It turns out it is the extratropical circulation that actually favors the following El Nino growth, in particular this North Pacific oscillation, which is the second EOF of the extratropical atmospheric circulation. And you can see that this NPO has a significant correlation with the Nino 3.4 spread in December with a correlation coefficient of 0.16. And looking into some details, we can see that this cyclonic circulation of the NPO will reduce the trade winds in the subtropical northeastern Pacific, therefore causing this warm SST anomalies there. And this horseshoe-like warm SST anomalies, unlike the weak atmosphere-ocean coupling on the equator, it has a very good strong coupling with the ITCZ, indicated by this blue contours on the left. So you can see it shift the ITCZ northward, and therefore inducing this southwesterly wind anomalies to its southwest. And gradually you will see this horseshoe-like SST anomalies, or sometimes called meridional mode. It propagates southwestward and consistently couples with this ITCZ. Because this coupling is so persistent that it lasts until even in September, when it interacts with the mean precipitation, like with the ITCZ, and starts to induce westerly wind anomalies on the equator. And this is when the Bayesian feedback starts to get in and further increase the warm SST anomalies on the equator. Therefore, through this sequence of processes, the wintertime North Pacific oscillation can effectively contribute to the El Nino growth. And here comes the conclusion. So here we have developed an ensemble hindcast-based method to quantify the role of stochastic atmospheric processes in ENSO evolution. And this framework can be extended to other air-sea interaction phenomena. And we suggest that a single MJO event in March alone cannot effectively contribute to the wintertime ENSO amplitude. So we suggest that it might take a sequence of MJO events in boreal spring to significantly affect the subsequent ENSO evolution. And this is because the coupling on the equator in the boreal spring is quite weak, while the extratropical circulation can effectively contribute to the ENSO growth by inducing the meridional mode-like SST anomalies, which can effectively couple with the ITCZ. And yeah, that's all for my talk, and I will appreciate questions.
We do have time for questions.
Hi, you. Nice talk. I'm just wondering if you explored the opposite hemisphere effect, if the South Pacific meridional mode has a similar effect on the SPCZ.
So the South Pacific meridional mode, it really play a role when in its boreal kind of summer season. So if you want to look at that, you may want to examine, say, the May 1st initialized hindcast. And we've mainly focused on the spring season because we want to overcome this so-called spring predictability barrier. But I'm sure you can do that with the May 1st initialized hindcast. Thank you.
Go ahead, Jerry.
Yeah, I was just curious, the anomalous cyclonic circulation that weakens the trades and kicks off the meridional mode, you're saying it's stochastic processes, but is it really stochastic? Is there something driving that anomalous cyclonic circulation coming out of the tropics, or is it really stochastic, do you think?
We think it's really stochastic, because you can see in the tropical Pacific, the signal, there's really not much signal, SST anomalies and So what one could easily test this by applying, the SST anomalies observed in the tropics to AGCM and see if it can force this, NPO-like circulation and yeah,
okay, thanks.
thank you.
All right, thank you. You will move
Mm.
on to the next speaker, who is in person, Julie Arblaster.
Okay.
Hi, everyone. Did you get me from?
It should be at the bottom. Your talk should be at the bottom.
Oh,
Could you click on that hide button right there?
okay. Thanks, everyone.
We're not sharing.
We're not sharing.
Yeah. So go ahead and just go ahead and pause that. Do it again. Stop screen share.
Good. Okay. Thanks, everyone. So I'm Julie Arblaster, and I'm from Monash University in Melbourne, Australia. And I'm going to be talking on the predictability of the 2020 strong Antarctic vortex and the role of ozone in predicting it. And I wanted to thank Jerry Mill, who is hosting my sabbatical here at NCAR. I'm going to be here through the end of May, and also acknowledge our funders. So part of this study was funded by the Department of Energy as part of the Catalyst Group, which I've been a long-term collaborator with, as well as our Antarctic Centre at Monash, SAFE, Securing Antarctica's Environmental Future. Okay, so this study is really is published at the end of last year in JGR Atmospheres, led by Dr. Unpar Lim at the Australian Bureau of Meteorology. Even though Jerry is not involved in this study, it's certainly been inspired by some of his early work in Southern Hemisphere meteorology and more recently in near-term predictability. Okay, so recently the Antarctic polar vortex has really become something that people are thinking about more in the Southern Hemisphere as a source of predictability for surface climate. And so here we're showing the polar vortex over Antarctica as potential vorticity. And you can see that the winds are circling around Antarctica, but there's quite a variation in the shape of the vortex and its strength. And this has been shown to be, at certain times of the year, coupled down to the troposphere and have a correlation with the southern annular mode, which is really looking at the strength and the position of the southern hemisphere storm tracks. And so as these winds move south and strengthen, we get increased rainfall over Southeast Australia. And as they move north and weaken, we get decreased rainfall over Southeast Australia and also other parts of the southern hemisphere. So I thought I'd just start with the life cycle of the southern hemisphere stratospheric jet or polar vortex. And so here I'm showing the zonal mean zonal winds from the surface to the upper atmosphere for every month from April through to December. So you can see that at the southern hemisphere westerly jet really starts developing in southern hemisphere autumn and peaks in winter here. in around 40 to 50 south at the stratopause. And then in spring, it becomes weaker, is disturbed by a lot of vertically propagating waves from the lower stratosphere, upper troposphere. And so this further weakens and warms the vortex, and it contracts towards the pole and moves downward. And then in late summer, late spring, early summer, it completely breaks down in the stratosphere. There's no longer any winds in the stratosphere, and we just live with the tropospheric jet. So this is the climatological life cycle of the Southern Hemisphere jet, but there are often cases when that polar vortex sometimes happens faster than normal, and so you get this anomalous spring polar vortex warming and weakening, and earlier vortex breakdown, and at other times it happens slower than normal, and you get this delayed vortex breakdown. So this is a typical dynamical evolution of a really strong spring polar vortex. So here again in the black is the climatological winds, and the colors here are now the anomalies. And so you can see that you get an equatorward shift of the winter stratospheric jet, indicated by this dipole of colors here for this strong anomalous spring polar vortex. And then these anomalies of the jet move poleward and downward with time. You can see it coming down into the troposphere here, and you get this polar vortex in spring. And then in late spring, early summer, the spring polar vortex anomaly move further poleward and into the troposphere. And that's when you get that coupling into the positive SAM. Okay, which is this dipole of pressure with low pressure over the Antarctic continent and high pressure in mid-latitudes is that leading mode of Southern Hemisphere extratropical circulation variability. So we have seen the impact of these stratospheric polar vortex weakening events or strengthening events on the surface climate. And so this is a paper from 2021 led by UNPA, where we had this sudden polar vortex weakening in 2019, just happening as we had published this paper that came out in October 2019, suggesting that these weakening of the polar vortex could lead to significant influence on Australian late spring, extreme temperatures, mean rainfall, so drying here, and then increased wildfire danger. And as you may recall, in the spring of 2019, Australia had some really significant bushfires, and these occurred at the same time as this sudden polar vortex weakening was happening. So this is showing again those a similar plot where you've got the evolution of the zonal mean zonal winds at 60 south. I'm trying to find my mouse. And so this was a really sudden weakening of that vortex led to this negative SAM at the surface and really strong warming over the polar cap. But recently we've had really extreme variability of the Southern Hemisphere polar vortex. So here are the zonal mean westerly anomalies at 60 south again. And so you can see this weakening event here in 2019 that we had looked at in the previous slide. And then here in 2020, 2021 and 2022, and even 2023, and these really strong anomalies, and so a delayed breakdown of the polar vortex. And so in this 2020 event, which I'm talking about today, it was the strongest on record in the last 45 years. So at the bottom here is the SAM index. So you can see this really consistent, strong, positive SAM. And then if you look just at the November, December Antarctic vortex strength at 10 hectopascals, you can see it was, the strongest on record. So just showing a few more statistics about this event. So here again is that strongest on record for this October-December period now. Also, really significant cold anomalies over the Antarctic polar cap in the upper stratosphere, and significant but not record ozone depletion over Antarctica. However, the seasonal forecast system in Australia at the Bureau of Meteorology was unable to predict this event. So even though it was one of the strongest on record, and usually we have fairly good predictability, these forecasts of the polar vortex strength here, so this is the observational strength in terms of standardized anomalies, and then the forecast starting 3 months before, so July forecast, the August forecast, and the September forecast. It wasn't until 1 month before, or actually initialized at October, for this October to December mean polar vortex strength, could we actually get any predictability. And so this is despite the fact that in previous years, or subsequent years, we could get good predictability even back in the 3-month lead time. So this is the forecast skill of this October to December mean stratospheric vortex, and you can see it's got quite good skill even out to 3 months lead time. So what was happening in 2020? So here is the just a little bit of detail about the 2020 event, and this is the canonical kind of vortex weakening or strengthening pattern. So typically in the upper stratosphere and in the southern hemisphere winter, for these weakening events, you get a strengthening in the upper stratosphere, and then that switches to negative wind anomalies in the September to October period. And they propagate downward in late spring to the surface. However, in 2020, the vortex didn't follow this typical pattern. We did have strengthening of the winds in the upper stratosphere, and there was some indication that this dipole would occur and that the winds would then weaken and propagate down into the spring. But for some reason, those winds remained strong and remarkably persistent through October. And so from some analysis, it's clear that part of what was going on was that there was this sudden reduction of upward propagating wave activity in September that is associated with this height pattern in the southern hemisphere. And so there was this anomalous tropospheric circulation pattern that persisted in September 2020, and it really reduced this upward propagating wave activity that would usually act to weaken the vortex. And so because there wasn't any upward propagating wave activity, the polar vortex stayed strong and undisturbed. So that's some of our diagnosis of what was going on. And so then we looked at using the seasonal forecast system in Australia to try and understand how that fed into the predictability of the event. So this is the operational version of the Bureau of Meteorology's dynamical coupled S2S system. So I won't go into many of the details here, but it is very similar to the Access S1, which was operational at the time of the 2020 event, just some small bug fixes and a slightly different initialization technique. And it is based on the UK seasonal prediction system. And just wanted to point out that it does have high resolution in the atmosphere, 85 levels with, I think, 18 of those levels above in the stratosphere. And yeah, 60-kilometer resolution in the atmosphere. So we were really interested in what the role of ozone was for predicting this event in the Access S2S system, and I think in most operational systems, they prescribe climatological ozone. There's no time-varying ozone anomalies. And this can interfere with the dynamics of the model and perhaps degrade the forecast certainly for the polar vortex, and potentially its coupling down to the surface. So we ran a 3-member ensemble hindcast for the 1981 to 2018 period, and then 33-member ensemble forecast just for that 2020 event. And so the control was using the standard climatological ozone forcing. This comes from the CMIPS 5 dataset, I think, by Tierney et al., which is based on SAGE satellite observations. And then we ran also some ozone experiments where we looked at actually prescribing the anomalies of ozone. So this is not interactive ozone. It's basically if the model had the perfect ozone as was observed, what would the forecast of the polar vortex and the SAM be? So these are the results. So here on the top, we have the zonal mean zonal winds at 60 south from the surface to the top of the atmosphere. And you can see in the observations this strengthening of the zonal winds through the spring. In the control, the forecast wasn't able to get that strengthening, though it did pick up the tropospheric part of the jet later in the summer, indicating that might not be related to the polar vortex. And then here in the experiment where we've got the ozone anomalies prescribed, we do get a much stronger anomalies of the jet. And then you can also see over the polar cap this real cold anomaly that occurred. The control gets it to some extent, but when you have the ozone forcing it, really enhances that, improves the simulation. So we did look at the contribution of that wave driving, which we hypothesized was leading to the strengthening of the vortex in that 2020 event. And here I'm showing again the zonal mean with zonal winds in the upper stratosphere, so 10 hectopascals and 50 hectopascals in the observations. You can see in the control, it really, these blue bars, they just didn't get that strengthening of the winds at all. This is, I think, again, for the October to January period. And these dots are the ensemble members. But you can see the ensemble members that had reduced poleward eddy heat flux or reduced wave driving were certainly able to get a stronger increase in the vortex anomaly. So it does suggest that September wave activity was really related to the vortex strength. And then again, in the experiment, we have a similar relationship, indicating it was potentially just some intrinsic dynamics leading to that strengthening of the vortex. In terms of coupling down to the surface, the inclusion of ozone does get a better forecast of the SAM, the positive SAM here, compared to the observations. We get better forecast of the anomalous rainfall in the Southeast Australia, but it doesn't seem to help having ozone to improve the prediction of these South American rainfall. So it does suggest that there's scope if we did have interactive ozone or some way of forecasting ozone, that we could have a better predictability in the Southern Hemisphere of surface climate for these big events. Okay, I am running out of time, but I did want to say that there was a really extraordinary stratospheric warming in the winter of 2024 last year, and we're doing some ongoing work now to try and understand what was leading to that over those. And so just to finish, I wanted to highlight that in Southern Hemisphere predictability, there's two main sources. ENSO is a really big source. We have really quite good skill in Australia and other parts of the Southern Hemisphere through predicting El Nino and La Nina and its influence on our surface climate. And that's of real interest to our agriculture sector and others. But more recently, through this work by Unpar and Harry Hendon before her, indicating that this source of predictability from the Antarctic polar vortex. And they don't seem to be strongly related, and so there's these sort of two sources of skill in prediction. And you can, often there is skill in predicting from the winter polar vortex strength, you can predict the late spring SAM. Thing here, so two sources of predictability. So we need to both model both of those well and monitor them for prediction and skillful forecasts. Okay, so just to summarize, we have shown that the dynamical seasonal evolution of the polar vortex from winter to early summer is an important source of long lead predictability in the southern hemisphere. We've had these really extraordinary events in the last 5 years. Some hypothesis of why that might be are ongoing, but really to improve our skill in the seasonal forecasts, I think having some interactive ozone would be really useful, and we're certainly in Australia thinking of how we could do that. And yeah, then this 2024 event, UNPAR is currently writing up understanding of what might have led to that winter event. And yeah, we're thinking of some experiments to do with the low sea ice potentially that might have had that influence on the vortex there. I'll leave it there, thanks.
Maybe one quick question.
At the beginning, you showed the kind of time evolution of anomalies, and you have like the tilted vortex, and the anomalies kind of move forward and down. I'm just wondering, is getting that tilt really important? Getting it right in models important? And the reason I'm asking is because that tilt is much better in CSM3 with Julio's mountain moving mountains. So do you think we should expect improved predictability because we're getting the kind of wintertime structure of the vortex better?
So yeah, yeah, certainly coupling between the stress is important. Yeah, and I think some centers have looked at the influence of ozone on that as well, and tried to put interactive ozone, so the dynamics and the ozone together. But unfortunately, I think when you do that, the ozone climatology and and so I think that's going to be a difficult thing for models to be able to get the ozone and the dynamic working.
Right. Interactive ozone would only help if you're getting the wind anomalies and the temperature anomalies to begin with, right?
Yeah, and so having the ozone climatology kind of keeps that connected in terms of the climatology of the wind, but the grade both. Thank you.
So our next speaker is this person talk titled Ensemble Reuse, Impact of Soil Moisture Guided Ensemble Subselection Forecasts.
Hi, everyone.
Mike's not.
Hi, everyone. Yeah, thank you very much for this great opportunity to share my most recent research activity. I'm Daisuke Tokuda, coming from the George Mason University, supervised by Professor Paul DeMayer. But I'm staying for 1 year in Foothill Lab, supervised by Dr. Mike Eck. Let me start with this background of my research. So the boundary condition into each forecast model, including machine learning or numerical weather prediction models. is very important. However, the chaotic nature of the Earth system, mainly in the atmosphere, presents two major challenges. The first issue is sharp sensitivity to initial conditions. A key method to address this issue is ensemble forecasting. Another issue is the lifetime of the initialization. Yeah, as shown in this schematic diagram. We discussed multiple times from yesterday. While accurate initial values for the atmosphere significantly improve the forecast skill in the first few days, but this effect fades about 2 weeks. This issue can be addressed in 2 ways. First is iterative initialization of the atmospheric fields. But it is insufficient to keep the forecast skill for weekly or monthly scale, I mean S2S scale weather forecast. So to accurately predict the atmospheric fields over several weeks, it's important to initialize not only the atmosphere, but the land state, which has a longer memory. So in particular, the soil moisture has drawn attention as a key factor influencing the subsequent air temperature changes. So when the net radiation from the atmosphere reaches the ground, it is partitioned into 3 components: latent heat, sensible heat, and ground heat fluxes. The soil moisture controls this energy partitioning. So I mean, in dry soil, evaporation decreases while sensible heat flux increases, leading to warmer air temperatures. So this, causal chain creates a negative relationship between soil moisture and air temperature. Additionally, many studies have explored its connection to heat waves. So this study focuses on the initialization process mainly for the land conditions in operational forecasting. So typically old ensemble members are discarded in favor of new ones. So, but is this always the best approach? So I agree to that the Earth system changes constantly. This is a fact. However, the latest ensemble members, which are initialized with the latest information, always outperform the past ensemble members. Is it a fact or just a expectation? So that's my primary research question. So while past ensembles diverge due to the chaotic nature, some ensemble members may still follow a favorable trajectories, which is aligned with reality. So the research question of this study is here. Can we improve the latest forecasting skill with the past ensembles? Especially, the target variable of this study is daily maximum 2-meter air temperature in fourth week forecast. So let me assume this scenario. So the latest initialization generates n ensemble members for a given grid. Additionally, there are another n ensemble members initialized on the past, like here. So in the past, for example, 1 week ago, the key idea is not to use all of them, but to selectively choose n ensemble members out of the past ensemble members. We then compute the average of the total n plus m ensemble members as a representative. So how do we choose these past ensemble members? This study focuses on the soil moisture. So that is, we choose past ensemble members that best predict soil moisture at this most latest initialization timing. So so for example, to improve the July 15th weather forecast, I'm also referring to the past ensemble members initialized on the July 8th. And then, so to select or to filter those ensemble members, I'm referring to the soil moisture on July 15th. And a key point to consider is that there are 2 parameters. So how many ensemble members to include and how far back in time to select past ensemble members. So we have July 1st or July 8th or more earlier ensemble members at this example. So but those parameters are optimized during the training period and tested during the testing period. I'm now summarizing the data used in this study. So I use NLDAS2, and also this study limited the temporal coverage to the summer season, I mean JJA season. And soil moisture is top 28 centimeters. And there are 4 forecast models in total, including CESM2, which is kindly given by Meg and Sasha. Thank you very much. And 3 models from the S2S database. And initialization processes take place once or twice a week. And the available period for the hindcast experiment is different among the models, but in this study, we use all of them, but let me talk later about when training and testing periods are. And all of the variables are converted into percentile. So then we can directly compare the soil moistures at the different depths, I mean, between the reference data set and forecast model. And also, forecast removed, I removed a drift from the forecast data set. And we perform a brute force approach to determine the optimum values for the 2 parameters. In this study, we use mean squared error, MSE, as the error metric to divide the data. And these parameters are selected for each sample, each grade, each lead time, and each month. And what the sample meaning here? And to divide the data into training and validation periods, we use the bootstrapping method, which randomly splits the data into test training and testing periods or years 100 times. And the results shown in the following slides are the mean of those 100 samples and the statistical significance with this center. And the slide shown here is the improvement in weekly forecast result compared with the latest ensemble mean. I mean, bigger MSE indicates the worst forecast skill. So then the positive sign of this equation indicates the improvement induced by this proposed method compared with the latest ensemble mean. And red color improves the improvement, indicates the improvement, and black dot indicates the statistical significance. And CESM2 and from first to fourth week, from CESM2 to Météo France. And so those 2 models, CESM2 and Météo France, provide good examples to understand the impact of this method. I mean, in the first week, many grids show statistically significant improvement. But as the lead time increases, the affected area gradually shrinks. We will discuss these spatial patterns, very clear spatial pattern we can find, but let me talk later about that. And additionally, while HMCR remains very significantly affected in many grids, even in the 4th week forecast, ESMWF shows little change, little sensitivity to this method, except for some grids. And maybe some of you may be thinking, so if the number of ensemble, the number of ensemble members are increased, the chaos-induced realization error will be improved. So then this result is not so surprising. I understand this concern, but we can address this concern in 2 ways. First, we compare our method with a case where all forecast ensembles from the previous week, I mean, using 2n ensembles versus n plus n ensembles this study. We compare that. And if, in particular, for the 1st and 2nd weeks, we can still find a significant improvement induced by this method, even though it uses few ensemble members than the alternative approach. While there are some grids, I mean some blue grids where the skill decreases in later weeks, but most of those changes are statistically insignificant. As the bottom indicates. And another way to address this concern is MSE decomposition. So these equations show the MSE consists of mean error derived from the squared bias and realization error or variance. Here we show the results only for the 3-week forecast, but the same pattern was observed for other weeks as well. And while realization error, I mean the bottom row, is decreased for many grids, but its magnitude is very minor. compared with the mean error, but the selective ensemble reuse also improves the mean error, which dominates the overall improvement or not. And what determines the impact of the proposed method? Yeah, I believe the answer lies in the change on the daily scale. Yeah, the black, yeah, I'm plotting those time series from, I mean, the sensitivity to late time. I mean, I have two lines. Black line compares the skill gain from the reference climatology without any model forecast to latest ensemble mean. So which indicates the current model implementation and current initialization implementation. And the blue line indicates the additional skill gain from the latest ensemble mean to this study. So then, while black line, how to say, black line decreases immediately after initialization. The blue line peaks after a few days or to 10 days, depending on model. So this time lag is very similar to existing time series. I mean, this schematic diagram, we discussed many times in this workshop. And sometimes, so this hypothesis was, how to say, it was said that this schematic is too idealized, but still, the results of this study, follow this, how to say, time lag, green line in the hypothesis panel. In other words, this ensemble reuse method emulates or supports the additional lambda initialization, I think. And this hypothesis helps us interpret the results in two ways. First, why eSIMWF shows the little sensitivity to this method? If the improvement in this study comes from the additional lambda initialization, then eSIMWF may already apply appropriate perturbation to its initial conditions. And second, it helps us understand the spatial pattern of the impact of this method. According to GLASSE 2 project and follow-up studies, so the impact of lambda initialization is explained by the soil moisture latent heat coupling and soil moisture memory. Since the impacts of this study is additional component, not overall impact of the lambda initialization, just additional component, but so the spatial pattern does not directly match those spatial patterns, but it's still, so such a finding is very helpful to understanding this spatial distribution. And in weather forecast context or post-processing context, so the accurately predicting extreme events is also very important. However, this method showing the upper side did not show a significant improvement in that area. These results show the forecast for 1 week and 2 week forecast for the from 75 to 100 percentile of the true air temperature. A preliminary analysis, not shown here, suggested that the method was too closely related to the normal conditions, which limited its ability to capture extreme events. To address this, we ran the parameter selection again using a true temperature weighted loss function. So this adjustment led to some improvements, although the affected area, even in the first week forecast, is limited. This result demonstrates that this method has flexibility and can be adjusted to meet different forecast objectives. So then it's almost time. So let me skip this slide. Comparing the other post processings. And so it's almost 15 minutes. So let me finish my talk by showing this slide. But still, so I'd like to emphasize that different from other post-processing methods. So this, our proposal emulates or supports the additional lambda initialization possibly. So then, it helps the, how to say, model improvement or discussion. Model-oriented discussion we can support with this method. That's all from my side. Thank you very much.
Really cool presentation. I had not seen this method before. I'm wondering if you or maybe somebody else has applied it to seasonal timescales or tried it on seasonal timescales.
Yes, so these parameters are collected for each month. So then, yeah, we have some seasonal, seasonal variation in parameters and forecasts.
Lead times, so out to, beyond week 4.
Beyond week 4, I'm sorry, I have not got it.
Yeah, thank you very much. Do you understand why for ECMWF in week 4, the skill gain is bigger than in weeks 1, 2, and 3?
Or what?
Yeah, this one. So the ECMWF at week 4, the skill gain is bigger than for the previous weeks.
Yes,
Whereas
yes.
for CSM, the skill gain is biggest for week 1. Do you understand why ECMWF is so different?
Yeah, actually, so we applied a time averaging scheme. I mean, so for the short lead time, so we have to, how to say, calculate the forecast skill day by day. I mean, discrete weather skill of the in fourth week. So we have applied a temporal average time window. So then, which affects both gradient between first and fourth week. Is it not sufficient?
Yeah, and maybe ECMWF is so good that you don't see the improvement for the week 1, whereas CSM is so bad that it helps.
Yeah, I have to say so.
Yeah, because it's 50 versus 10. Thanks. Thank you very much.
Okay. Sanjeev, go ahead and ask your question.
Yeah, so sorry if I missed it. You are using the most recent
Hold
answer.
on, we can't hear you well.
Okay. Can you hear me?
Slightly better.
Okay, so let me try. So I wanted to understand a little bit of method section. So you are using most recent ensemble as a basis for selecting the past ensemble, right? So like if the purpose is to increase the ensemble size or what? Like why don't we just use the most recent ensemble?
The timing of the earlier initialization is also optimized during the training period. I mean, so we can use, one week ago initialization or 2 week ago initialization or 3 week ago initialization, depending on the lead time. But those, initialization timing is also selected.
Okay, I can talk offline. Thank you.
Go ahead, Rob.
I think I maybe had the same question. So is your conclusion is basically if you increase your ensemble size, you get higher scale. Is that another way of phrasing it, or is there something more subtle? So you've kind of augmented your latest ensemble with prior members that kind of looked good at that initialization date. So you've boosted your ensemble size. Is that correct?
Yeah, in the industry, boosting the ensemble size, how to say, the better ensemble selection is also, leads to an improvement.
You're combining those with the latest.
So between this comparison, so not only by increasing the ensemble size, so we have to select better past ensemble members.
Okay, maybe we'll take this into the break. We'll come back at 10:40. Thanks to all the speakers.
Okay.
I also worked on it for 2 years.
As a graduate student, are you still
No,
looking to
just
present
out of my
for
undergrad.
ESP or S2S?
I was working with Brian Zeros. I was working on.
I think it's like 2 weeks from Tuesday.
presentations with K-means clustering. So
All right, hello, everyone. Perfect. Thanks for that. We'll get started. So, our first speaker is a virtual speaker, and that's Shiron from University of Maryland.
Hi everyone, hi, I'll share screen. Okay, I think that should be working. So hi everyone, thanks for the opportunity to present in the meeting. I'm a fourth year graduate student at the University of Maryland under the supervision of Maria Molina. And today I'll share with you some work that we've done regarding the S2S predictability of North American weather regimes. This is work that is under review right now. And yeah, hopefully it goes smoothly for the second round of reviews. Our main research question is very similar to the research question that Yaga talked about yesterday in her talk, which is where is atmospheric predictability coming from? Essentially comparing the atmosphere, the land, and the ocean. And so the main difference regarding our work is that we are trying to do this based on machine learning models. And so we want to be able to identify not only which components, but also which processes are yielding or providing predictability at the S2S scale. And so the challenge or assumption regarding the machine learning framework is that we want to be able to represent a very high number of complex processes that affect the Earth system at the S2S scale, including feedbacks. And so for that, we had to address basically three methodological questions. One was what to predict. The other one was what variables represent the Earth system, for which we did kind of a review of literature to be able to select those variables, and then what machine learning model to use that was able to identify those sources of predictability. And so regarding what to predict, we focus on the large scale or the weather regimes, which is less ambitious than predicting surface anomalies, to basically simplify the problem a little bit and get some skill from the machine learning models. And so for representing the large scale, we computed the weather regimes. So we basically used daily geopotential height data from 1981 to 2020. We extracted a region of interest that covered North America, removed the annual cycle and the regional trends, and then standardized the data to get the Z500 anomalies. And then after that, we reduce the dimensionality using PC analysis, and then we compute like k-means clustering on the data to obtain 4 weather regimes. This is consistent with the method presented by or posed by Simon Lee to get year-round weather regimes instead of just for the cold season. And so these are the 4 weather regimes: the Pacific Trough, the Pacific Ridge, the Greenland High, and the Alaskan Ridge. These weather regimes have significant surface anomalies regarding temperature and precipitation, and not only those variables, but also storm tracks and so forth that has been shown in the literature, and they're pretty relevant for S2S prediction. They are so relevant that there is some literature that shows that predicting correctly the weather regimes, and then from that predicting the composite temperature precipitation might be even as skillful as predicting directly the temperature and precipitation anomalies. So that makes them relevant to study and to try and predict them. So we have already the issue solved of what to predict. And then the next question is what predictors to use to represent their system. So we take 4 variables from the atmosphere, representing mainly the large scale, but also the stratosphere. We take 9 variables from land, including soil moisture and temperature and snow depth. And we also include many ocean heat content variables, and also sea surface height, sea surface temperature, mixed layer depth, and some ice properties. And so to each one of those variables, we do a similar pre-processing to what we did to the geopotential height. But for them, we take the weekly average at week 0. And so that will be the predictor from each variable, that weekly average anomaly, standardized anomaly at week 0. And so what's different from some work that has been done regarding Earth system prediction with machine learning is that we're going to train different models with each variable individually. So it's easier to identify and compare the skill of each variable to each other in a kind of more clean way. And so, for example, we have SST at week 0. And so the input will be the field at week 0, and then the output will be one of the 5 classes, or 4 weather regimes plus no weather regime class that facilitates the analysis and makes the weather regimes cleaner. So the next question is what model to use. We tried different models. We tried different neural networks and also XGBoost, and we decided to stay with XGBoost since it showed comparable skill to the deep learning models, and it also has a low computational cost, and it also has fewer hyperparameters to tune and lower sensitivity to them, so it makes it more robust and allows more fair comparison among variables to be able to conclude with more confidence. We did cross-validation and cross-testing in the whole period in order to extract information from the whole period. And we did an exhaustive hyperparameter optimization. So we get the best possible model for each variable and for each lead time. So there's a lot of variables and a lot of lead times and a lot of training rounds, and all that was possible thanks to the GPUs that Cecil provided. And so here's an example of the results that we're interested in. In the y-axis in this plot, I have the F1 score representing the skill of the model. In the x-axis, I have the lead time that goes from week 1 to week 8. And these are, each line in here is the skill of a model trained with a different ocean variable, in this case. I also have here this blue dashed line, which represents the skill of a model trained with all the variables at once. And we see that it doesn't show increased skill compared to the other variables. And then to assess significance of this skill, we compared with the skill of the persistence of the persistence forecast and of random forecast, both just random and then also considering the climatology. And so everything that shows skill above those 3 thresholds and the confidence intervals, we assume that it's contributing significant skill to the predictions. So we did the same exercise for the 3 components, right? We have atmosphere, ocean, and land. As expected, we see that the skill of the atmosphere decreases with time, and the skill of the ocean and land remains more or less stable across lead times. Now, to compare directly the three components, we take the best model from each component. And so that is, for example, the yellow line is the best model for the atmosphere at each lead time. And if we compare these results to what Yaga showed yesterday, it's not directly apples to apples, but we see something similar, which is the atmosphere being the most important component, apparently up to weeks 3, 4, and then the ocean and land being kind of stable across lead times. However, this represents the predictability in a very general sense, and we wanted to understand specifically in which seasons and which weather regimes and which specific variables were providing more predictability. And so if we stay at the general perspective, it's very difficult to differentiate which variables are really providing the predictability, right? This is this indicates which variables at which lead times provide meaningful or significant predictability. And if we just compare this, it's very hard to differentiate or to extract meaningful information from here. So we went deeper and stratified these by season and by weather regime, and got something like this in order to see in which weather regimes and in which season we actually have meaningful predictability. One something that we not saw, or one result, is that a lot of this predictability came from predicting the no weather regime class during summer, which is not very interesting, right? But still, if we go beyond that, we see that, for example, for the Pacific Trough, Pacific Ridge, and Greenland High, especially during winter and fall, we see significant predictability coming from the ocean, from the atmosphere, and from the land in many lead times that go beyond even week 4. And so if we zoom in on those, we can start noticing some interesting things. For example, we see that ocean heat content variable seems to be important, especially for the Pacific Trough and Pacific Ridge. We see sea ice showing up also as relevant for the Pacific Trough and Pacific Ridge. We noticed that the stratosphere showed relevance only for the Pacific Ridge in our models, which was somewhat surprising. And we also saw some other variables such as U200 and geopotential height being important, and also OLR specifically for the Greenland High. In terms of the land, we saw that the weather regime that was most affected by land was the Greenland High, especially regarding soil moisture and also snowpack or snow depth. And so the next question after this is, what are the regions or what are the processes that matter regarding these variables? Like where are the models looking at when doing these predictions, and if the skill that apparently we have from those is actually physically meaningful. And so for that, we are going to use explainable AI, which has been proven to show or to be useful to understand where the machine learning model is looking at and to highlight regions that offer certain predictability, especially at the S2S scale. And so the method we use is the Shapley values, or SHAP, which basically quantifies the contribution of each feature, in our case, each pixel or grid cell, to the final prediction. And it has some nice properties that makes it preferable to use with the XGBoost model. And the most important one is local accuracy, which basically means that the output of the model can be put in terms of the importance of each pixel. And so, for example, we can get the output of the XGBoost model, which is the likelihood of a weather regime happening, as a function of a base value, which is basically the climatology probability of the weather regime, plus a function of the sum of the importance of each pixel. And so that differentiability makes it kind of clean in order to compare one pixel to another. And so what we do after that is that we averaged those Shapley values across cases that presented correct predictions of each weather regime. And so, for example, in here we have the average SHAP values for correct predictions of the Pacific Ridge in week 6, which is 109 cases. And so we see that the method highlights this region in here. And if we look at the week 0 composites of SST, then we see that it's corresponded with a La Nina pattern. And so, of course, the most notorious thing that we encountered, which also increased the confidence in the methods, is that the ENSO was pretty relevant, especially for the Pacific Trough and the Pacific Ridge. And that is consistent, not only coming from the ocean, but also there are atmospheric variables that show ENSO-related patterns. So like OLR, for example, or Z500, which provide predictability to the Pacific Trough and Pacific Ridge regimes. And there's also consistency of the SHAP values highlighting these tropical regions. And so, as I said before, it increased the confidence we had in the methods. And so we also looked at other variables that helped predicting correctly some weather regimes. And so we found that ice thickness and ice concentrations were also relevant for the Pacific Trough and Pacific Ridge regimes, which is consistent with recent literature that indicates that less ice over the North Pole favors the occurrence of ocean lows. We also found some interesting results regarding the stratosphere and the Pacific Ridge regimes. However, we didn't find a lot of literature regarding specifically the stratosphere and the Pacific Ridge. We had a couple of hypotheses. One is that sudden stratospheric warmings affect these events. And so in here we have the probability density of non-sudden stratospheric warmings versus sudden stratospheric warmings. And if we compare, this is for the general data, and if we compare that with correct predictions of the Pacific Ridge, we see increased occurrence of sudden stratospheric warmings. But this is just a hypothesis that we're still looking, as well as looking at the QBO, for example. And I'll go very quickly through the others since I'm running out of time. We found relevance regarding the OLR for an MJO for the Greenland high, consistent with literature. And we also found some kind of unclear results regarding the soil moisture and the snowpack. But yeah, if you want to take a deeper look into these results, you can go to the preprint. So the conclusions are that exhibits could see previously identified sources of predictability and could shed light into potentially new ones. And so ENSO and MJO were highlighted, with ENSO being more relevant. And there are also two that are kind of more mysterious, which are the stratosphere being important and the snowpack and soil moisture for the Greenland high and Pacific Ridge. Finally, I just wanted to mention very quickly some work that we're doing regarding Lens 2 and the representation of weather regimes. We found that the weather regimes are well represented in terms of frequency and duration in Lens 2 compared to ERA 5, and we're finding some trends that might be related to non-internal variability, but more to a forced change regarding some weather regimes. And I'll leave you with the summary slide. Thank you so much. I cannot hear. Yep.
Can you hear now?
Yeah, I can. Now I can.
Hi, Dara. Nice talk. I was wondering if you were surprised about the lack of importance of outgoing long-wave radiation for your predictions.
Yeah. I was really surprised. I expected it to be more, not necessarily more important, but to appear more as important for other weather regimes, not just the Greenland high. And with such scattered relevance, I expected to see something more robust. And yeah, it's definitely interesting to see more or investigate more into that MJO stratosphere and then weather regime connection, which I think there's some literature regarding it. But so yeah, it's like that the chain of events is kind of difficult, and maybe also the models aren't getting it right.
About the chain of events, I was wondering with the Pacific Ridge stratosphere connection, is there a chance that like ENSO would be driving both of those, or does the method kind of prevent that?
So you mean in this case, like La Nina, for example, going like affecting then the stratosphere and then affecting the occurrence of the Pacific Ridge? That's a great question, and I think it'll be interesting to look at it. Definitely, the Pacific Ridge is more related or more associated, or correct predictions of the Pacific Ridge are more associated with La Nina happening. And it might be that both are like both ENSO affecting the stratosphere might be playing a role together. But for that, it's harder to see, because then we'll need to, I don't know, evaluate both models in kind of in a joint way or something like that. But yeah, it's an interesting hypothesis, I would say. Thank you.
I should just prep for Gyron going before me, because I think this is the third time I've given a talk and he's heard before me, so there will be some redundant content here, but that's always nice to see. Okay, so the research I'm presenting today is work that I've done with Katie Dagan and Maria Molina on can transfer learning help identify tropical state-dependent bias relevant to mid-latitude subseasonal predictability. I realize that's a really long title, and I hope that it'll become clear. I'll bring the slide up at the end to answer it. So hopefully by then you'll all understand what I'm talking about here. But basically, in an overarching sense, what I'm interested in is a data-driven approach to identify biases associated with sources of predictability. So to start off, what I mean by state-dependent predictability, or often referred to as forecasts of opportunity, is this concept that certain conditions in our atmosphere and our ocean can lead to more predictable behaviors than others. And one of these is known as the Madden-Julian oscillation, or the MJO, which we've talked a lot about. Another one is the El Niño Southern Oscillation, or ENSO. And when these phenomena are active, there's some feedback. Okay, cool. And when the MJO is active, we can use information about its state, so it's state-dependent predictability, like how strong it is, how fast it's moving, where it's located, to improve our prediction scale of what will happen on subseasonal timescales over the mid-latitudes. Specifically, what I'm going to be focusing on here is boreal winter, so winter time in the northern hemisphere. And some of my previous work has shown how we can use state-dependent predictability, or how we can identify state-dependent predictability using a neural network. And how we do this is we apply in a categorical sense. There is research showing that you can also do this for a regression sense, but I'm only going to talk about categorical here. But in this categorical sense, what we do is we apply what's referred to as a softmax activation function. And what this does is it takes the output of our neural network and sums the value to 1. So since this is a binary classification problem, our two values will ultimately sum to 1. So we have 0.88 here and 0.12. In this case, let's pretend we're predicting whether we have a warm temperature anomaly or a cold temperature anomaly. Because this is binary classification, if the value is above 0.5, that means that we're predicting that class. And in this case, we're predicting a warm temperature anomaly. And we can see that the value is very close to 1, which is what I'm going to talk about here in terms of what we're going to refer to as confidence. So you can imagine, instead of having a value that's very close to 1, we have a value that's a lot closer to 0.5, suggesting that our neural network isn't as sure that this should be a warm anomaly versus a cold anomaly. So the question that we asked in this paper was, when the value is closer to 1, does that actually mean that our network is more correct? And this is a concept that Melissa Bernine talked about a little bit yesterday. So in a graphical sense, we have confidence on the x-axis here and accuracy on the y-axis. And we're asking the question, as confidence increases, does our accuracy increase? And if this is the case, we can use confidence as this proxy to identify forecasts of opportunity, or these periods where we have enhanced predictability, or in this case, enhanced accuracy. And what we found in the paper that I have on the bottom here, if you're interested in learning more, is that we do in fact find that when we have this relationship, we're able to identify subseasonal forecasts of opportunity. We can then take this a step further and focus on those forecasts of opportunity in that upper right quadrant of the diagram using explainable artificial intelligence. And Jaron nicely touched on this earlier, but basically in using a cat as an example, my favorite animal, we have a neural network that's been tasked to predict whether there's a cat in an image. And what XAI does is when the neural network says, yes, this is a cat, you can back propagate that information through our neural network to create a heat map of the relevant regions that that neural network used to make that prediction, that it was a cat. And what you can see is that our neural network is indeed highlighting that there is a cat in this image and where the cat is located. It's not necessarily highlighting some random place on this image. So we can see that it's identified something physical. Okay, so now I want to take this research even one step further and apply explainable neural networks to identify state-dependent predictability bias. And in this regard, I'm interested in bias as defined as a systematic difference in sources of enhanced predictability between models and observations. So said in an example form, what I'm really interested in is if we were to train a neural network purely on model data, I want to understand what sources of predictability led to enhanced predictability in the model sense. And then if I were to train a completely separate neural network on observational data, what would that heat map ultimately look like? Was it going to look at different sources of predictability? Is it looking at the same sources of predictability? So we're trying to get at this predictability bias, or sources of predictability different if we were to train on a model versus observations. But unfortunately, on subseasonal timescales, reanalysis data isn't very long, and it is very difficult to train neural networks that are robust across many years. And so we're going to take this concept that I just brought up, but instead use transfer learning. And so transfer learning is this concept that if you have a problem that's very similar to your problem of interest and it has a lot of data, you can train that model on that large amount of data to learn basic stuff about, for example, the atmosphere. Then you know that that data may be biased, like climate model data. We have a ton of it. We can train a neural network, but it may not perfectly represent our atmosphere. And then we can update that neural network using our limited data set, or our information that we're actually interested in, which is our reanalysis data set. And so we're going to take the weights or the knowledge that our neural network has learned and transfer it to our final neural network, and then tune those weights to update and account for these biases that the model may have learned training on climate model data. Then using these XAI techniques that I talked about, we can explore what the neural network was looking at when it was only trained on the climate model data, and then how this XAI heat map updated after we've fine-tuned our model for reanalysis data. So to test the feasibility of this approach, we decided to use a perfect model framework. So we're using E3SM here, but we've also done this work using CESM. But within the E3SM case, we have 20 ensemble members. And what we decided to do is split those ensemble members in half and add a fake state-dependent bias to half of those. And we're going to call that the climate model data. And then in the other half, we've left them as normal, and we're going to call this truth, or our reanalysis data set. And this has no bias in those members. Okay, but before I talk about what this actual bias is, I'm going to tell you about the prediction problem. So what we're interested in here is the relationship between the tropics and the mid-latitudes on subseasonal timescales. So we focused on using tropical precipitation to predict the geopotential height circulation anomaly at 500 hectopascals, and we're only predicting the sign here, so a positive or negative circulation anomaly over the North Pacific. And we know that the North Pacific is influenced by tropical precipitation through phenomenon like the MJO and also ENSO. We're focusing on the week 3 time frame. So what we decided to do is add a tropical state-dependent bias only when there is an ENSO event, so an El Nino or a La Nina event. What we did is we took our tropical precipitation and we just reassigned what the latitudes are, shifting the whole tropical precipitation 60 degrees east in those members, which should be a very clear signal in terms of a bias here. So we initially train our model using our neural network using this state-dependent bias, and then we transfer those weights to update using our non-shifted data from E3SM. Now, if transfer learning works, we would expect it to unlearn that shift or learn that there's a new region to focus on. And so in that regard, we would expect that our performance of our pre-transfer learning network with the bias should be about equivalent to our post-transfer learning network. And that's what we find here. This is our confidence versus accuracy diagram that I was talking about earlier. We find that both our pre and post transfer learning models perform similarly and are both skillful, and they're both able to identify these forecasts of opportunity because as confidence increases, our accuracy is also increasing. And so we can use those confident predictions to explore the state-dependent predictability. Now I'm going to pretend that we don't know what this bias is that I've added because I'm really curious about whether we can use confidence as our way to identify state-dependent predictability. So I'm going to pretend that I don't know that ENSO is what's biased here, perfectly biased. So what I'm going to do is instead focus on these confident predictions for our composites of our heat maps. So now I'm going to take our biased transfer learning, or our pre-transfer learning network that has the bias members, and compare those heat maps to our post-transfer learning network that's been retrained. And so this is our pre-transfer learning model using the bias members. We can see it's focusing on this region just to the west of South America. And then if we then look at our post-transfer learning network on our unbiased testing members, we do in fact see that there's a shift in focus, at least 60 degrees east. But what's also interesting here is that the region that was originally important for this prediction is also still highlighted in this post-transfer learning network. Okay, so what I haven't really highlighted here is that these results, I'm using 9 ensemble members to retune. And as we all know, we don't have 9 ensemble members of our real world. And so we had the question of how many ensemble members does it actually take to have transfer learning work? So the question is, what if we had 1 ensemble member or 2 ensemble members, all the way up to 9 ensemble members? And that's what I'm showing on the x-axis here, accuracy on the y-axis. And then the bottom violin plots here are the accuracy for all predictions, and the top violin plots are the accuracy for the 20% most confident predictions. And then the scale of the pre-transfer learning model is on the far right in the green violin plots here. And like I said before, we would expect the accuracy to be very similar if we were indeed correcting for this bias. And what we see that in this set of members that we use to train and validate our model, the testing member, it takes about 2 training members to actually identify this shift and correct for it. And since we're using the historical data, this is 1950 to 2014, this is about 128 years of data, which we would require data from before 1900 in that regard, which arguably we do not have, especially for tropical precipitation. Okay, so since we've trained all these models with iteratively adding the number of training members here, on the top plot, we have our pre-transfer learning model, which has been trained with that bias. And then I'm highlighting the XAI heat map for those confident predictions when we've updated to the same accuracy as our pre-transfer learning model. And what we see is indeed, we have a very similar heat map to the 9 transfer learning members for retuning, which is that bottom right plot. But what we found interesting here is that when we retrain with 1 member, which is a lot more like using reanalysis to retrain, we see that the heat map kind of disappears for that 1 training member. And we do know that it doesn't perform very well, so this could be related to that. But it's also interesting that this blob just west of North America, or South America, disappears basically and then reforms as important. So what we decided to do is just take our original neural network, and instead of training it with our bias members, we train it with just normal E3SM data and do the exact same prediction problem, and then decided to compare our no transfer learning approach to our post-transfer learning approach. And what we see is that these are relatively similar heat maps, suggesting that instead of retaining that information to the west of South America, the neural network seems to have forgotten it and then relearned it, which suggests to us that we need a lot more members in transfer learning to actually identify these biases. So the question was, can transfer learning be used to identify tropical state-dependent bias relevant to mid-latitude subseasonal predictability? I'm going to say kinda. We saw that transfer learning worked, and we saw that we were able to identify the bias as it was clear that there was a shift in our regions of importance, but we clearly don't have enough reanalysis in this specific setup. Once we have 128 plus years of data, come talk to me.
Questions?
The amount of data you need depend on the size of the bias?
Yes, we are only focusing on this shift, and if the bias is shifted eastward and northward, for example, I would expect we'd need more data depending on how strong the shift is. If it's located in a different spot and it's just like an amplitude change, I think this would all affect how many members we would need. And given that ours was a pretty clear hammer to the system, we think that this may be like the bottom number of members needed.
So a smaller bias would need more.
Yeah, it actually might be harder for the neural network to identify a smaller bias. That's all hypothetical, my understanding of what's happening here, but yeah, could be the case.
So related to that, you're only adding bias during ENSO events. I don't know how you define that, but that drastically reduces the sample of when there's a bias present.
Yes.
In models, there's bias, I mean, non-event years as well.
Yep.
So maybe it's more optimistic in that sense, right?
Yes, but on the subseasonal timescales, we're especially interested in these forecasts of opportunity to improve our skill, which is why we decided to focus on adding bias purely to our state-dependent predictability. But if we had even more bias, which is what you're saying, we have bias in our sources of predictability or forecasts of opportunity and in the base system, I think that would actually take more work to correct for than just the state-dependent predictability.
You showed a plot where you had the ensemble members on the x-axis and then you had the sort of skill scores of accuracy. Yeah, this one. What's going on there with member 5? Can you explain why the accuracy goes down for 5 and 6 members?
I do not know why it goes down. Yeah.
Thanks.
Yeah. And sometimes we actually have members. So I have a plot here. Here, where we use different testing members. We do a k-fold analysis. And so what I showed was an example where we have 2 retraining members that are needed or fine-tuning members, but we have examples of 1, which is more like reanalysis, but over half require 2 or more retraining members to actually identify the bias.
Any questions? All right, thank you. We'll move on to our next speaker, is a virtual speaker. Gabrielle Bragg. So I will stop sharing. So you can share.
Can you see my screen?
Yep, it's coming.
All set?
This point,
Say that again.
Yeah, but can you put that in presenter mode? It's down
I think
at the bottom right, it looks like a little podium to the left of your positive N plus slider. Sorry.
okay. Sorry about this. Okay. Let's see if this does it. Is this
Yep, that looks good.
Okay, great. Glad. All right, so hi everybody. My name is Gabrielle Brown. Thank you for your patience as I figured out all this tech issues. But I'm a second-year master's student at the University of Oklahoma, working under Dr. Kathy Pijon. And today I'll be sharing my work on developing a framework for evaluating sources of predictability for extreme events on subseasonal timescales in Southeast Asia and Latin America. So with that, we can kind of jump right in. So we know that climate change impacts are occurring currently in the form of extreme weather. And depending on the region that these extreme events occur in, it can lead to some substantial insecurity, especially in more vulnerable regions. And so the diagram I'm about to show is kind of walks us through how that's the case. So in a particular area or country, there can be antecedent conditions such as inequalities, maybe weak institutions, or a history of conflict. And then there's an onset of some sort of exogenous climate shock. And that can be in the form of floods or drought, or maybe even a heat wave. So with that, we have your expected initial primary effects, which are water and power shortages, or maybe even a loss of property. But then there are, for more vulnerable regions, the secondary effects, such as anticipated livelihood disruptions, where many people don't know how to move forward in ways such as growing enough food or making enough money to support their families. So this kind of creates a tinderbox, one might say, where some groups may view this as an opportunity, such as opening in the social contract, opportunity to increase strength or status, whereas others can see it as grievances. Maybe they see inequity or exclusion, differences in ideology, or maybe just an unmet response expectation to the said climate shock. So overall, this can lead to instability in the form of migration, protest, or even violence. So the goal of this project is to reduce the potential for insecurity by reducing the impacts. And to do that, we're trying to intervene earlier in the process and further inform adaptation and preparation decision-making by using a more actionable timescale, such as subseasonal forecasts or predictions ranging 2 to 8 weeks ahead of the climate shock. So providing advanced warning and advanced notice. But going beyond this, we're trying to enhance the accuracy and lead time of subseasonal predictions and identify key drivers and mechanisms contributing to the predictability in various geographic regions. So with that, we're developing our framework with the use of 2 case studies. These are both extreme precipitation events, and they were chosen based off of the impact to both of these regions, which is Pakistan and Peru. So the first is the 2022 Pakistan floods, and the second is the extreme precipitation and Cyclone Yaku that occurred in Peru back in 2023. So the data sets that we're using for this work are the Climate Hazards Group Infrared Precipitation with Station Data, which is a high-resolution gridded data set used to capture detailed characteristics of the precipitation in both regions. Next, we're using the ECNWF Reanalysis version 5 or ERA 5 data set, which is being used to investigate variables going beyond the precipitation, including some of our potential drivers or mechanisms behind the precip. And then lastly, we're using the NSF NCAR Community or System Model version 2, subseasonal forecasts and reforecast experiments. So with this, let's talk about our research questions. Now, these research questions are the foundation of this framework. So the first is, what are the defining characteristics of the extreme event, including determining what those potential drivers or mechanisms are behind the event? The second is, how far in advance could we have provided useful forecast information to the impacted region? And then lastly, what Earth system components contributed most to the predictability and just general occurrence of the event? So for the sake of today's presentation, just for the sake of time, I'll be focusing solely on the 2022 Pakistan floods case study and talking just a little bit about our initial findings with Peru. So as many of us may know, in 2022, Pakistan experienced anomalous precipitation in July and August. The figure below kind of shows the annual average precipitation anomaly for July and August. And as you can see, shown by this red arrow, 2022 is substantially more positive in July and August compared to any other year between 1981 and 2023. Now, looking at the daily average precipitation anomaly, the extreme events over the course of the summer were separated into events. Now, existing literature's definition or separation of extreme precipitation on the 2022 Pakistan floods can vary. Some have separated the events into 3 events subjectively defined by the peaks in duration and above average precipitation, shown by this daily average precipitation anomaly plot, where you can see event 1 in orange, event 2 in yellow, and event 3 in red. While others, because there's been a lot of research on this topic, have separated the events into 2 events separated by the month July precipitation compared to August precipitation. And they've done this because there were varying drivers or mechanisms behind each month's precipitation. So considering that the preset definitions can vary, we move forward with the idea that there were 3 separate events and kind of allowed the reforecast experiments to kind of aid us in determining if this was good to move forward with or a solid definition to move forward with. So now let's talk about what we have found for potential drivers. Now, I do just want to acknowledge that the drivers I will be discussing today may not fully capture the full range of contributing factors, but they are the most commonly identified amongst existing literature. But we have taken all the potential drivers and evaluated them with ERA 5 data to ensure that we're getting similar results as to what previous work has gotten on this project. So the first potential driver I'll talk about are just monsoon pulses. Research has highlighted that the extreme precipitation could be due to just 3 distinct strengthened monsoon surges. The second is sea surface temperatures. At the time, negative sea surface temperatures were present in the Indian Ocean basin, which previous research has highlighted may have weakened the meridional temperature gradient, potentially leading to our third driver, which was this anomalous easterly wind south of the Tibetan Plateau. Now, these were really prominent features of the precipitation in July. While they were still present in August, they were just substantially weaker. But the last potential driver I'll talk about is very specific to August, and that is a blocking pattern elsewhere, specifically over Europe, that led to a circulation pattern over Pakistan that was really conducive for precipitation. And like I said, this was very specific to the August precipitation. So with this in mind, we can talk about our experiment data. Now, I know that many attending today and from the presentations, everyone's very likely well versed in the CSM2 reforecast experiments, but just to give a brief overview, this unique set of initialized prediction experiments is separated into the 3 Earth system components: atmosphere, ocean, and land, and it uses climatological initial conditions to determine the sources of predictability. So the table to the right shows each experiment and displays which components are set to lead time dependent climatology given the experiment being looked at. So with this in mind, how did we personally use the experiment data? So ultimately, we converted our forecast and experiment data to anomalies and used anomaly correlation coefficients. Now, the plot to the right shows an example of how we visualize this data, but we specifically applied these experiments to understand the predictability of precipitation. So the title of this plot, and then all the plots that I'll be showing from here on out, is the week being forecasted for. Each week we forecasted for was a week that contains some dates in July and August of 2022, and they align with the initialization dates of the model just for easier comparison. So the x-axis shows the lead time in weeks, and the y-axis shows the anomaly correlation coefficient, where -1 is a perfect incorrect forecast, so the opposite of what we would expect. 0 shows that the model had no skill, and 1 is a perfect forecast. So generally, positive values will indicate that the model had some sort of predictive skill in forecasting that week being forecasted for. So as an example, I did want to bring to light just 5 plus weeks. So 5+ weeks ahead of the week being forecasted for, which this week specifically is the first week that contains any dates in July, shows that the atmosphere was higher, or was a higher source of predictability, shown by the blue and yellow bars, being increasingly positive compared to the ocean, which was negative, or which had negative anomaly correlation coefficients and kind of hovers around 0, and that's shown by the green and black bars. Excluded from today's presentation are the experiments that focus on the land's contribution, as we found that the contribution was much less than that of the ocean and the atmosphere, so we decided to exclude that from what we're showing today. So with this in mind, we can take a look at the sources of predictability for July. So our initial takeaway was that the general subseasonal forecast, which is shown by the red bars, was rather inconsistent from week to week in terms of lead time and in terms of the week being forecasted for. It was relatively high in variability, which was a little unexpected. But looking at the reforecast experiments in early to mid-July, specifically the first 3 weeks being shown, we found that the atmosphere played a more dominant role in predictability, which was shown by increased instances of the blue and yellow bars being increasingly positive compared to the green and black bars representing the ocean's role. However, this did an interesting flip during the 4th week, so the 18th to the 24th of July. The ocean contributions to predictability increased substantially, and the atmosphere's role decreased, shown by the blue and yellow bars being negative or kind of hovering around 0. Now, we found this to be really interesting because this 4th week aligns with the second extreme precipitation event that was shown by the yellow shading in a few slides back, when discussing how the extreme precipitation over the course of this summer was split up in existing literature. So, with that, we found that for July, the atmosphere played a more dominant role in the initial extreme precipitation event, so the first one, but the ocean played a heightened role in the predictability of the second extreme precipitation event. Now, looking at August, similar to July, we found that the general subseasonal forecast was high in variability and overall inconsistent. Further, for much of August, the atmosphere played the largest role in the sources of predictability to the ocean. So the third extreme precipitation event's sources of predictability mainly came from the atmosphere. So just as we kind of wrap up this presentation, I wanted to revisit my research questions that I initially posed towards the start of my talk. So the first was, what were the defining characteristics of the extreme precipitation for Pakistan during the summer of 2022? And we found that there were a variety of drivers identified as potentially playing a role in the extreme precipitation events, including strengthened monsoon pulses, negative sea surface temperatures, anomalous easterly wind, and a blocking pattern over Europe that led to a circulation pattern over Pakistan that was really conducive for precip in August. The second was, how far in advance could we have provided useful information to Pakistan in regards to the forecast? And we found that the predictive skill varied from week to week and overall had limited consistency. And then lastly, what Earth system components contributed most to the predictability of the event? And we found that the atmosphere dominated in predictability, and the ocean did have episodic but still significant contributions, especially during that 4th week of July that encompassed the second extreme precipitation event. And for this reason, since there was kind of a flip in sources of predictability from event to event, we have stuck with, there being 3 extreme precipitation events. But in terms of next steps for Pakistan, we do plan to kind of apply the reforecast experiments to the potential drivers to see if this is still the case, and kind of to see if we can better understand which played a more significant role in the precipitation over the course of this summer. But in terms of broader next steps for this project, we kind of plan to apply this methodology to look at the extreme precipitation that occurred in Peru in 2023 as a result of Cyclone Yaku in early March, and more broadly as a result of the coastal El Nino event that occurred at the same time. Looking at this plot below, it's the March, April, and May annual average precipitation anomalies. And as you can see from 2023, it's substantially more positive than any year between 1981 and 2023. Additionally, looking at the plot above it, it shows the April sea surface temperature anomaly, which has very high positive anomalies off the coast of Peru, and we are identifying that as a potential driver. So we really look forward to seeing how the forecast and reforecast experiments compare with a different event and a different geographic region overall. But with that, I will conclude my presentation, and I would be happy to take any questions or feedback for how I can continue to improve this work. Thank you so much.
Questions, Steve?
Thanks, Gabby. I have a clarification question. You were showing ACC skill as a function of week, right?
Yes.
So
Yes.
doing a kind of spatial correlation, I presume.
Say that again. I'm sorry.
Normally, we would compute an ACC across many different reforecasts, not the forecast of a particular event. So are you showing spatial correlation as opposed to temporal correlation?
Yes, I'm showing spatial correlation. So these values were taken based off of the anomaly maps over Pakistan that showed the precipitation anomalies in a spatial sense. Yes.
Okay, so the CESM2 S2S system might have done a decent job of predicting anomalous kind of aggregate precipitation over Pakistan without getting the spatial pattern correct, right?
Yes, yes, it definitely could have, in considering the methodology that we're using, where we were just looking at the anomaly where it was above average compared to below average over Pakistan as a whole. Yeah, it could have, but we're looking at comparing the spatial plot. So.
Okay, thanks.
Thanks, Gabby. Nice talk. Wondering if have you looked at other variables and looking at the skill in those? I know there's some work that suggests, because models have a real difficulty getting precipitation. If you look at moisture instead, you could use that as some kind of verification.
Okay, great. I'm definitely will take that into consideration. Thank you.
Any questions? I guess I was wondering about error bars due to sampling and kind of if you've thought about maybe quantifying that to know what kind of week to week differences you should really be paying attention to, or.
I have not, but that is a very good suggestion. So I will take that into consideration, as I don't know right now, but thank you.
There's no more questions. We'll move on to the next speaker. Thank you. So our final speaker before lunch is Andrea. Oh no, nope. Okay, that is not on the schedule. I must have not paid attention to my emails. Okay, our final speaker before lunch is Meg Fowler. Soil moisture.
Yeah. I'll say
My
it's
one
better.
umbrella is prepared.
8, yeah. Okay, thanks, Alan. Is this on? Feels on. No.
You maybe want to leave it a little off.
Okay. Okay.
Yeah.
Okay, so I'm going to talk a bit about work we're doing in SPAT, looking at the limited role of land on atmospheric predictability in CSM2, which you've heard a lot about over the last few days. I'm really loud. Okay. Is that Okay, awesome. It's disconcerting to hear your voice like that. I want to acknowledge my co-authors on this work, most of whom are here in NCAR, but also Paul Dermeyer from George Mason University, who provided a lot of the plots that I'll show you towards the end of the talk. But I thought I'd start big picture with why we care so much about the land surface and its interactions with the atmosphere. Soil moisture anomalies, whether they're wet or dry, drive really important changes in the atmosphere in terms of surface fluxes, which can then impact atmospheric circulation and subsequently precipitation. And that can even extend beyond the mean state to things like droughts and floods. And one of the ways that we think about the interactions between atmosphere and land is through something called the local coupling process chain, or LOCO, which Joe introduced yesterday in his talk. But to kind of give you an idea of the ways in which these interactions happen, we consider an initial soil moisture anomaly, either wet or dry, that then impacts your surface fluxes. Those surface fluxes we usually evaluate in terms of an evaporative fraction. So how much of your incoming radiation is going towards evaporating water versus warming. Those fluxes can then impact your planetary boundary layer, or the mixed layer that's near the surface. That then impacts precipitation in clouds and can feed back into near surface temperature and moisture, which impacts how we feel the weather every single day. And it wouldn't be an SPAT talk if I didn't show this figure one more time. So the idea is that the land surface in this green line gives us a sense of predictability on a timescale of like 2 to 4 weeks. And this is pretty well known in theory. But in the most recent CSM experiments and some other lines of evidence, that's not what we're actually seeing. And so instead, the land surface is giving us basically no predictability within the timescale that we would expect. So one of the questions that came out of this work that Yaga and others led last year is that, are there deficiencies in the simulated land-atmosphere coupling that can help explain the limited impact of land initialization? I'm going to preface this with an asterisk and just say this is very much a work in progress, so I'm not going to answer that question today. Apologies. But I'm inviting you to kind of geek out about some cool plots with me for the next few minutes. So how we're going to answer this question is through a series of model simulations. I will note that we have the existing CSM 2.1.5 S2S hindcasts, reforecasts, which are a great resource. I'm not going to actually show them today, but important to note we'll use those in the future. What I am going to focus on is a set of climatological AMIP runs, so land and atmosphere are active, ocean is climatology. We're running it with the same model configuration, though, as was used for the reforecast. So the idea here is that we have 25 years of a control case, which is exactly what the reforecast would have seen, but we also have a sensitivity experiment. And in this scenario, what we've done is kind of go in and tune a parameter in the land model CLM that we know has an impact on land-atmosphere interactions. So I'll show you the control and then an additional experiment that has enhanced land-atmosphere coupling strength. To validate our simulations, for the most part, I'll compare to tower observations from FluxNet 2015. Again, Joe talked about this yesterday, but it's kind of our best guess for what's happening in the real world at a point. And then also against ERA 5 reanalysis. I may call it observations, I apologize in advance. It is not. So I'll show you that in a minute as well. So I want to take two approaches to answering our initial question, and I'll start with a land-based perspective. So kind of focusing in on that bottom part of the LOCO diagram. How well does CSM capture impact of soil moisture anomalies on surface flux anomalies? So to answer this, we're going to look at something called the terrestrial coupling index. Essentially what this does is it measures the sensitivity of a response variable to a driving variable. And in this case, our driving variable is soil moisture in the top 10 centimeters, and our response variable is sensible heat flux. And it's normalized in this case by the standard deviation of soil moisture so that we are ensuring that there's actually some variability in the driver and it's not just happenstance. If you want more information, there's a number of papers on this out there, but I think Paul introduced it in 2011 in his GRL paper. So if we look at the default version of CSM first, here we're looking at that coupling strength between soil moisture and sensible heat flux, shaded. Everywhere in blue is where we would say we'd have a really strong coupling between land and atmosphere, because if you have a strong negative anomaly in soil moisture, you would get a strong positive anomaly in sensible heat flux. So dry soils driving more enhanced temperature fluxes. You can compare those to flux tower observations, which are in circles. You can kind of get a sense that, the model's not doing a terrible job per se, but it could be better. And so one of the things we tried was ramping up the terrestrial leg of the coupling index. And so as expected here in the scenario, when we change the CLM parameter, we see a lot more blue regions. So if you look, for example, at Australia, at parts of the central US, you'll notice a lot more blue. So the coupling index did increase, that part worked, but this is actually worse in terms of agreement with observations. So this would then imply that it's not necessarily what's happening at the surface that's driving this. And so we're getting stronger coupling in the model leading to worse validation against observations. So an initial conclusion might be that the terrestrial coupling leg is not the culprit for limited land-based predictability. But that's just half of the picture. So let's look at the atmospheric side of things. How sensitive is the atmosphere to variations in surface fluxes? What happens once you leave the land surface? Now to look at this, I'm going to introduce a bit of a new metric, and I'll try and walk you through it. The idea is that we're looking at a convective triggering potential, or CTP, which is a measure of atmospheric stability, and it's coupled with a humidity index at low levels, high-low. This was developed by Kirsten Findel and Eltahier in 2000, and you can kind of see the combination here in this figure on the right. And so CTP measures early morning atmospheric stability. So if you have negative CTP, or like negative CAPE, or a lot of SIN, the atmosphere is too stable for rain to happen. So we wouldn't consider any land surface as being overly impactful in that scenario. But when we add in the humidity index, we start to get more interesting things. So say we have a relatively high CAPE or CTP, but our humidity index is really low. What this means is that if you get a disturbance, you might expect to get rain whether you're over wet or dry soils regardless, because the atmosphere is preconditioned to rain. If you have a really dry scenario and your humidity index is high, it's too dry, and again, a perturbation just isn't going to lead you to precipitation. What's interesting is kind of this sweet spot in the middle here, where you have an atmosphere that is not too stable or not too unstable, and humidity that is kind of sensitive to what happens at the soil surface. So I'll show you a figure in a moment looking across CONUS, but just to kind of prep you, anywhere in blue are regions that I would consider atmospherically controlled, so where the land surface just doesn't really matter in terms of potential for precipitation. Anywhere in red is kind of a positive feedback, where precipitation would rather occur over wet soil, so that additional moisture coming from the soil would lead to precipitation. And in green is the opposite. You have a dry soil advantage, where dry soils would tend to lead you to precipitation. And so if we start by looking at this in ERA 5, this is 10 years of June, July, and August daily data, and you get a sense of kind of the climatology that we see over the US, where in the western half of the US, we tend to have most summer days be atmospherically controlled. They're not too sensitive to what happens at the land surface. In the central US, you have a dry soil advantage for precipitation, or at least potential of precipitation. And then in the eastern, we have a wet soil advantage. Now, if we compare that to what we see in our control AMIP CSM2 simulation, there's some differences that pop out, and I'll highlight a few here. Typically, in CSM2, we tend to see more regions be atmospherically controlled than we see in ERA 5. This is especially true here in the central US, and also here in kind of the North American monsoon region. So that might indicate there's something physically happening that the model's not quite getting, but ERA 5 is. So overall, from the atmospheric perspective, CSM2 seems to be kind of leaning towards this atmospherically controlled scenario, so the land surface isn't having a huge impact. But all I've shown you so far is really just kind of these two perspectives, and I've kept them separate, land and atmosphere. The whole point of this is that the two interact. So can we look at the full process chain? And this is where things are going to get fun. So this is kind of a crazy diagram. I totally understand that. This is from Paul Dermeyer, and this is a pipe diagram. So if we walk through it a little bit, we start here at the surface. We're looking at soil moisture, net radiation, and surface temperature. As you move up the diagram, you move up in height all the way up to a cloud response and a precipitation response. Each box is some shade of green, which tells you about the temporal standard deviation of that variable through time. Each link then is also fun. You can have a different width, a different color, it can be dashed. All of these mean different things. So the link width is proportional to the coupling index magnitude. That kind of goes back to what I was showing you before, the coupling index between soil moisture and sensible heat flux. And so if you squint really, really hard, soil moisture to sensible heat flux, there's this tiny little line. So this is indicating that they're not very connected. And if it's a dashed blue line, it means that the atmosphere is actually controlling it. So one would normally expect surface temperature to be positively correlated to sensible heat flux. And at this station in Kansas, we actually see is that the atmospheric is control, and this is a dashed negative line. So let's broaden this. So this is an Ameriflux site here on the left, right. In ERA 5 ray analysis in the middle, and CSM, our control simulation, is over here on the left-hand side. And just as a quick glance across, you notice different colors, different widths, things don't necessarily match. So let's kind of walk through this a little bit more, and I'll start at the surface. The soil moisture variability is too weak in CSM2. So if we look at the shade of green, it's kind of the easiest thing to see. This is a really pale kind of New York Liberty green. This is a really navy blue. If you're a W fan, congratulations. It's kind of concerning, right? Even ERA 5 and Ameriflux are really different. So that kind of calls into question what we should be using as our baseline to get it right. But either way, CSM2 is too weak. If we then look at sensible heat flux variability, again, kind of concerningly, things are not moving in a logical direction. So Ameriflex variability of sensible heat flux is about 15.5 watts per meter squared. It's almost double that in CSM2. So there's something else driving a lot of variability in the model that's not present in observations. And that's just in the mean temporal variability. But if we start looking at those connections between each of these things, weirder and weirder things start popping out. So here we're looking at the link between surface soil moisture and evaporative fraction. There's a really thin dashed blue line here. So not a lot of linkage between these two in observations. In ERA5, there's a definite correlation in the direction that we'd, well, logically I would have expected, where soil moisture leads to evaporative fraction. And that's a little bit overstated in CSM2. If we move up that chain, the link between evaporative fraction and 2-meter humidity or 2-meter temperature, again, is overstated in the model relative to observations and even relative to ERA5. But again, I would note, if you look at this link between evaporative fraction and 2-meter temperature, it's severed in observations and yet present in ERA5. So again, calling into question, what do we use as our baseline? And just to kind of conclude on the process chain here, if we move all the way up to the connection between moist enthalpy and total cloud fraction, again, models are not lining up with observations. And I will note that this is all just one station and one season. This is all June, July, and August. So try and imagine like scaling this up and just the level of uncertainty that you have to try and consider, which is challenging. So can we look at the full process chain? You can, but there are a lot of sources of potential biases. And we want to look across climate regimes, land surface types and uses, seasons, everything like that. And that does complicate things a little bit. So what we're trying to do right now as part of SPAT and the S2S project is developing the tools that help us do this and choosing the right metrics that are really going to be useful for assessing biases in the models. There are, of course, a number of next steps. Most of these are in progress, but really we want to continue to assess the process chain from surface anomalies all the way up to atmospheric responses and identifying biases across locations. And then hopefully identifying different tunings we can use in the models or different parameterizations that need to be added or modified that can help us improve land-atmosphere coupling and hopefully as a result improve our predictability. And we will be leveraging case studies to assess this, including on extremes and mean biases. That's kind of work in progress, so hopefully next year we'll have that. But for now, I'll thank you for your time. Thanks.
Questions? Katie. Thanks, Meg. Can you go back to the plots with the red, green, blue over the US?
Oh, yeah.
So I was also wondering about like the mid-Atlantic coast and the New England coast.
Yeah.
Do you have a sense of why that's different in ERA5 versus the model?
That's a really good question. Not offhand, no. It's kind of a weird. Typically, when I think about land atmosphere interactions, the most sensitive region is kind of the central US. And so it's interesting that that it pops out across all the eastern US and that there's this difference along the coast. I did regrid ERA5 to the CSM2 grid. And so it might be interesting to look at like the raw data and see that it's still there. Yeah, but yeah, that's a really good point.
For someone not as familiar with land data sources, how much do we trust ERA5?
Not like a ton. Okay. There is an ERA5 land product that I think is probably a little bit better on the land side. But looking at like the Ameriflex versus ERA5, I was getting a little bit concerned, in all honesty. Yeah.
ERA5 land is still driven by ERA5 precipitation.
Yeah, so you still have those biases.
Steve and then Julie and then.
Just wondering about the pipe diagrams, whether it makes sense to compare to point measurements using a coarse grid model. Do you have a single column coupled land atmosphere? You could kind of get tuned at the Ameriflex.
Yeah. That is an interesting question. I think it's come up a few times. It would be nice to have like a suite of single column model runs we could do that are nicely tuned and validate well against observations. Even then, you're still operating basically on a grid cell. So you would remove any impacts from like effective, things coming in, but you'd still have basically a 1 degree or 2 degree land surface. So any kind of heterogeneity that you might see at a site is still getting masked when you're looking at a single column. That might play a role. Yeah, but no, it's a good point. And it's not a great comparison. Yeah.
I think another challenge with single column is precipitation, so constrained by the large scale moisture fluxes that you describe. Need a way to prevent that constraint. from
Yeah.
being under.
Yeah.
Julie?
Yes, I'm wondering why you use the AMIP run and not the coupled run. Especially for the monsoon region, I would have thought that the coupling, ocean atmosphere coupling might impact that.
Yeah, and that's an interesting point too. So part of this is kind of trying to reduce noise and look at just the local land atmosphere interaction. Running 25 years in AMIP is cheap, easy, and it hopefully will give us a good guess. But you're right, for the monsoon region, it might really help to have a fully coupled model.
Maybe that East Coast.
Yeah. Yeah, I'm wondering if the S2S3 forecasts are those AMIP or fully coupled? Yeah, so that might be another way to look at it right now. Yeah, that's a good point.
Judith?
Just a comment, we have also run uncoupled S2S forecasts, and they're not right distributed or analyzed, but we have them if you want to look at the differences. I didn't understand what a pipe diagram is. Are these correlations? Yeah. And my question is, have you just looked at the biases between the land and the atmosphere?
Yeah, like in say like humidity or just one field.
So moisture or something, or I'm not even sure. I understand that you don't have one single land data set, but yeah.
Right. Yeah, and so one of the interesting things in Yaga's paper, I think Sanjeev looked at soil moisture, and one of the questions was like, maybe our soil moisture is just terrible, and therefore getting bad, interactions with the atmosphere. But the soil moisture looked good. And so that kind of led us to the point of maybe it's the interaction, then it's not just the mean state, because the bias wasn't awful. I haven't looked at every single piece. But again, I really think it's the interaction between variables as opposed to like, we're just really biased in this one thing. Although given the variability biases as well, that might factor in.
I'm gonna say the same thing as you said yesterday. I feel like over the last 3 days, we've seen Yaga's paper mentioned a lot, and it's kind of been assumed that there's a problem.
Yeah.
But it could just be that that's the predictability that comes from the land.
Yeah.
How confident are you that there is a problem? I mean, you're trying
Yeah.
to get at it whether there is a problem, but I'm not sure that assuming there's a problem is necessarily the
Yeah.
right starting point.
Yeah, I think that's a good point. It's definitely mostly theoretical that we expect land to have a 2 to 4 week predictability window. But it logically should. I think it's been shown in some observational studies that there is this predictability that comes from a land surface state. So the question is, when we just look at a forecast, why is it not happening? And if everything looked great, even for the coupling, I would say that maybe that's fine. Land doesn't give you predictability, but from what we're looking at so far, it's not that the coupling looks fantastic. There's plenty of issues and biases. So I think it's fair to assume something's going on.
But I guess the predictability that's been looked at mostly so far is like over the whole planet and over all initialization dates, whereas it could be in like transitional regimes.
Yeah.
When you start off really dry,
Yeah.
there's predictability.
Yeah, and I think some of that we saw with Daisuke's talk as well. So like when he was looking at skill gained from adding a CSM2 member, there was persistent skill added in the desert Southwest through to like week 4. So maybe that's a region where you expect land to add a lot of predictability, but for all of US, maybe not. And so that's another, that's a good point.
Sanjeev, go ahead with your question, Sanjeev.
I had a comment, like two comment. One is, that figure has been mentioned several times. So maybe if you go with the assumption, all models are wrong. So that way it doesn't give you too much stress. But more on a serious note, one of my hypotheses is the some of the land related predictability was already coming through the atmospheric initialization. So it is a part of the atmospheric initialization. That's why we are not getting that kind of a theoretical line when we divide it using these experiments. Okay, that's all.
Yeah, that's a really interesting point. Thanks, Sanjeev.
Okay, in the last minute before lunch, Judith.
Just a comment. I mean, weather prediction centers employ many people to initialize the land. I'm sure it helps on NWP timescales. So I mean, at least the first 10 days, or week 1 and 2, I'm sure we can reach out and look at the literature. There's also a paper by Matt Newman and colleagues they use a limb and they have this reemergence of predictable and soil moisture, but they're fitting Lin to observational data and they're finding predictability on the S2S timescale. I think there's lots of evidence that there should be skill above 0 on the S2S timescale from the land initialization.
Great. We'll break for lunch. So we're coming back at 1. Yes, 1 o'clock. Let's thank all the speakers again. Have you prepared anything for the discussion or?
Reform. It's kind of odd how we scheduled the break though. Got 1 hour break. The discussion goes nowhere early.
He's currently, he said 20 minutes.
Yeah. Sometimes it's live and sometimes it's not.
Yes, oh, yeah.
Yeah, I feel like it's a little hard having it, not having just have the overview. Then
Right,
it's like,
right.
things that people triggered.
We've got a remote presentation.
Okay, perfect. Yeah, we do. Yeah, I'm all set as soon as they're, as soon as they turn their camera on and
Okay.
share their screen, we'll be able to communicate that.
Thank you. Thanks for coming. Okay, we'll get started again. Thanks everyone for coming back. We've got 2 talks here after lunch before we move into a discussion session. Our first speaker is Andrea Mollad. Andrea, if you go ahead. Sure.
Hi. Can you guys see my screen?
Yes, we can see your screen, but can you put it into full screen presenter mode?
Oh, good.
Perfect.
Okay. Hi. Thank you for including this talk as part of the workshop. I think the topic here is a little different, and perhaps maybe part of the discussion later, the organizers can weigh in on whether these kinds of talks are appropriate for this working group meeting. But this is basically a systems talk. This is to present some of what we have been doing here at NASA GMAO as part of our new S2S, GIOS S2S3 seasonal prediction system that we're going live with in the next month or 2. So here I'm going to talk to you about the ensemble forecast perturbation strategy that we've worked through and are happy with the way that we've done things here. Just a very brief, maybe it's obvious to folks, maybe it's not, about why NASA is doing seasonal prediction, what this whole effort is about. Certainly it's not our responsibility to provide seasonal forecasts to the nation. But the idea here is that our main raison d'etre here is to develop innovative uses of satellite data specifically to improve subseasonal or seasonal prediction skill. The main areas that we've been focusing on here are assimilating sea surface salinity and aerosol optical depth as part of our system. But of course, we need to maintain a state-of-the-art system to do this. And so we engage in the coupled model development, the seasonal prediction group, the ocean analysis development, the perturbation strategy for the ensembles, as well as some of the predictability studies. Our version 2 was released in November 2017. It's getting a little long in the tooth. And our version 3 system is, we've completed all the retrospective forecasts. And here it says 50%. We've completed all of them now, and we're going for release. We've caught up to real time, and we're going to release in the next month or two. And so just a little bit of a characteristics of our model coupled assimilation system that we use for initialization and the ocean assimilation system. The key element here and the unique element for us here is what I've got in that first line in pink, which is we include a prognostic aerosol model and a higher order cloud microphysics, so the aerosol cloud interaction in our seasonal prediction system. These kinds of things are usually present, obviously, in climate projection systems in the decadal, but typically not in seasonal. So we're actually providing seasonal forecasts of aerosol, dust, et cetera. I guess that this is what's mostly relevant here. So the main topic here that I want to talk about is our forecast ensemble strategy. There are two aspects of the ensemble strategy that I will talk about here. One is how we do the ensemble perturbations, and the other has to do with the ensemble size. So, because both were changed as we evolved between our version 2 and version 3 of our systems. The motivation for the change in the ensemble perturbation strategy was that essentially we looked at the tropical Pacific SST and we found that it was under dispersive early in the forecast, over dispersive later. Just a word or two about these confidence, the forecast confidence measures and the what under and over dispersive means. In the lower left, if we can think about evaluating the confidence of forecasts by comparing the ensemble spread, how far apart the members are, and the mean error, which is how far away they are from the truth, we can distinguish between a good ensemble and a bad ensemble. This is a slide, a depiction of this that was taken from a talk that I found online that was done by Eugenia Townley years ago. A good ensemble on the left is an ensemble where the green line, which is the mean error, the truth, excuse me, and the ensemble spread is within those two black lines. And so the ensemble spread covers the truth. The bad ensemble on the right is where you've got this really tight ensemble and you've got the truth, that red dotted line far outside of your ensemble spread. That would be a bad ensemble. And the metric, there are several metrics for this. The metric that we look at here is this so-called R ratio, which is the ratio of the intra-ensemble standard deviation and the standard error. These simple algebraic equations are here. And so this R, which is that ratio, if it's less than 1, we say the model is under dispersive, which basically is saying we need to increase our spread a little bit relative to what the error is going to be. And if it's bigger than 1, we're over dispersive. And if you take a look at the plot on the right, lead month on the x-axis and start month is on the vertical axis. We see the blues on the left, which suggests that early in the lead month 1 and 2, we are a bit under dispersive. We want to expand a little bit. And on the right, we see the reds, which is suggesting that we're over dispersive. So we wanted to tighten this up at both ends. And so the idea is that we went to this method called synchronized multiple time lag. This was mostly developed by Siegfried Schubert and Anna Borobakov. The early work of this is in a technical memorandum in 2019, but the idea is that we are selecting perturbations, the eigenvectors, the patterns of the perturbations, randomly from 1 day through 10-day differences in our coupled assimilation states. And so the spatial structures, he shows all of the math in the technical memorandum, but the idea is that this is a decent approximation of had we done the singular value decomposition and looked for the modes that are growing the fastest. These would be the modes that you would find and that you want to perturb. And so to show you what some of these modes look like, we did some of the EOF decompositions, and these are the ocean temperature perturbations that we're looking at here. 1 day, we're looking at structures, this is across the Pacific, we're looking at structures that roughly resemble the thermocline and the perturbations that you would get around the thermocline. 10-day perturbations, we're talking about things that sort of intuitively start to look like internal waves. On the atmosphere side, if we take a look at what some of these perturbation modes look like, we're talking about planetary waves, we're talking about Mount-Julian oscillation, structures that look like that. The synoptic ones on the bottom look like patterns of baroclinic waves as they move through. And so the idea is that by varying the separation time between the analysis states that we use for these patterns, we can generate a huge array of these modes that we want to be tickling, because those are the modes that we need to perturb properly. The scaling is described in that technical memorandum as well, and how these different states are how we do the scaling to make sure the perturbations aren't too big. I think the scaling is based on 10% of the variance. I don't remember quite the details, but the key of it is these perturbing the proper modes and the proper patterns. And so I don't have the plot to show you, the revised plot on the upper right. We've just really finished the retrospective forecast and we're putting this together now, but we have indications that we have reduced the ensemble spread near the end of the lead times in the forecasts. So now some discussion about the ensemble size. The motivation was clear. Our version 2 was running 10 ensemble members, and that's just too small. If you look at the plot from the Scape and Smith paper on the left here, the number of ensemble members on the x-axis and the mean 1 month lead NAO skill basically climbs with ensemble size. We were sitting here at the 10 ensemble members at this 40-45 skill number, 0.4, 0.45 correlation skill. And our idea was we wanted to climb up that curve a bit. What we also found, though, was from our own analysis, I apologize, is that if we take a look at the plots on the right, again, function of ensemble size, this time the vertical axis is RMS error. So the smaller numbers are the ones that we want to pay attention to. That's the better forecast. And we found that in general, beyond 10 ensemble members or so, for ENSO, for instance, here at 4-month lead, but we looked at longer leads as well, the RMS error for ENSO is just not changing with ensemble size beyond a certain number of ensembles, some small number, 10 or so. I understand that very rarely we did see that more ensemble members helped us, but in general, our takeaway from the analysis that we did was that we need the large number of ensemble members for short lead times, where you're looking at mid-latitude teleconnection patterns and things like that. Beyond that, when there's really not much predictability left, the longer leads, the prediction skill that we're looking for is in the tropics largely, and so we can reduce the ensemble size later. We fully understand that there is some predictability here that we are leaving on the table at some of these longer leads. But this was the choice that we made. And the idea of doing this is that we do a k-means clustering to get a subsampling. So we run the first 3 months in the depiction here in this cartoon on the left. We're going to run as many ensemble members as we can in a month. And for us, this was 40. That's as many as we could afford. And so the idea is that we run those out for the first 3 months. At 3 months, we do the stratification, k-means clustering, and we're basically allocating within each cluster and subsampling out of there, picking what we call the winners, and then proceeding for the rest of the forecast with that smaller number. Some results from the clustering that we did, if you take a look on the left, we did some experiments where we ran all 40 out for the full length, and then we looked at what that gave us in terms of spread relative to the clustering. And so the idea is that on the left in this example, we established the 4 clusters. The coloring is just a color that we assign to each cluster. There's no significance whatever with the coloring. And then each cluster had a certain number of ensemble members, and we representatively choose clusters out of that. And on the bottom, we have the subsampled clusters and the means. And the idea is that in cases, if you look in the middle, we have a case of we have a big spread and a case where we have a small spread. And the subsampled cluster of 10 in our case is well representing the spread of the 40 in terms of the Nino 4 metric that we're using to do this, with, again, the idea that we are looking to pick up the longer lead predictability from mostly from the tropics. And so the idea is that we're happy with the way that we're doing this clustering. It's reflecting the spread well. And so in the end, our suite, the forecasts run out to 9 months. We initialize every 5 days. That has to do with our coupled assimilation. We run 40 members in a lag burst sequence. Every 5 days, we initialize another 5 or 10, and then we select, based on the k-means clustering, 10 members for the remaining 6 months. These are all initialized from our weekly coupled assimilation system that we run. So this is just one piece of the result that we're looking at here. 1 month lead on this is for the NAO, and this is for the NAO for a full year. If the numbers are higher, if we just look at the boreal winter NAO skill. On the left, the 2 plots are the time series and the correlation numbers for version 3, lead month 1 and lead month 2. On the right are the old system with the smaller ensemble size. So we're seeing the correlation that used to be about 0.45, 0.46, 0.47 here for this sample size, and we've jumped up to 0.6. And if you look at the Scaife-Smith curve, we climbed right up that curve to what we would expect to find at about 40 ensemble members. The numbers for DJF only are 0.66, which for us is quite a respectable NAO skill. The other plot that I just am showing here is the ENSO teleconnection. We're expecting this to be about the same, and it is. Again, on the left is version 2, on the right version 3. I apologize, but this title says a 40-member average. This is not 40. This is our 10-member ensemble on the right for version 2, 40 on the left. But basically, we've done no harm with the ENSO teleconnections, so we're happy with that. We've looked at some of the other modes, and the ones that you would expect are increasing in skill, and a lot of them stay neutral. So just a quick summary of what I talked about here. The ensemble perturbation strategy approximates perturbations of the most important and unstable structures, and the confidence has improved with this strategy. And the ensemble size has expanded to 40 for the first 3 months and then drops down to 10. And we've got some of the AO and some of the other modes that we've looked at as well that you would expect, the mid-latitude teleconnection modes. They've all jumped up in skill, in part probably due to improvements in the model, but this ensemble size has helped us a lot. And there's the citation for the tech memo. Thank you very much for your attention.
Are you making these available?
So we're working out now how to make the suite of hindcasts available to the public. Right now, what we're doing is if people need particular fields from particular selections of them, we're putting them on the small public-facing disk space that we have, asking them to download it, and we're trying to work out, this is a lot of data, and we're trying to work out how to make it publicly available. I consider that a very important next step to do with all of this, is to make these data accessible to anybody that wants to look at them.
Would be great. Thank you so much. Judith here. I have a question. So on the NWP timescales, we can get, what we want is that the spread is representative as the error. So we get the state dependence in the spread, which we can use as an uncertainty measure. Do you know, on a subseasonal timescale, it's not clear if this still survives, or if the averaging that happens is basically getting rid of all of the state dependence of the spread, and we might as well sort of assume a Gaussian kernel around a forecast. Do you know, for the indices you're looking at on the seasonal time scale, if there is sort of that state dependent spread? Is it that if initialized in certain ENSO states, the spread is systematically different than in, let's say, a non-ENSO state?
We've looked at that not for the NAO index or for any of the indices, but we've looked at that specifically for subseasonal week 3-4 2-meter temperature scale. And it seems quite clear that it is state dependent.
Oh, thank you. I'll follow up.
Okay.
All right, I don't see any other questions. But Isla has one other question.
Well, okay, did I understand correctly that you then don't have a signal to noise paradox in the NAO if you're just going up that theoretical curve?
All the models are still too, the variability is still too big, so we're still too noisy. So yeah, we came up the prediction skill curve, but we haven't looked at whether there's the signal to noise paradox that plot is from, that paper. But our model is too noisy the way that all the models are. So we probably do.
All right, thanks, Andrea. We'll move to the next speaker. It's an in-person talk by Isaac Davis. Test.
Is working. Put in this morning. It's Isaac Davis. it's this, the tab. Yeah. Cool. Thank you. So there's a talk entitled, "Do AI models produce better atmospheric river forecasts than physics-based models? Quantitative evaluation." Work done by me in collaboration with Anish Subramanian and Tim Higgins at CU Boulder, as well as Luca Del Menake and Agnev Sengupta at CW3E, the Center for Western Water and Weather Extremes at Scripps. So as some project background, machine learning numerical weather prediction models have been popping up and demonstrating remarkable accuracy and efficiency compared to physics-based methods. They beat the ECMWF system in root mean square error for most variables on most pressure levels, with orders of magnitude less compute. However, no comprehensive study has yet been done investigating their ability to forecast atmospheric rivers. And it's crucial to understand this as they become more and more commonplace in our forecasting toolbox. So the models and the methods. So the top 5 models here, GraphCast, ForecastNet, ForecastNet V2, Aurora, and Pangu Weather are all data-driven models. They're all AI models. Then the bottom model, HRES or HiRES, is a conventional physics-based numerical weather prediction model from the ECMWF that's very high performing. Now I want to draw your attention to the resolution column here. And you can see that these top 5 models, the data-driven models, all operate on a 1/4 degree grid. They, for the most part, only have 13 pressure levels, with the exception of GraphCast that has 37. And in comparison to HiRES, the physics-based model, it has 0.1 degree resolution, 137 pressure levels. They all output 6-hourly data, but the internal physics time step of HiRES is much smaller than this. I also want to draw your attention to the output variable numbers. HiRES outputs hundreds of variables, and these machine learning models only output a couple, 9 to 14. Oh, that got a little messed up. Well, anyways, so the methods, I create 10-day forecasts initialized at 0 UTC each day from November 1st, 2023 to March 31st, 2024. This is the wintertime cool season on the US West Coast where this study is focused, and this is when atmospheric rivers are most prevalent there. So this creates 152 10-day forecasts per machine learning model and for HiRES. So this is 7,500 days of forecasts that I ran for this project, which is only possible because these data-driven models are so fast. Then I compare this forecast scale of these different models on the US West Coast across a variety of metrics. I use ERA5 as my ground truth. My US West Coast bounding box is from 15 to 65 degrees in lat and 170 to 250 degrees long. I detect atmospheric rivers with the CG climate algorithm, and then I attribute atmospheric rivers in forecast to reanalysis using the at-risk algorithm at 1,000 kilometer threshold. And I'll talk a little bit more about this algorithm later. So results. So I wanted to start off with a case study here on February 3rd, 2024. 2 ARs made landfall on the US West Coast on this day, and they brought almost or over 7 inches of rain to LA in under 2 days. So this caused a lot of flooding, landslides, and states of emergency in many of the surrounding communities. On the bottom left is the ERA5 reanalysis from February 2nd, just before these atmospheric rivers made landfall. The shading is showing the integrated water vapor. So that's the total amount of water vapor in a column from the surface of the earth to the top of the atmosphere. And it can be measured in kilograms per meter squared or millimeters, they're equivalent. The outline in the red dashes is the atmospheric river outline. It's detected by CG climate. The contours are mean sea level pressure, and the vectors are the 850 millibar winds. On the right, we have difference plots of 4-day lead time forecasts from each of the models, minus the ERA5 reanalysis at that time. So now the shading is showing the difference in integrated water vapor between the forecast and ERA5. Vectors showing difference in 850 millibar winds, et cetera. And you'll notice these are pretty similar. The AI models perform pretty well compared to HiRES. I think some of them outperform HiRES in this case study, namely GraphCast, Aurora, and Pangu Weather seem to have lower integrated water vapor errors. And equivalent or slightly smaller wind and mean sea level pressure errors. Here, ForecastNet v2 and ForecastNet might have slightly worse forecasts, but these all look physical. They all look enough like ERA 5. So now I'm going to take a look at some more compound metrics aggregated over the entire study period. So now we're looking at root mean square error versus lead time for a couple of atmospheric river related variables. Here, the dashed white line is HiRes, the physics-based model. And one of the immediate things that sticks out is HiRes is beaten by most of the machine learning models here. They mostly have lower root mean square error for these forecast metrics. This is with exception to ForecastNet, which tends to perform worse. But for the most part, at all lead times, HiRes is outperformed by these models. And here, GraphCast and Aurora in the yellow are our top performers, with Aurora being the very top. Now, a quick look at integrated water vapor bias over the study period. So the first thing that jumps out is that GraphCast has a pretty significant negative bias of about 1 kilogram per meter squared integrated water vapor. Also, most of these models, including the physics-based one, tend to lose moisture with lead time. But other than that, the biases in the AI models and the physics-based models are of similar orders of magnitude, excluding GraphCast. So now I want to talk a little bit about the atmospheric river skill algorithm, or at risk, which is what I use to attribute a forecast AR to one in reanalysis. Basically, I just take the outline of the AR as predicted by my AR detection algorithm. I calculate the integrated water vapor weighted center of it. And then if that center in a forecast AR is within 1,000 kilometers of an AR in ERA 5, then I'll consider that a hit. If it's not within 1,000 kilometers, then it's a miss. So now that I can attribute ARs and forecasts and reanalysis, I can make a plot like this that shows the distribution of the errors in meridional landfall location of the ARs at various lead times. It's important to look at this metric because on the US West Coast, the way the water basins are oriented, just a small error in meridional landfall location can drastically change where most of the water from an AR ends up going. And water managers need to know where it's going to make landfall so they can make the proper decisions. So starting out with the plot on the left showing days 1 through 4, we see that HiRes on the white performs very similar to all the AI models. They're all basically indistinguishable at this lead time. They're all performing well. At days 4 through 7, some more differences are apparent. GraphCast picks up a southern bias. Some of the AI models move up and down slightly, but it's very slight and probably not that statistically significant here. So other than GraphCast, the AI models are performing similarly at this lead time. Moving on to day 7 through 10, GraphCast continues its southern bias, and the other models remain fairly close to HiRes. So the takeaway here is that the AI models tend to do almost as well or as well as HRES. Now I'm going to take a look at a couple other metrics often used for ARs and for forecasting. One of these is Critical Success Index, or CSI. This measures the proportion of correctly predicted events out of the total actual and predicted events. It's kind of like accuracy, but you're not giving credit for a true negative prediction. It's like if there's no AR and we predict that there's no AR, that gives us no credit. Next, probability of detection, or POD, indicates how often an atmospheric river event is correctly forecasted when it occurs. So if there's an atmospheric river that we see, what's the probability that we forecasted it? Then false alarm ratio, or FAR, shows the proportion of predicted events that did not occur. So the top two indexes, CSI and POD, closer to 1 is better, and then false alarm ratio closer to 0 is better. So now taking a look at the top plot that shows critical success index, we see HiRes in the dashed white line again is the top performer, especially at shorter lead times. After around day 5, Pangu weather becomes fairly competitive with it, and the other AI models are close behind. This is with the exception of Aurora, which lags behind in this index. We see something very similar for probability of detection, or POD, in the middle graph, where HiRes is ahead at shorter lead times. The AI models aren't far behind. And then after around 5 days, Pangu weather becomes most competitive. ForecastNets and GraphCast aren't far behind, and Aurora lags behind the rest. Another, again, a similar story for the bottom graph with false alarm ratio, where high res is best at the shorter lead times. Pangu weather is more competitive, but here they're all a little more squished together. The differences aren't as clear. But again, Aurora is the worst performer, especially at these longer lead times. And this is particularly notable because Aurora was our highest performer when it came to root mean square error performance. So something about that is not translating into these metrics where you need to actually detect an atmospheric river. This pure root mean square error performance isn't everything here. So in summary, these machine learning techniques show a significant improvement over the physics-based method in reducing root mean square error of forecasting AR variables, and Aurora and GraphCast were the top performers. Most of these machine learning models showed competitive performance to high res when it came to predicting meridional landfall locations. But with the critical success index, probability of detection, false alarm ratio, the AI models kind of fell behind and the physics-based model had an advantage. And notably, Aurora, with the best root mean square error performance, did not do very well here. So in conclusion, despite this decreased average root mean square error, the physics-based model is still the better option for forecasting atmospheric river events. However, these AI models are not that far behind. So what might explain this difference? Why might these models be worse? Well, it could be the lower resolution. High res is 0.1 by 0.1 degree versus quarter degree, and it has 137 levels versus 13 or 37 in the AI models. And the pressure levels is really important when it comes to calculating integrated water vapor. The more pressure levels you have, the more accurately you can do this and less assumptions you need to make. AI models also have a known issue of producing smoother forecasts, especially at longer lead times. It'll smooth out the forecast fields because it reduces root mean square error. And this could affect the atmospheric river detection. Then also, atmospheric rivers are somewhat extreme events. So maybe these AI models haven't seen enough atmospheric rivers on the US West Coast in their training data to really nail them down, which also could explain why they do better in the longer term averages. So as final thoughts, root mean square error is not everything, and it's what a lot of these models are trained on. These AI numerical weather prediction models are not ready to replace the tried and true physics-based systems, even if they outperform in root mean square error. Additionally, they still don't produce the full suite of variables that HRES does. But these are still first generation systems for the most part, except for ForecastNet v2, which is second generation. But they will improve in the future. So there's a promising future for this. And these AI models still prove useful where computation power is a significant bottleneck. These are very cheap to run. It takes about 5 minutes on a modern GPU to produce a 10-day, 6-hourly forecast at quarter degree. So there is a place for these models. So that's all I have. Thank you.
Nice talk. I think it's really interesting how you were able to run all these AI models, and I'd be curious to hear more about how that process went. Like, were there challenges in accessing the weights and the code, or was it easier than you thought it, would be?
Yeah, so all of these models are just published freely on GitHub. The weights are free. They do all have instructions to go with them for you to start running them. They don't work the best in my experience, and you need to do some troubleshooting. But if you're interested in running them on Casper or anything or Derecho, I have it working. So
That's great. So you're running on Casper and Derecho GPUs? That's great.
yeah, it's totally possible.
Nice quote, thanks. Did you look at the rainfall associated with the AOs?
Yeah, well, no,
Okay.
because only one of these models actually outputs precipitation. The rest don't even predict it. Only GraphCast does. And I haven't looked into it myself, but I've been told that its precipitation predictions are not that good. So it's based off of ERA5.
I'm totally ignorant about how, very nice talk, by the way. Totally ignorant about how these different models are trained or tuned. Do you know if they were trained to capture AR, like were they going after ARs or were they trained for something else and AR is like a fun side benefit?
Yeah, so they're just trained for general weather prediction. They're trained off of ERA5 to predict 6 hours ahead, basically. So there's no tuning for ARs or anything like that. It's just tuned on root mean square error, essentially.
do you anticipate that if they were trained specifically for AR detection and forecasting, that they could, improve significantly?
I mean, I would guess, yeah, I think it'd be really interesting to fine tune one of these models with a bunch of AR examples and see how it changes the forecast skill.
I think Andrea had a question as well.
Go ahead, Andrea.
Yeah, so the work that you cited, DeFlorio and others, those guys are running the multi-model ensemble AR prediction and using that as to advise the water managers, obviously, as part of this project. Just wondering if you looked at some comparisons of performance, skill, instead of just using one model, using like their multi-model ensemble, for instance, for some of the events that they've been predicting.
No, I haven't done that, but it would be really interesting. It would be cool to get some of that data.
Based on the fact that since RMSE is not everything, I was wondering if you had thought about a better error metric that you think we should be minimizing instead.
Yeah, I don't know for that one.
It's a really hard question. I was just
that's a
curious
good question.
if you've had thoughts.
I'm going to think about it more. Thank you.
Sharon?
Yeah, thanks. Very nice talk. I'm wondering if there's a chance, I know the weights are public, but is there a chance that the testing period was used to train these models or to train these weights? Or, yeah, I don't know. How good is the documentation in terms of that?
Yeah, really good question. The dates that I tested on were outside of the training period for the models. They weren't used as a validation data set. They were used for casual inference, or forget the exact terminology.
Okay, thank you.
Oh, I have a question. Sorry if I missed this, but you're looking at the winter of 23-24, right? A 3-month stretch or something like that. Yeah. How many ARs were there? And does that, give you robust statistics in your skill metrics?
Yeah, so there are a lot of ARs in the domain. There are fewer that actually make landfall on the US West Coast. I think a majority of the days actually have an AR somewhere that's crossing into the domain. Not too many make landfall, but those are all multiplied by 10, I guess, kind of by because you're forecasting them at different lead times. But yeah, it could be nice to add another season to this. Good question.
Christine.
Yeah, that was a really, really nice talk. I'm wondering if some of the failures were dominant for a specific flavor of an AR. I know you probably haven't looked at that yet, but it might be worth digging into a little.
Yeah, that could be really interesting to look into and see exactly why Aurora is failing. There is a certain kind of AR associated. It's a good idea. Thanks.
All right, thanks a lot, Isaac. Thank you. Dark. Yeah, could be. Now we're going to transition into the general discussion, and I didn't prepare any remarks beyond the working group update that I gave yesterday. So this really is just an open forum to ask questions, give us feedback, how the working group is going, what you'd like to see. And if we don't get any discussion, I can try to spur some on. But I'm gonna start just looking for hands and hear one. Yeah. Oh, Andrea.
Yeah, so this is a question that I briefly raised and mentioned that I just sort of want to put out to the organizers of this working group, the leads of the working group, and to the community, whether this is a reasonable forum for the system developers to be giving each other updated information about sort of the latest and the greatest aspects of the system so that we can learn not only what each other does, shared output data, but also sort of have a better sense of where others are going and advancing. I don't know if we have a really good forum in the US to share this kind of information. And I'm wondering if you view this working group as potentially a forum for that. So it's a question more than a proposal.
Yeah, I can say we're definitely welcome to presentations like yours that inform us about how different prediction systems are being developed at different organizations, right? It's obviously a CESM working group, but we definitely learn from each other. So talks like yours are helpful to have, keeping in mind that most of the working group members are going to be mainly focused on CESM.
Okay, thanks.
Dylan.
I guess in the interest of kicking off discussion. I mean, I know you and I had been discussing kind of offline any plans or priorities in more high resolution forecasting space or predictability space. And I'm just wondering what the general vibes are among the working group as to whether that should be a priority. I thought Yaga made a lot of good points yesterday, and I guess I can just echo them from Noah's perspective that there are a lot of stakeholders who would really like more regional scale predictions, whether we can get the accuracy associated with those local scale physics is like an entirely different question, but whether we should be trying and allocating resources in that space is kind of the question that I'm posing to the group. There's a variety of ways that can make that a little bit more tractable computationally using statistical methods, but it's just a matter of whether it wants to be a priority for the group as a whole. So that the prompt for the group is, should we be focusing on more high resolution predictability problems with computational resources that are available?
So I'll start off responding to that and open it up. So we did just go through the exercise of renewing the CSM CSL allocation in the fall. So we had to submit a working group proposal that was successful, and we got about 46 million core hours for the next year and a half, I think is the cycle now. About half of that we put under sort of development activities, much of which will be focused on building off of the CESM2 systems that I introduced yesterday, in particular CSM2, S2S, land atmosphere coupling, MEGS work. So that will be supported under the EFPWG allocation. But then we also put in work to better understand drift and methods for deep drifting. And I touched on that yesterday too. And we think we've made progress there that is really pretty exciting, specifically to address this resolution issue, right? We can't afford the full hindcast sets with global high res or even regionally refined high res, but we can afford case studies. And I think that's going to be where we should put our eggs in the next year, is maybe using regionally refined CESM2 to do particular case studies of events, and maybe have techniques to do that in a way that we can remove any spurious drift. A lot of our production allocation is sort of dedicated towards the second year, when we're intending to be able to contribute to initialized hindcast with CSM3. And really that such an expensive model that is going to take up most of our allocation. And that's not even touching decadal timescale reforecast. It's really focused on S2S, maybe a SMILE type CSM3 in year 2, but we can't even afford to finish SMILE CSM3. So that's my answer, and then see if anyone else has comments.
I don't know, maybe Rich knows more about this, but I feel like there's desire on the atmospheric side to have cheaper physics that could be used for high resolution. And so maybe if discussions are happening around that, it would be important to kind of get the ESPWG voice in as to what would be desirable if there was any kind of cheaper physics for high resolution.
Do you mean global quarter degree?
Well, yeah, quarter degree, I guess, to start with. I don't know, Rich, do you want to chime in about any discussions that have happened along those lines?
Yeah, I mean, we talked about Camp 4 physics, but we also, after the visit from the Met Office, we talked about kind of simplifying the boundary layer and shallow convection with the Met Office's the lock scheme. But basically, it's much quicker, and we think it might be, one option of many of providing a model that isn't just CSM2 at high resolution, which would be really expensive.
CSM3.
Sorry, yeah, CSM3, sorry.
I would assume that along those lines, we'd be taking the steps that Dave was discussing yesterday toward the machine learning enabled CSM3. We could, if we had machine learned versions of our parameterizations to plug into a hybrid system, it would potentially be much cheaper to run.
Yeah, but that, I mean, in Dave's timeline, that was what?
Yeah, it's beyond your allocation, I guess.
Right, I think that's maybe something we'll put into a subsequent CSL proposal. And then there's the question of vertical resolution too. Most of the CSM3 experiments that we put in the proposal are going to be the low top version of the atmosphere with only limited tests of higher top. Is that the right strategy? I guess we don't know yet which is the better model. Do we?
No. Well, I feel like the high top's gonna be better in terms of for seasonal. Well, we have these project with scripts with CSM2 where there's really very little impact of having a high vertical resolution. But I don't know. I feel like for things like the Southern Hemisphere, that might be improved in CSM3 with the new improved vortex because of the mountain moving mountains and things like that. Yeah.
Jaron?
Yeah, I was thinking a little bit about the last presentation and like the potential of machine learning and what has been evaluated and what needs to be evaluated and how easy it is to it. I don't know if maybe Isaac has some idea. I mean, he ran the machine learning models out to 10 days, but I wonder how feasible it is right now to go beyond that, to go maybe to the 2 weeks to 2 months lead times, and if there is work in that regard, and how comparable are the results that we can get from there to the physics-based models. I know pushy SOS exists, and they claim to beat the IFS ensemble. But yeah, I don't know if people have more knowledge about this or ideas what needs to be done or what needs to be evaluated.
responses to that. So I see Jeff and Kevin are in the room, and might be good to get some kind of update on plans for DART reanalyses that may be relevant to the working group.
Yeah, so I'll address that. We have the capabilities to do weekly coupled reanalyses for almost any of your components, caveat land ice at this point. We have no resources at all and really no mechanism to get resource being within Sizzle. So the two showstoppers there are a scientific desire on your part, which we are open to, and computational resources, which I think you realize are non-trivial for this, which would again have to come from another place for us. As far as scientific collaboration, we're ready to go whenever, and we're also certainly happy to collaborate on those ensemble results and other things you already have. But I think the important point is we can't lead that effort. I think you may be aware that Sizzle in particular is under some pretty tight constraints since we manage the machine in our capability to actually get and lead resources on the NCAR machines ourselves. So those types of activities would have to come either from within CESM or potentially from within NCAR as a whole as we move into the new strategic plan, where I think a lot of your goals are completely central to the new strategic plan. So I guess my feeling would be we should be working coherently together to address maybe getting some of those resources from NCAR.
Yeah, I spoke to Dan Amron yesterday, and he said something similar. You're kind of in wait mode to see where this strategic plan is going to deliver in terms of to affect these things.
And one follow-on comment. So that was the step where we know everything. We're very interested in still in strongly coupled data assimilation, and we are we know how to do the infrastructure for that and everything. We have many demands on our time, and so when we see that someone's actually ready to provide resources and to collaborate on that, we can do it. But again, we're not going to do it just for recreational purposes. We want to work with people, and we don't do science, Earth system science per se. We do data assimilation science, and we rely completely on Earth system scientists like those in the room to do projects like that. We are ready to do it when people are ready to work with us on it.
Another comment about resources. Mohawk Gramti has developed an algorithm that may help us to reduce the computer time required by up to 3/4. So that would be a huge savings and may make assimilation or generation of visual conditions much more achievable. So we still need to look into how feasible that is, but the initial results are really promising.
What's the innovation?
It's a hybrid assimilation mode where the covariance is a combination of climatological and something that's derived from the ensemble. And so you can actually run with a much smaller ensemble size, typically like 1/4 of the normal 80 members that we've been doing.
We had some discussion with Brett Raska about the land EA effort. And we heard a lot about how atmospheric coupling is potentially an obstacle in our S2S systems. Do you have any update on where Brett's work stands, or like what the time window is of his assimilation product?
Sure. So again, Brett is actively working on a number of aspects of land surface data assimilation in CTSM and in particular in CLM. Of course, you know the challenges with getting impacts out of those things, but exploration is needed there. I think Dan is probably planning on reporting on that in either the winter meeting of the land surface, which I guess is still to come, or in the summer one. Again, the situation is pretty much the same. Is from a tools and support thing, we have systems that are ready to go, and it's really a question of the resources and the science. So the land stuff is on its own significantly cheaper, and so it is conceivable that with less resources than say atmosphere or ocean, we could do a longer period reanalysis stuff. if there was a scientific driver for doing that with just the land components.
I think there is, or it would be more well-founded than our current technique for initializing the land, which is just reanalysis for CTSM.
And I think a scientific discussion that needs to go on there is, of course, CLM is a incomprehensibly complicated model compared to the states that we have for the atmosphere of the ocean, which, you have Navier-Stokes underline it. And so there is a need to discuss exactly which parts of the land system you think are important to initialize. And so there are separate research that's going on sort of longer timescale, biosphere type stuff, soil moisture and other things. We have collaborations that are already underway. Another quick note on the side is that DOE is suddenly expressing much more interest in data assimilation aspects of this. So we have currently funded collaborations with E3SM model, so ELM and the atmospheric component there that are looking at data assimilation with their systems. ELM is so similar still to CLM in many facets that I think there is room to consider again how we connect those pieces of research between what the DOE folks are doing and what we're doing here.
Thanks. Any other comments online or in the room? Judith.
Yeah. Yeah, thank you so much. I think there's still a lot of open questions about the predictability of the different components and also the impact on initialization across the different lead times. So I think it would be great to do more in the perfect model world where I see NCAR as contributing science, not forecasts too. And maybe have discussions what we can do either with existing runs or new runs to look at the predictability and predictability of the different components and impact of initializing the different components. What do we need and on which time scale? Well, I'll see experiments, something like that, where we get rid of the ops. Sorry, ops are important, but we just work in a perfect model scenario, so we don't need to worry about discrepancies between in situ observations and credit forecasts.
And if I can just jump back in, so exactly what the emphasis of the P and SPAT is going to be seems like an open question to me. So how much it's prediction and how much it's predictability really going forward is open. So ensemble data simulations like we provide are the tool of choice for OSCEs, as Judith is describing, and for understanding these things. And in fact, I think our scientific expertise within the DARES team itself is stronger on that sort of predictability and other things. And so again, these things can be done. The cost is not necessarily that much cheaper, but the ability to generalize from one set of experiments to another, I think, is often easier. And so again, we are anxious to support, even more anxious, I think, to support that type of research than we are pure prediction research, and the tools exist. Again, it's a question of where the research is going to come from and what the focus is going to be. So we can do it. People just have to want to do it.
All right, well, we've come up on time for the break. We're going to take a half-hour break and come back for the climate variability and change session. So please join us. Thanks. Yeah. They would respond physically. They
is Italian.
Okay, thanks. Okay, thanks, Anshi, for the introduction. And my name is Yichao Liang from National Taiwan University. So today I want to share this ongoing project, and we discussed this with Ayla and Clara and Nan for a while. And we try to conduct large ensemble simulation with single anthropogenic greenhouse gases and aerosols. And I also want to thank some collaborators and also some of my Taiwanese colleagues to help me conduct these simulations. Okay, so this is the extension simulation set. Follow IDA's CSN2 single forcing large ensemble project, and in that you guys have the greenhouse gas, anthropogenic aerosol, and the biomass burning, and everything else. So in this simulation, we want to further focus on the greenhouse gas and the anthropogenic aerosol, and we try to separate even more the single forcing for these two anthropogenic forces. And we use the only method to quantify the impact of single forcing following the DMIP. So before that, just quickly go to look at the effective radiative forcing from CME6. So we can see each greenhouse gases like CO2 or the methane or the N2O or ozone or black carbon aerosol. Each of them has the different effective radiative forcing. So combine that, we can see their total net effect, but it will be also interesting to separate it. And this is more quantification for this effective radiative forcing for these climate forces. So we are more, as mentioned, we are more focused on the greenhouse gases and the aerosol. And for the aerosol part, we mainly focus on the sulfate aerosol and the black carbon. And for the greenhouse gases, we'll separate the total greenhouse gas into carbon dioxide, CO2, methane, and the CFC and the N2O. So from the forcing perspective, so here's the 5 forcing from Ella's paper. So we want to run single forcing with the CO2 forcing only simulation, methane only, and the N2O. And for the CFC runs, we combine this F11 and the F12, combine them together, and we call this CFC simulation. And for the aerosol part, now we only focus on the black carbon and also the SO4 plus SO2, and we call this the total sulfate simulation. So now we completed 10 ensemble members for this single forcing. And for the greenhouse gas single forcing for CO2, methane, N2, and the CFC, we run the simulation using CSN2 from 1850 to 2050. And for the aerosol single forcing one, we run the carbon only simulation and also the sulfate only simulation from 1850 to 2014. So these are all completed, and they use some computational hours, but in Taiwan, but we finally managed to complete all these simulations. And we focus on in the following analysis, we focus on 1850 to 2014 period. And the change or the response is defined as the last 40-year mean minus the first 30-year means. And the anomaly is calculated as the difference with respect to the first 50-year mean values. So here, just give you an example. So there's an existing greenhouse gas run and anthropogenic aerosol runs. So this is how you guys produce the simulation, and you force all the aerosol or greenhouse gases combined to produce the large ensemble. And the black line is the greenhouse gas runs, and the blue line is the anthropogenic aerosol runs. And we run another 6 set of simulations, and we can put the result here. And this is for the global surface air temperature on the top and Arctic surface air temperature on the bottom. So play around with these simulations, we can try to test the linear additivity of the responses, right? So here I also show the solid dashed line as the sum for each single forcing for the greenhouse gas set of simulation. So the sum equal to the CO2 I mean, the response of CO2 only simulation plus the CFC1 and the methane one and the N2O ones. And we can see in these metrics, the sum is very close to the greenhouse gas runs. So they are pretty much linear additive. But we are going to show there's nonlinear response show up, especially in the spatial distribution later. Okay. And so the scientific questions we could ask is like, for example, for the greenhouse gas set of simulation, we could try to study the nonlinearity if there's any. And we can further look at this mechanism or what is the process producing this nonlinearity. And for the greenhouse gas single pulsing runs, in particularly for the black carbon runs, I guess it's very interesting to further know that what is the role of black carbon in affecting global and regional climate. Okay. So I'll skip this. So now looking into the spatial patterns, so I will show each of the single pulsing runs in this order. So greenhouse gas on the top left and the follow on. And also, in particular, I want to focus on the sun minus the greenhouse gas run because this reflect or reveal the nonlinearity. Okay. So this is the surface air temperature. So if we look at the sun minus the greenhouse gas runs, we can see some positive surface air temperature response in the North Atlantic and some cooling effect in the Northern Europe or Eastern Europe. So this nonlinearity, the magnitude is actually comparable to the response in weaker forcing, for example, CFC and the CH4. So this nonlinearity indeed happens, but we couldn't see this nonlinearity evidently in the regional or global average as we see in the time series, because that for this case, for example, because it's positive value kind of can cancel out the negative value. But if we expand the spatial domain, we do see this nonlinearity, a signal or response shows up. And on the other hand, on the other side, the black carbon on top right panels, we show this overall warming in the Arctic, but the spatial pattern is somewhat different from the greenhouse gas. Okay, so the next example I want to show is the sea ice area. So again, the time series of the Arctic sea ice on the top and the Antarctic sea ice in the below, they are pretty much linear additive if you just look at the time series. But if we zoom in to look at the spatial patterns, it shows some very interesting features. From the top, the Arctic sea ice, we can see there's a negative sea ice reduction signal in the sea ice age in the Arctic, but in the interior Arctic, we see more sea ice increase. So the sun minus greenhouse gas run gives this spatial non-uniform distribution of the sea ice. And the similar sea ice increase and the decrease also happens in the Antarctic or in the southern hemisphere. So you can see there's a red and blue colors in it. So again, if you take the Arctic or Antarctic average, so this signal becomes very weak and then the nonlinearity is kind of disappear. But this indeed happens if we look at the spatial pattern more carefully. And I guess this has some physical meaning behind it. I haven't done more careful analysis to understand why, but this nonlinearity spatial patterns, like less sea ice in the sea ice age and more sea ice in the interior of sea ice. I think there is some physical process over there to govern this. And also quickly look at the precipitation. Again, if you look at the global mean or tropical mean, this shows very close. The dash line, black dash line is very close to the black solid line, shows the largely linear additivity signal. But if we look at the spatial patterns of it, in particular in the tropical region, in the tropical Pacific warm pool region, there are less precipitation in sun than the greenhouse gas. So the nonlinearity of the precipitation indeed emerges in the tropics. And further research can look into why this happens. And the last example I want to show is the net primary productivity, the NPP, because we want to have some implication for the biogeochemistry community. So global average shows on top panels, we see the black dash and the black solid line are very close to each other. And also the CO2 can kind of explain all of these variations. And they are linear additive, and the CO2 contributed to the most. But the more regionally, if we zoom into the article, I'm not sure this makes sense, but if we zoom into some regions or smaller region, the CO2 still dominates, but not contribute entirely. But again, this largely show this linear additivity if we look at the time series. But if we look at the spatial patterns, so again, the some minus greenhouse gas around, we see some like positive values happening in the, for example, in the Alaska regions. And this indeed gives us that the nonlinearity indeed happens in certain regions. And this is, again, the magnitude is comparable to the response for weaker forcing like methane N2O or CFCs. And I'm not sure, so this is known for the community. So for the aerosol runs, you see the MPP, especially the sulfate run here. Okay, so you can see the overall reduction of MPP in the northern high latitude, but the overall increase of the MPP in the tropical regions. Yeah, I'm not sure community know this, but I feel this very interesting, and perhaps it's related to the cold temperature in the high latitude and more precipitation in the tropics, which may be looking more. And for the black carbon, we do see some increase of the MPP following a warmer climate. So just move to the discussion. So I think the nonlinearity indeed emerges if we focus on some special specific regions, so like the sea ice or tropical precipitation or regional MPP. But just to be aware, if we took area mean, we look at time series, this nonlinearity probably be offsetting and become less clear. Okay, so we may follow up to ask, what does this nonlinearity means for detection attribution analysis? Because I guess all of this detection and attribution analysis, they based on the linear additivity. So this set of simulation could provide some insight for the detection and the attribution analysis, especially we want to look at more on the spatial patterns. And also the role of black carbon, I found is very interesting. I think it's kind of relatively new. I mean, for the CSN2 simulation at least. So I guess the black carbon is interesting. It's a warming forcing agents, but it's not spatially uniform, unlike CO2 or these greenhouse gases. So the warming pattern they produce, we can already see in some of these spatial patterns. So it's very different from the greenhouse gas ones. So it's worth to looking more on this. And personally, I'm more interested in study the polar climate change by using this single forcing and the different and also attributed to different single forcings. But I guess this simulation, because it's covered the global and should have more implication for wider community or for other sectors among the CSN communities. So if you have interest in want to look at this simulation, I'm happy to share. So I talked to Ayla maybe last year. So eventually we will prepare a data server maybe in Taiwan, and we can share the data openly. But at this moment, if you have interest, I think you can contact me, and I can process the data and maybe transfer to Casper and for you if you have interest. Yeah. And finally, just want to quickly go through. So I also talked to Ayla and Clara a few whiles ago. So now we completed this set of simulation. So it's already cost me a lot of computational resources, but I probably still have some to conduct a couple, one or two experiments. So Clara actually mentioned it's also interesting to have one simulation with the anthropogenic aerosol and the greenhouse gas forcing together, so we can further test if this nonlinearity or linearity with the single greenhouse gas and the anthropogenic aerosol simulations. Okay, but other forcings like the tropospheric ozone or stratospheric ozone may be also useful. So this is something the community can discuss, and I just want to discuss with the community like which one or which set of simulations is the most useful for all of us. Okay, so I think I'll stop here. I'm happy to take any questions. Thank you.
What the nice set of simulation? Any question?
I guess I have two questions. One is, we had a talk from Mark England on Monday about methane MIP. I don't know if you're aware of that.
Yeah, I actually talked to Mark a couple of months ago. So I think what we see here was Mark's leading the methane MIP, right? So I actually showed the result to him. So here the methane is the magenta line. So it's very weak forcing and produce very small temperature response and other responses. So I discussed with Mark. So Mark think that maybe this set of simulation can be a baseline simulation for the mid and mid. And he also mentioned that because here I run Chem 6 without chemistry, so maybe this is another possible reason why the response is underestimated. In any case, I think here the set, especially the CH4 related only simulation, could provide a baseline or the reference simulation for methane MIP. Yeah.
And he's going to run, I guess, Wacom with chemistry, so maybe you can compare.
Right. That's a good idea. Yeah. But on the other hand, Mark mentioned to me that because of the chemistry components, it's too expensive. So maybe he can only produce like 3 or 5 members.
Okay, yeah.
He has 4 members. So that's useful.
And my other question, well, maybe it's more of a comment, but I feel like the sea ice thing is because it's bounded by 0. So if you, in each of the smaller warming experiments, you lose ice at the edges, but with all of them together, you get to 0 and then you can't lose any more ice.
Yeah.
And then this in the middle of the sea ice, I think it's hard to change the sea ice fraction. There's enough sea ice there that it's 1.
Right.
Do you think that's
what's
going
sea
on?
ice is an interesting component. So if we're close to 0 and 1, so it kind of bounded by these boundary values, right? So it cannot vary too much on there. So probably that's the key to generate this non-linearity. Yeah. But I'm wondering, I don't know. Yeah, it's good. It needs more analysis also, for example, the mean CI state for each single forcing. And I think with that analysis, you can show some clues. Thank you.
Any other question? Thank you. All right, let's move on to the next talk. Will be a remote given by Chengfei He. Hey, Chengfei, can you hear us? Okay.
Hi, could you see my screen?
Okay, go ahead.
All right, so
We're not sharing.
Oh, we're not
No, it's
sharing.
okay, it's okay. Maybe it's. Yeah,
Share? Okay. Yeah.
okay, screen?
it's good, yeah.
Okay, yeah. Hi, everyone. Thanks for having me today. So I'm Chengfei. Today, my talk is some recent findings about the role of external forcing in major climate modes, especially for the Atlantic multi-kilo variability. And this talk is mainly based on 2 papers with a lot of colleagues in the University of Miami when I was a postdoc there, and now I'm an assistant professor in the Northeastern University. And my conclusion is basically the title here. The recent Atlantic multi-kilo variability and other climate modes are dominated by external forcings. So the Atlantic multi-kilo variability is it is very important climate mode. It has widespread impacts like the Atlantic hurricanes as well as Sahel rainfall. Here we form it as Atlantic multi-kilo climate variability, the AMCV. And because the AMCV is so important, so there are a lot of studies trying to understand its formation mechanism. But it seems the cause is very controversial. Usually it falls into 2 categories. So first category think it is because of the internal variability, mainly from the AMOC. Also like the atmosphere could play some role there, like the North Atlantic Oscillation, the NAO. And the other category thinks that the AMCV is driven by external forcings. In particular, the anthropogenic aerosol emissions in the past century has more decadal variability, so the aerosol could affect the atmospheric radiation than for the sea surface temperature. I think right now the community already acknowledged the impact of the aerosols, but they don't consider it is as important as like the AMOC. So today my major question is what cause of the AMCV? So with this question in mind, I will try to combine both observation and model simulation to answer this question. I will analyze the hurricanes and the Sahel rainfall and AMV together. But I have to emphasize that previous studies usually focus on the whole past century for this AMV. But as we know, the anthropogenic forcings increased significantly after World War II. So this seems like this implicitly assume the external forcing is kind of relatively constant in the past century. So for current study, I mostly focus on the post-1950 era. And during this period, we have reliable observations for the hurricanes and also Sahel rainfall. And I will use historical simulations from 46 76 models. And in total, I have over 400 ensemble members. This large ensemble allows me to knock down the internal variability and to isolate the force response. And finally, I will use the single forcing runs from DAMIC to quantify the role of external forcings. The single forcing runs here include the greenhouse gas run and supergenic aerosol run, as well as like the natural forcing runs. So each single forcing run has like 70 to 100 ensemble members. And finally, I will use the same data and the method to check other major climate modes like the NAO and TVO. Okay, here is my results. From the top to the bottom are the time series of the AMV, Sahel rainfall, and vertical wind shear in the tropical Atlantic. The vertical wind shear is a proxy for the Atlantic hurricane activities. The red here is observation, and the blue is the ensemble mean of the 76 simulations. So it is a false response. And all time series here are detrended and normalized. I will not define why we detrended here. And this is another project, but I will show you that the unnormalized time series later. So first, let's just focus on what we have here. So we see the model AMV, Sahel rainfall, and vertical wind shear are highly correlated with observation. Their correlation is actually about 0.9. So if we regress the observation onto the forced model simulation, then at least 80% of the observed variance in this regression could be explained by the forced response, because the R-squared in this regression is basically the correlation, square of the correlation here. So this seems to suggest that the observation is mainly dominated by external forcing, but it is still too early to conclude here, because external forcing may be overlapped with internal variability. Then in next step, I will show the internal variability alone could not lead to the observed AMCV in the tropical Atlantic. So to check if the real world could arise due to the internal variability, time series doesn't help, because this is like trying to deduce someone's family based on their appearance. Similar looks doesn't necessarily indicate familial ties, and the difference doesn't preclude them. Instead, we have to check the DNA of that person. And likewise here, we have to check the DNA of the AMCV system. And one DNA marker here is the covariability in this AMCV. Basically, it is a correlation between AMV and Sahel rainfall, and the correlation between AMV and vertical wind shear. So it describes the coherence of the AMV and its tropical impacts. It is inherent to the system and independent of their trajectory in the past or the magnitude. If the real world could be generated by the internal variability, then they should share common DNA. So the red star here we see is the correlation for the observations. Both of them are around 0.85, and this is consistent with previous studies. And now what I show here is the correlation due to the model, the internal variability. I removed a false response from the ensemble members in the historical simulation, and then I carried the correlation the same way as in the observations. The color pixel here stands for the number of ensemble members have a certain correlation value. So if we add all these pixels together, then we get a total ensemble member. So here is 400. The result here is pretty clear. The observation is at the tail of this distribution. So that means none of the 400 ensemble members have a correlation value higher than the observation. That is to say, the internal variability share no common DNA with the real-world observation. And back to this model internal variability, we can see it has a large spread here. And this large spread is actually expected because we can think about in this way. Think about in a world with no evolving external forcing. The correlation between AMV and the precipitation or the vertical wind shear could be interrupted by a lot of other processes like the ENSO, like the PDO. So sometimes when all these processes are contributing in the same direction, it shows a high correlation here. But when they are competing with each other, then it will show a low correlation. So as a result, it shows a large spread. And overall, the average of this distribution is this green star here. We can see it is far away from observation. So from this point of view, we also see like the internal variability is very unlikely to produce a real-world AMCV. And we also perform this analysis in the PI control simulations. The result is very similar. So the first conclusion to summarize here is that the DNA shows the internal variability is very unlikely to expand this real world. And since I analyzed the covariance rate due to the internal variability, and it cannot explain the real world observation, what about the internal variability plus external forcing? Then I further calculated the covariance rate in the historical simulations. And this time, I didn't remove the false response from the ensemble members. So each ensemble member has both internal variability and external variability. So we see here, this distribution moves a little bit toward this observation, but again, observation still at the tail of this distribution. So this says the internal variability plus external forcing cannot expand the real world as well. And right now, I think we only have the last option. It is just the forced response. So the forced covariability rate is this blue star here. We can see it is close to this observation. So finally, after this DNA test, we are able to conclude that the real-world AMCV since 1950 can only be explained by the external forcings. If this test still cannot convince you, then I'm going to show another independent evidence that also supports the dominant role of external forcings. The other evidence is the AMV-induced atmospheric teleconnection. Here, the left column is from observation. The top panel shows the circulation and the geopotential height regress onto the AMV. And the bottom is the rainfall over the land regress onto the AMV. On the right panel here, it is a false response from Smith-6 simulations. So we can see they are actually pretty consistent. This consistency is not seen like in the internal variability driven AMOC. So I provide two references at the bottom so you can check there. So from this point of view, again, we see that the AMCV induced teleconnection is also forced. So this also suggests the AMCV in the since 1950 is driven by external forcings. And now I'm going to briefly introduce the mechanism of this system. The mechanism is pretty simple. It is just a gale-type response, like what I show here in the gale model. When we have the asymmetric heating across the equator in the tropical Atlantic, so for example, a heating in the tropical North Atlantic and a cooling in the tropical South Atlantic, the atmosphere will induce a baroclinic mode in the tropical North Atlantic. In the low level of the atmosphere, there would be a cyclone anomaly, and at the high level of the atmosphere, there will be anti-cyclone anomaly. And this baroclinic mode is pretty clear in the observation as well as in the forced model simulation. For example, in the low level of the atmosphere, the westerly anomaly will transport water vapor from the ocean to the North Africa, therefore lead to the rainfall here. And at the high level of the atmosphere, because of this anticyclone, the easterly anomaly prevails in the tropical Atlantic. And together with the westerly anomaly in the bottom of the atmosphere, they perturb the vertical wind shear, therefore affects the Atlantic hurricane formations. So based on this mechanism, we can see the AMV affects the Sahel rainfall and Atlantic hurricane through the sea surface temperature gradient in the tropics. This is basically the multi-decadal Atlantic meridional mode, the AMM. It is the sea surface temperature difference between the tropical North Atlantic and the tropical South Atlantic. And we will see this AMM is superior than the AMV for the physical mechanism. And in the next slide, I will show it is also more consistent when we do the attribution of the external forcings. So this is attribution the AMV to external forcings. I'll skip all the technical details how we quantify the role of single forcings. The result is here for AMM, Sahel rainfall and the Atlantic hurricanes we see. They're mostly driven by the anthropogenic aerosols and natural forcings. For natural forcing, it is mostly composed by the volcanic aerosols, and the greenhouse gas plays a minimal role for them. This is expected because the greenhouse gas usually induce uniform warming in the tropical Atlantic, so there won't be any meridional temperature gradient. As a result, they won't affect like the Sahel rainfall and Atlantic hurricane through this AMM. And finally, I also quantify the role of forcing to the AMV. And the interesting fact here is, in addition to this aerosol and natural forcing, the greenhouse gas here also have an important role. And this is not surprising as well, because when we define this AMV index, we use the linear detrending North Atlantic sea surface temperature. And this linear detrending usually cannot completely remove the impact of the greenhouse gases. So to summarize here, the AMCV is mostly driven by the anthropogenic and volcanic aerosols. And from this attribution perspective, the AMM is more consistent with the Sahel rainfall and the vertical wind shear or Atlantic hurricane activity than the AMV because of the geotype response. So far, I showed that AMCV is driven by external forcing and the physical mechanism is because of the geotype response. And at the beginning, I also showed that the normalized time series. And now in this slide, I'm going to compare the normalized and non-normalized time series. So first, on the left is the normalized and on the right is not normalized time series. For AMV, we can see they are more or less the same. Maybe in the non-normalized ones, the modeled force response is a little bit smaller than the observation. But when we take a look at the Sahel rainfall and the vertical wind shear, the force response is much, much smaller than the observation, even though these two time series are highly correlated. So because of this small amplitude, actually, we need hundreds of ensemble members to knock down the internal variability and to get the force response. And because this force response is muted, so that means the model is dominated by internal variability. This leads to the bigger question in our climate models. So why the signal to noise ratio is so low in our models? So in this slide, I will try to still use this distribution to show this signal to noise problem in our climate models. So the first distribution we see, it is because of the internal variability. And the bottom distribution is because of internal plus external variability. When we compare these two distributions, we will see the role of external forcings in the single ensemble members. But we can see when we have external forcing, so the distribution shift little bit toward this blue star because this blue star is a pure false response here. But still, the distribution at the top and the bottom, they are pretty similar. The distribution at the bottom, it has a large spread, and the average of this distribution, the green star here, is quite similar to the green star at the top. That means, so in the single ensemble model ensemble member, it is dominated by the internal variability because the force response is too small, like I showed in the last slide. The magnitude is too small, so it cannot affect the correlations between AMV and its impacts. That means our model has a very low signal-to-noise ratio. But like I showed before, the single real-world realization is dominated by external forcings because this red star is close to this blue star here. This suggests in the real world, the signal-to-noise ratio is pretty high. So why we have such a paradox here? I think that it is still an open question. And this signal-to-noise paradox is similar to that in the predictability community. So the signal here for us, it is a false response. In the predictability, so it is the ensemble mean of the initialization. And the noise here is the internal variability. The noise there is because of the ensemble spread. So why we have such a paradox here is still, I still don't understand there. So I think this is an open question for all of us. And finally, I would like to show the NAO and the PDO. We apply the same data and the same method to calculate the forced NAO and the PDO in the symmetric ensembles. And we can see here the force response is well correlated with the observation. So this again suggests that the NAO and the PDO are also influenced by external forcings. If you want to have interest for these two indexes, you can take a look at Jeremy's paper. At the bottom, I provide the reference here. So this is my take-home message. We see the recent tropical AMCV is mostly driven by the anthropogenic and volcanic aerosols. And we see for the AMM, actually, it's better to interpret the tropical impacts than the AMV because of the geotype response. And finally, I show the NAO and PDO are also influenced by external forcings. And we have several open questions here. So first one is a signal-to-noise problem in our climate models. And you may also wonder, what about a pre-1950 period and what about AMOC? You can check our papers. Thank you.
Anything? I have one quick question.
Hi, Jeff. Hey, Pedro Dinesio here. I was wondering if you have any ideas on why the internal variability doesn't seem to explain that correlation. What's wrong about the internal variability? I would hope that the models can produce A and B, internally generated A and B-like variability. What's wrong? Is it just not persistent enough, or the amplitude, or the patterns?
Could you say it again there? So it is a lot of noise in my speaker here.
Okay, I'll repeat the question. I'm wondering if you have any ideas of why the models internally generated variability cannot explain the relationships that you find in nature. I would expect that the models will have an A and B internally generated. What's wrong about it?
Oh,
is it not persistent enough, or too weak, or the pattern is wrong?
Oh, yeah, this is a good question. So I think because when it is internally generated, there is a lot of other processes in our climate model or in the real climate. So it could affect the AMV's relationship with the Sahel rainfall, like the Atlantic hurricanes. So in that way, so if it is internally driven, it is always like has a kind of large spread there. But if it is driven by external forcing, then everything follows external forcing. In that ways, they are always coherent. So they shows like a large correlation there.
Thank you.
Yeah.
Thanks. Okay, let's move on. Next speaker is.
Oh, I speak. Okay. Is this a pointer? Is one of those. Right now. Is it me?
No, it went to sleep because the presenter.
Protein. If you have numbers, it's protein. Right. So when we got the invitation to, or the reminder to send presentations, I thought I would practice communicating the ideas behind this work that I'm doing with Julia Mindlin, who was here last week. Now she's back in Germany and it's really late in Germany. So I decided, and since I'm heavily involved in writing a paper presenting these results, because it connects concepts from nonlinear dynamics and ENSO dynamics. So I'm the ENSO person in this paper. And it's kind of interdisciplinary, at least for me, because I'm not a nonlinear person, but I kind of been converted. So I thought, well, maybe I'll present and see if I can practice communicating these ideas and if they start making sense in my head. So thanks for being here, because it's the first time I present this. How do I, next. So there's these huge questions outstanding in ENSO research that we still, or we think we have answers. But when Julia contacted me years ago with these results, they made me rethink this conventional wisdom. So is ENSO an oscillation? Just to remind you, the oscillation in the name of ENSO, the El Niño Southern Oscillation, it's not a temporal oscillation. The Southern Oscillation is a spatial oscillation. So this is a bit redundant. When we talk about oscillation here is the temporal evolution of events. So these are different oscillations. And currently we think, no, El Niño is a series of events. There's very little oscillatory behavior. So when you have an El Niño event, a La Niña event, and then the system loses the memory. And after a while, another El Niño event happens and the cycle restarts. So the predictability is largely lost after La Niña. I've done a lot of research on this with my collaborators, Clara, Yuko Kumura, Xian Wu. And so you need noise. That's what we think, that you need noise to reinitiate the cycle. Although today we had a talk that showed that perhaps the North Pacific alone can do this without relying too much on westerly wind bursts. So I feel like these questions are still up for grabs. And the other question, this other massive question, is ENSO irregular due to chaos or due to noise? And here the distinction is that when we say noise, we talk about external noise, so noise that is external to the coupled ocean-atmosphere system. So it's just the atmosphere alone. And to answer these questions is hard. These questions have been explored for decades, since the 1990s, especially if there's chaos in ENSO, but there's no evidence of chaos in nature. Perhaps because people were excited about chaos in ENSO in the 90s, and we didn't have enough observations, and now we have 30 more years. So perhaps Julia, when she was doing this analysis, she got lucky just because we have 30 more years. We also, I think, I'm not gonna diminish her work, but sometimes you make discoveries just because you're at the right time. So perhaps this is the right time to visit this question. Also, the other reason why I think we found this is because we use CSM2, and CSM, since CSM1 and CCSM4 have a very realistic El Niño Southern Oscillation in terms of temporal evolution. And we spent so much time looking at that with Yuko, Clara, and Xiang. So perhaps it was just the right time. So the idea that ENSO is a cycle or a series of events goes back to a paper by Billy Kessler in 2002. So So these are the observations that he had back then. The solid line is a Neo 3.4 SST index, and the dashed line is the depth of the thermocline, zonally average across the equator. And we think these two quantities define a phase space. I'm going to try to use nonlinear dynamics concepts. But that's the oscillation, right? You can see that one leads the other. So, and this is what underpins almost any theory or conceptual model of ENSO, is that it's an oscillation between the depth of the thermocline and SSTs. The thermocline deepens prior to El Nino, that warms the central equatorial Pacific, then it shoals and it drives the onset of La Nina. But if you squint, you start seeing these phases, and this is what Billy identified, and then Yuko and Clara wrote another paper on these ideas, and then I came on board on this topic, that you have these phases after La Nina where things somewhat slow down, that you have a deeper thermocline, but it takes forever to deepen, and you have this long-lived La Nina. So you can write these two quantities in phase space. So these two quantities define a phase space, Nino 3.4 index on the x-axis, the depth of the thermocline, the anomalous depth. So deeper, positive is deepening, negative is shoaling. And you can see these orbits, the system going around. So let me see if I can point you but it goes around like this. I should have put an arrow. So you have these, where the circle widens, you have the big El Nino events, like the 97 El Nino that you see labeled there. In this analysis, Billy only included the first part of the 1997 event. This ends around 2000. So we see the ending of that event, but not what happens after. But you can see that when you get to this part of the quadrant, the La Nina part, with the deepening of the thermocline, things slow down. All those points are a monthly value, so when they get together, it means things are moving slowly. So there's something about this oscillation that slows down during this La Nina phase. Oh, that's what I wanted to make. I should trust myself. So you see that oscillation that accelerates during El Nino, and then it slows down. With Clara proposed a mechanism why that happens. The thermocline becomes decoupled during the La Nina phase from the SSTs. NCAL models are really good at doing that, at least until CSM2. CSM2, I hear that there's some problems with CFM3, but we shouldn't get too worried yet. And there's these ENSO chaos papers, which are pretty obscure for a linear person like me, but essentially what they show is that if you can create chaos, so irregularity in a model, but these are conceptual models, so zero-dimensional models like the delayed oscillator, and if you crank up the coupling and make ENSO unstable, and you add the annual cycle, at some point the annual cycle starts disrupting the oscillation and makes the oscillation skip a year. And you can make the ENSO events last longer. And sometimes they last 2 years, sometimes they last 3, sometimes they last 4. And that's what you see on the y-axis there, is that's the frequency or the inverse period. So 1/4 is 4 years. And you crank up the coupling and in the model, and then the model starts creating this chaos because the annual cycle of the tropical Pacific climate entrains ENSO and makes it skip a bit or not. And you can create a lot of irregularity. But the issue in these models is that in these models, you need a lot of coupling for this to happen. And that's somewhat unrealistic. So there's a lot of research on this, but the good thing is that now we have more observations. So this is 1990s, 2000s. And now I've become obsessed with this time series, and I feel like I'm seeing things in this. It's not so irregular as I thought it was. And you see these rapid transitions, right, from El Nino to La Nina. Everyone knows that. Even my mom knows that after El Nino, there's a La Nina. And then you get this slow crawl out of La Nina back to El Nino. Like we saw in 1997, it takes multiple years, but it's never a fixed period. Sometimes you can count 5 annual cycles, the little spike. Sometimes you can count 4, sometimes you can 3. So there's these periodicities or these orbits, like the system likes to return to the starting point. So now we can explore these questions because models have improved in the simulation of the oscillation. And here I'm plotting the lagged autocorrelation function. So it's the correlation of the Neo 3.4 index with itself. And you can see in observations to the left, the very active period since 1980, and then the evolution of the NCAR model. So now we have great models to do this and to study, see if there's chaos in climate models and in observations. So our approach, I'm going to try to go fast because I probably spent too much time with my intro, but I think it's important. So we looked at orbits in the observed and simulated Neo 3.4 index, in climate models, and in observations. We use different metrics to capture the orbits. The close return maps, it's very simple. You're just trying to look where the time series starts to look like itself. You count the time that elapsed when the time series, and even there's a lot of methodologies to do that. And then time delay embedding, this goes back to Ethereum by Takens. I'm really new to this. I've learned all this stuff in the last year on YouTube. But the idea is that if you know one quantity of a system, say SSTs, the Neo 3.4 index, in that quantity, you have information of all the phases. So you can reconstruct all the phases of the attractor of the system from just one variable, just by embedding, by delaying that variable without knowing what the thermocline does, what other quantities do. So then we have a mathematical model of ENSO. It's still not physical, it's just mathematical. We're still struggling to connect it to the physics, but it has some of the features that we observe in nature. And then we look at semi-6 models because you might be interested about that. So a few tricks to look at the orbits. We kept seasonality in the time series. So if you look at this time series, it's Neo 3.4 SSTs, but the full quantity. We keep the annual cycle. And you still see that it looks very much like the anomaly version of this index. But we want to keep the annual cycle because we know the annual cycle sometimes goes away and comes back with ENSO. During big and new events, the annual cycle goes away, almost disappears. And these two modes interact with each other. The annual cycle is really not a force mode, it's a couple mode because it's forced by the position of the ITCC. So that's one of the things we did to look at the orbits. And the other trick was to look at satellite data that has sub-monthly resolution. So we are trying to reconstruct these transitions, especially when you have the seasonal fluctuations in this time series with more temporal resolution. So you can get those peaks, the curvature, and in that way reconstruct the smoother attractor. So we're working with weekly data, and from the model output, we're working with daily data. So this is the first metric. It means these are the close return maps. It's just a point is when the time series creates an orbit that looks like itself. The key thing here is the histogram to the right. And you can see that the histogram, the frequency at which these orbits occur, has some peaks. And the peaks are multiples of the annual cycle. So these orbits happen every 3, every 4, actually every 2, 3, 4, and 5 years. It's what you see the time series. You almost see it with your eye, that the time series starts looking like itself after a while. The important thing is the attractor. Okay, let me see if I can go back. So I had an animation there to show you the attractor. Then we reconstructed the phases. Essentially, we find that the system has 3 dimensions. It makes sense. It's the SSTs, the thermocline, and the annual cycle. So, but here we reconstruct them in this lagged Neo 3.4 index. So this axis is the Neo 3.4 index. This is the lagged Neo 3.4 index and another lag. So that's how we reconstruct the attractor. And you see that we find the 2-year orbits, 3-year orbits, 4-year orbits in this phase space. And this, when you look at these orbits in the time series, they correspond, the 2-year orbit is like sequences of neutral years, because you can see that it's almost centered in 0 in this 3D space. The 3-year orbit has that loop. So it went to La Nina, and it kind of went back to La Nina. So every one of those curves is like La Nina happening again. And I've been obsessed with those multi-year La Ninas for years. So it's nice to see them in this way. And then the 5-year orbit, I think, is really cool because it has multiple La Ninas. It's just, that's the, I'm trying to remember which event it is. But it's one of these big events followed by a multi-year La Nina. And you can see that actually the system kind of becomes predictable. It gets logged in that part of the attractor where it's almost like a limit cycle. The system keeps coming back to La Nina for a few years. And that's also a nice result because we've shown that some multi-year La Nina are very predictable. The system gets trapped by that, but those cold SSTs, by that thermocline that cannot deepen and kill La Nina. So this is all nice to see. And this is our conceptual model. Until now, it's mathematical. It's just an asymmetric oscillation. So this is our underlying oscillation. You have El Niño events that grow quickly, that overshoot into La Nina, that they produce a peak, and then the system slowly comes back to another El Niño, and the system oscillates. So we have a mathematical form for this. I think I have the equation here. No, I don't. This is a different version of my talk, but it's okay. So there's a you can write an equation with two phases and with just two modes to produce this time series. The nice thing is when you add periodic forcing, the annual cycle, so you can add to your equation cosine omega t, like something with a periodic forcing that will start perturbing it. If your forcing doesn't have a strong amplitude, so if that periodic forcing is weak, you're going to create a regular oscillation. So you still see the same elements of the time series, but it still doesn't look like the Niño 3.4 index, right? Because the annual cycle is not entraining the slow asymmetric oscillation, and it cannot make the system skips these years and produce chaos. When you crank up, this is done mathematically, when you crank up the amplitude of that periodic forcing, which represents the annual cycle, you can start creating irregularity. And you can see that most of the irregularity happens during La Nina and the return to El Niño, but not from El Niño to La Nina. The model still retains those really sharp drops from El Niño to La Nina, which we also see in nature. We always see La Nina after El Niño. Even this year that everyone thought we were not going to have a La Nina, here we are with La Nina called by NOAA a month ago. But the nice thing is that this equation creates chaos. It creates irregularity. And you can see the attractor with orbits that have that fast transition on this side of the orbit, and then the curves that represent this multi-year La Nina. So the nice thing is that you can apply some of these ideas to CMIP models. And perhaps this is the interesting part. I'm picking on two models. I just realized I'm picking on the Australian model here, and Julie's here. But there's essentially two subsets of models. There's a subset of models that doesn't simulate these orbits correctly, like we see in nature. When we look at the close return maps, that metric of how the orbits look like each other, we cannot see clear peaks in these long control runs. So these are control runs, daily data from very long control runs, lots of years. I'm just showing here a portion. And you can even see it here in the attractor. You don't see those curls that look like La Nina, these little things that the attractor does to go back to neutral and then to overshoot into El Niño. Whereas if you look at CSM2, it does it. You get all these multi-year La Nina, and you can also see that it has all those orbits with periods that are multiples of the annual cycle. 1, 2, 3, 4, up to 5. I think I'm going to stop. No, I'm going to show this. So something intriguing from these two models, and it's consistent for all the models in the two subsets. So essentially, there's about the same amount of models in one subset and the other. So Access, this model that is not as great as the observed chaos, has an oscillation when we looked at it as an autocorrelation function that is too oscillatory. It has this peak at 24 months, which has this tendency to produce El Niño events that just go that last 2 years. So you have El Niño, La Nina, El Niño every 2 years. And again, not this richness of orbits like CSM2 that has orbits that are 3 years, 4 years, 5 years. And when you compute the lagged autocorrelation function, it ends up looking like it does here with a loss of memory. And it's really not a loss of memory. It's that the events are decorrelated. Some last 3 years, some last 4. So when you do the lagged autocorrelation function, it looks like the events lose their memory. But there's an underlying oscillation that it's chaotic, so it's hard to predict, but it doesn't mean that the system is a series of events. It's just this fast, slow oscillation with chaos on top produced by the annual cycle, just perturbing the onset, essentially the end of La Nina. When you have a La Nina and it's trying to end and decay, then the annual cycle comes back and it excites that La Nina back to another La Nina. And perhaps it does it a third year or not, and it goes back to neutral. And in that chaotic way, El Nino goes back to, well, La Nina goes back to El Nino. So it's a bit of a stairway, but not like the one from the chaos papers that I showed before, but it's a slow return to El Nino that La Nina does chaotically. And that's why we see this range of La Nina events with 1, 2, 3 year durations. So the conclusions, we think there's evidence of chaos in observations by looking at these orbits reconstructed with this time embedding. We think that chaos arises, it's actually a saddle node bifurcation that happens during the slow phase of La Nina. The coupling is so weak that it's hard to perturb by the annual cycle. So La Nina is trying to end, and then you get the annual cycle comes, and it pushes the system back to La Nina or back to neutral. And if it's in neutral, it pushes it back to La Nina or neutral or back to El Nino. And that's how the system comes back to having another El Nino. So chaos, that's what I just said. Chaos alters the duration of La Nina, but and not so much El Nino. We still have some 2-year El Nino, but not as many. A few 2-year La Nina are highly predictable once they get into that part of the attractor that the thermocline is so shallow that it's really hard to bring it back to deeper and kill La Nina. So chaos also delays and shortens the return to neutral and the reinitiation of the cycle. There's realistic ENSO chaos in a subset of CMIP6 models. And we think that the unrealistic models might have either a weak annual cycle. This is an old problem, right? When models used to have a bad annual cycle of the Pacific cold dome. And perhaps some models still not have a great annual cycle that can entrain into the oscillation and produce this irregularity. The other issue could be just producing the asymmetry in the oscillation. We need models that have to produce that slow part of La Nina. So I think I'm going to stop that and there and ask any questions.
I have one quick question about doing the transition next to the speaker will be Avery. Avery, yeah. Okay.
Really good talk. I'm curious, so as we are developing CSM3, right, it's hard to get a lot of years. And so I'm wondering, how many years do you think we need in order to assess something like this? Do we need 1,200? Do we need?
Good question. Perhaps no, you don't need a lot because we did it with observation. So 70 years. Yeah,
Yeah.
It should show up in 70 years, perhaps.
Yeah, we should look.
Although the last 70 years are very active ENSO. So maybe I take that back. Maybe double that.
Okay.
But it's not 500.
That we can do.
Yeah.
It's really cool.
Steve? Yeah, I'm just thinking about John Fasula's work and whether, wildfire emissions are part of the chaos of the observed ENSO cycle that models are not representing. And how that colors your interpretation of the model ops comparison.
Not sure I understand the question. The one thing is that when you look at the Nino 3.4 time series, things break down. This fast, slow oscillation breaks down during the last 3-year La Nina, the 2020, 21, 22. That was this 3-year La Nina that came out of nowhere. It was not preceded by a big El Nino. But the nice thing is that John showed that it had another cause. So I'm happy with this explanation because of that, because it's pretty convincing that 3-year La Nina was very unusual in the sense that it was not preceded by a big El Nino, perhaps because of the fires forcing it. So I'm happy. Are you happy?
Yeah, but I guess my point is that comparing long PI control runs to the observed record, you're missing that element. Understanding model simulations.
That's what we have. I mean, if you don't use observations, you're still stuck with all those old chaos papers that look at chaos in conceptual models that are unrealistic. It's almost like, I think it takes some courage to look at observations, but yeah, you can exclude that part too. Actually, it's when things start breaking down is during that part of the record, the recent years, it stops working. And perhaps we're looking at it maybe at an interval where ENSO was very active and very chaotic. If you go back to the pre-60s when ENSO was weak, maybe it was just more noise dominated. So this is a recent ENSO thing.
Okay, what's the next task?
Thank
Go ahead, Avery.
Thank you. Yeah, so thanks for being here. I'm going to talk a bit about the work I've been doing during my postdoc with these folks up here, some of them are in the room, to think about different ways to disentangle kind of warming versus circulation influences on precipitation. And I'll get to some of the new nudging experiments that we're doing because that's what I promised in my abstract, but I'm going to talk about the statistical decomposition method at first. Okay, so I think we're all familiar with many of the challenges that exist in kind of being able to quantify drivers of precipitation change, but I wanted to motivate with kind of a summary from one of my favorite chapters in the last IPCC report, where they say there's high confidence that anthropogenic forcing has contributed to mean multi-decadal precipitation change across several regions, including Western Africa, Southeastern South America. It's really challenging to robustly assess the magnitude of relative contributions of greenhouse gas forcing, including stratospheric ozone depletion and different species of aerosols, because of things like the large role of internal variability, observational uncertainty that's worse in some regions compared to others, modeling uncertainty, and forcing uncertainty. So what I'm interested in better understanding potentially is the role of internal variability on precipitation change. And the way that I'll do that is first by kind of teasing apart precipitation into its kind of two mechanisms that contribute to precipitation change under global warming. We're thinking about the thermodynamic and warming contributions versus the dynamic or large-scale circulation changes. And so by thermodynamic, we're talking about changes that follow Clausius-Clapeyron and suggest that a warmer atmosphere can hold more water vapor, loosely following the wet get wetter, dry get drier. And then with the dynamics, we're talking about results from shifts in atmospheric circulation, which can affect the horizontal and vertical transports of water vapor, where we know from modeling studies that in response to greenhouse gas increases, we expect to see an expansion of the tropical Hadley cell and subtropical dry zones, and a poleward shift in storm tracks. So my driving research questions, the first one is really a mouthful. Can we better understand the role of internal variability on precipitation change by quantifying the relative contributions of dynamics versus thermodynamic changes in the CESM2 large ensemble? And then the second question is in the same vein, but using idealized experiments, what is the influence of warming alone on precipitation change when we control for the circulation? So I'll start with question one. And so I'll walk through how we quantify the dynamic versus thermodynamic contributions. So this is a fully model-based analysis. Looking within the CESM2 large ensemble, we're using daily data, so 500 hectopascal vertical velocities and daily precipitation. Considering the mid-latitudes broadly in both hemispheres from 20 to 70, I'll focus today just on the northern hemisphere. And we're comparing two periods. So our historical is 1981 to 2000 versus the future period, which is 2081 to 2100, focusing on Northern Hemisphere winter, DJF, CESM2, so fully coupled ocean and atmosphere biogeochemistry land model. And we're looking at just the 50 models with the CMIP6 forcing. And so SSP 3-70 for the future scenarios. So in order to do this decomposition, the first step is to obtain a probability distribution function, or PDF of omega, or vertical velocities, for both a historical and future period. So this is just an example of what that PDF looks like for all northern hemisphere mid-latitudes, where the x-axis is vertical velocity in hectopascals per day, and the y-axis is the relative frequency, and we've reversed the values for vertical velocity such that the positive values represent ascent and negative values represent descent. Here, our black line is the historical data, and the dashed gray line is our future data. And then once we have this PDF, we composite daily precipitation for each omega bin for both of the periods, and that looks something like this, where again, we have the x-axis being the vertical velocity, and now the y-axis is daily precipitation in millimeters per day. And so you can see where we have ascent, that's where our rainfall is occurring, and there's little to no rainfall occurring. Where we have descent, there's a slight uptick in the amount of rainfall that's occurring per given omega bin in the future compared to the historical periods. But so this is just, like I said, an example to kind of show the distributions that we're looking for. So we get all of these at each grid point. And then the dynamic change is the change in the mean precipitation due to the change in the omega distribution. So simplified mathematically to look something like this. So it's the differences between the circulation and holding the precipitation binning constant. And then the thermodynamic is just the opposite, where now we're considering the change in the expected precipitation for a given omega, which would simplified look something like this. So the two kind of distributions of precipitation binning, considering the historical circulation. So we'll do that at every grid point, and then we can look at the thermodynamic and dynamic components. So diving into some of the results, these are the ensemble mean results for 50 ensemble members, considering the historical and future precipitation change. So just this is the total precipitation calculated from the model. Some key changes in the forced response. We have an increase in rainfall over land, mid to high latitude lands, some drying over the Mediterranean regions, and over the warming hole, which we haven't looked into, but would be really interesting to think about more. And then we see some evidence of a shift of the storm tracks with a decline in rainfall kind of equatorward of the storm tracks, and then an increase in rainfall poleward of the storm tracks. And now this is just the ensemble mean of the thermodynamic contribution as we calculated it. So you can see that the thermodynamic contribution is largely capturing much of what we see in the total change. We're getting much more rainfall, or much more of an increase over the North Pacific than we see in the total. But overall, in this ensemble mean space, the thermodynamic captures the total change pretty well. And then when we look at the dynamic contribution, we basically have little to no contribution from the dynamics to this total mean change in the mean space, except for over the North Pacific. We're getting this interesting drying signal here. And then we do see some evidence of the storm track changes, but overall, especially over land, the dynamics are really not contributing to the changes in the mean space. Now I've just zoomed into the Western North America, and you can see even more clearly how well the thermodynamic term is capturing the total kind of forced response, and that there's little to no contribution from the dynamics. And now here I'm just including showing the standard deviation across all of the precipitation change maps. So we do this across the 50 ensemble members. And you can see that there's a lot of variability in the precipitation change along the west coast of Canada and the US. And that this isn't necessarily coming from thermodynamics, but it is coming from the dynamic term, and this makes sense, right? That the ensemble, the variability would evolve differently, so it would collapse to zero in the mean space. And so now what I want to get into is thinking more about what are the spatial patterns that lead to the variability in the projected precipitation change. So to do that, I'm using a machine learning algorithm, self-organizing maps. So I just feed the algorithm the 50 precipitation change maps, And this is just a 3x3 node result. And I don't have time to get too much into the details of this. But so these are kind of 9 patterns that of precipitation change within CESM2 that the algorithm identified. And I want to focus specifically on kind of this SOM1, which is this very wet case where it's centered over Northern California, and it's the wettest kind of pattern across all of them. And then we have these kind of moderate cases with increased rainfall either centered over Northern California or centered more in the Pacific Northwest versus this very dry case or the driest case where California could see some drying. And so now I want to think more about what is what's behind these patterns in terms of the thermodynamics and the dynamics. So you just saw these on the last slide, and now these are the thermodynamic contributions to change clustered across the ensemble members identified by the SOM algorithm. So the key takeaway here is that at first glance, at least, the thermodynamic maps are pretty consistent across all of the 4 SOMs here, where there's wetting over the Pacific Northwest and some drying over the Southwest US and over Mexico. So there's some variability in how far north that dry to wetting transition is occurring, but overall they're very consistent compared to when we look at the maps now when we've clustered over these same ensemble members, but for the dynamic contribution. So there's much more variability in like SOM1 versus SOM9. So SOM1, which we know is the wettest pattern, the dynamic term is contributing to that, whereas SOM9 is the driest members, and the dynamics are contributing to that drying. And then here I'm just showing the ensemble results again from the SOM algorithm, but we've removed the ensemble mean before we fed the precipitation change maps to the algorithm so that we could look at the internal variability across the ensemble members. And what I think is really interesting is the fact that these kind of top 4 maps, the total precipitation change with the ensemble mean removed, are captured quite well by the dynamic change that we've calculated. So then we can make the argument that the dynamic contribution, as we've quantified it, is capturing much of the internal variability within the large ensemble pretty well, and that the consistency across all of the thermodynamic patterns continues to kind of solidify the fact that the thermodynamic contribution can be thought of as capturing much of the forced response across the ensemble. And then the next piece with this is then to ask what are the large-scale atmospheric circulation changes across these SOMs. So again, here are 4 SOMs of interest, and now I'm showing changes in circulation. So this is just 500 hectopascal geopotential heights with the zonal mean removed, and it's the change between the climatologies of the 2 periods, so the future minus the historical, and then the ensemble mean is removed to capture some of the variability. So like in SOM1, we have these anomalous negative trends, which would suggest an eastward extension and strengthening of the subtropical jet, which would lead to the increased rainfall that we see in SOM1. And then SOM9 has the opposite, so it has more anomalous ridging in the region, which would lead to these drier conditions here. So my original question, or first question here, was can we better understand the role of internal variability on precipitation change by quantifying the relative contributions of dynamics versus thermodynamics? I think yes. I'm still interested in getting at this question of why do some ensemble members see an expansion and strengthening of the jet while others do not, given that all of the ensemble members are experiencing the same forcing, and potentially then can this help us rule out some of the scenarios in CESM2, which are following questions posed by Kevin Grice in this really cool GRL paper, where they did a similar analysis, but across all of CMAP6, and found these differences across the ensemble members and related it to be potentially biases in the historical climatologies of the circulation. But what's novel here is that we're able to look at this within one model, which should have the same historical climatologies, more or less, or at least not have the same biases across all of CMIP 6. Okay, so I have one-ish minute to introduce these nudging experiments that I'm really excited about and that Will Chapman helped me set up. So the question we want to isolate here is now, in the first part, we're statistically decomposing dynamics versus thermodynamics. And so with nudging, we said, okay, well, what if we just fix the dynamics and just allow the warming to evolve? So we have this experimental design in CAM 6 where we have the AMIP nudged hist. I'm happy for suggestions on the naming. So the historical and the future, they're nudged to the same Era 5 winds for reanalysis. So it's U and V nudged every 6 hours from 850 pascals to the top of the atmosphere. The historical run is from 1979 to 2014. The future one is 1979 to 1998. And the differences are just the sea surface temperatures. So in the historical run, it's the prescribed historical SSTs and CI6N. And then for the future run, it's the we take the CESN2 large ensemble mean from 2081 to 2100. So the circulation should essentially be the same, and the only difference is the boundary conditions of the SSTs and sea ice. And so this is just kind of our bird's eye view of the Northern Hemisphere. We see this shift, what appears to be like a shift in the storm track, but the storm track shouldn't actually be shifting. And when we look, then we zoom in to Western North America, we see drying over California. And I'm kind of stumped by this. Why would the North American Southwest get drier under historical large-scale circulation patterns and a warm ocean? So these runs are still kind of new, and I haven't dove into them completely. But the questions I'm thinking about with these are, like, what are the precipitation trends in each nudged run? So over the 2 periods, how different do those trends look? What does the tropical Pacific look like during the different periods that we're considering? And then another idea with this kind of framework of runs is that I'm really interested in is, can we use these simulations to also better understand trend biases in hydroclimate in models more broadly. That's all. Thank you.
Do you have any questions?
Really nice analysis. I was wondering, so the use of the historical run as your climatology, I guess, will have quite a lot of influence from aerosols, and those aerosols will be different in each member. And so I'm wondering if you used a base period in the 2020s or something, maybe the aerosol influence would be less, and to see if you got the same result.
For the nudging runs?
No, for the thermodynamic process.
Okay.
Change, just to see if you get the same patterns or if they're kind of driven a bit by the aerosol.
Okay, yeah, I like that idea. I have, within another cooperation, I was going to just compare like 1981 to 2000 to like 2000 to 2020. So that's an extra reason to then do that. So thank you.
I just wondering if you can expand on that. You said in the previous section at the end there that you could potentially rule out, and I missed the way you would rule out possible CSM scenarios or
Yeah, so wondering if, or yeah, like, is this scenario of, can we rule out the scenario where there's no extension of the jet potentially? I haven't thought exactly.
Yeah, yeah, that was a question. What would constitute a reason to rule something out?
Well, I guess it's not what we expect based on the theory, right? So then get like that. And one thing that I'm really interested in and didn't get into, but thinking about like if the potential state of the historical period and that climatology has any influence on then how the forcing evolves. So thinking about the evolution of these modes of variability and seeing looking then and identifying kind of like which ensemble member most matches our realization that we're living in. Does that make sense? No.
Okay.
Thank you.
Let's move on to the next talk. We'll give you Ben Lenton.
We're gonna have to download mine as well. It's
Oh,
slow.
Use this one.
Am I coming through on the mic? Cool.
Awesome. Well, thanks for having me here. And thanks to Claire for the push to submit this. I forgot to actually update her affiliation, but this is work primarily done and entirely led by Ulla Heel. I just recently learned how to pronounce her name kind of correctly. She learned some Danish. She's now at Seaworthy down in Pearl Street. But we're still chugging along trying to get this paper out there. And so in this study, we looked at the Pacific warming pattern and how it modulated future hydroclimate across the Americas. And so I'll give a brief motivation that has some overlap with Ari's. In particular, I'll talk about the issue of ocean warming patterns and the tropical Pacific paradox issues in our models we've been seeing. And then I'll mostly spend my time talking about a series of AGCM experiments that Ulla ran in CAM 6, looking at the sensitivity of hydroclimate to possible future scenarios of the tropical Pacific. And so Ari set me up well. Nice job on this schedule. But precipitation really matters. It's really dynamically difficult to understand at basically every time scale. And it's really linked to a lot of the adaptation we're going to have to take to climate change. And so even in IPCC consensus reports, there's a lot of uncertainty and long-term trends and variability. But what I'll be talking about today is we also really need to understand the link between large-scale ocean patterns and variability with terrestrial hydroclimate changes as well. And so as Ari was talking a bit about our first pass theory for precipitation changes is held and sowed and wet get wetter. But there was this neat study that shows that wet get wetter doesn't really work over land at all. And so just to summarize from this paper, I thought it was pretty neat, but basically only about 10% of global land area follows Heldensoden. And in particular, it really isn't followed in regions where there's going to be the most direct socioeconomic impacts. And so we can't take just our Heldensoden theory and apply it to think about what will happen to precipitation in the future. And so in general, we have a few really robust projections of the future. And so this is a study of Flavio, Clara, and Isla's, where they were attributing changes in future hydroclimate. This is historical, but the Southwest US is one of these regions where we've at least been able to attribute historic changes in precipitation really strongly. But there's a lot of uncertainty, even if we can say something about the past, there's a lot of uncertainty in the future, especially when you account for multiple scenarios. It's just one of the IPCC massive figures showing a lot of different possible futures in this region. And this is all using these CIMMIT models that kind of in the past 3 to 5 years have been shown to have some pretty systematic biases in their forced response to sea surface temperatures in key regions driving North American hydroclimate. And so this is from the Rob Wills paper. And the key bit here is just that the ERSST trend over the past 40 or so years in the top left has a very different pattern than the multimodal SST trend. And this study and many others have shown that this observed is almost at the very edge of internal variability across CMIT 5 and 6. And so that really is a problem because as folks started showing at least as early as 2010 and probably much earlier, depending on how the tropical Pacific warms into the future. So here I have a La Nina-like scenario and an El Nino-like scenario. Depending on how the tropical Pacific warms into the future, we see very different responses in the hydroclimate. And so your eye, of course, goes first to the big changes in the tropical Pacific that are going to be directly driven by these changes in sea surface temperatures. But zooming in on this box a bit, you can start to notice that there's also some pretty big differences over land in the Americas. And so I think there's probably earlier studies as well, but this was done all the way back in 2010, saying really the sensitivity of these future long-term trends in the Americas is really sensitive to how the tropical Pacific evolves. And so the research questions that were motivated throughout this study were really trying to understand how the pattern of tropical Pacific warming influences the terrestrial precipitation trends. In particular, how to think about this SST warming affecting not only long-term trends, but the variability, and particularly those driven by ENSO teleconnections. And then we also really wanted to know about, okay, we have trends, we have some seasonal variability, but what about extreme seasons, either seasonal droughts or really kind of seasonal floods? And does this SST warming pattern change the occurrence of these extreme seasons? And so as I mentioned, this experiment was all run in CAM6. We were using just off-the-shelf CAM6 with prescribed monthly SSTs. And we run some future simulations from 2015 to 2100 with the 585 scenario. And the SST forcing was an idealized concoction of an idealized ENSO pattern, a linear warming across all regions globally other than the tropical Pacific, and then two different tropical Pacific warming patterns, which we called no EP or EP, where EP means Eastern Pacific warming. And so what the no EP is, this trend is using the observed tropical Pacific pattern or observed tropical Pacific trend, and then superimposing a linear warming on it as well. So it looks basically like the La Nina-like warming we've seen over the past 40 years. And then in the EP, we took, I think this is actually a mistake. I think we took the CESN1 warming. We also ran the CESN2 warming, which had an even more extreme Eastern Pacific warming pattern. And so to compare this to a control and to build a climatology, we ran an equivalent number of years of CAM6 AMIP, again, just using the observed monthly mean sea surface temperatures from the year 2000 with that same idealized ENSO pattern on it. So we weren't dealing with a difference in how we were treating ENSO seasonal variability or ENSO interannual variability. And so we didn't follow Pedro's nice asymmetric pattern of ENSO here when we were describing our pattern. We have a very regular ENSO. I just wanted to decompose this a little more, but we took the spatial pattern as just the first EOF after detrending the Pacific. And we had a temporal pattern of a large El Nino followed by a large La Nina, and then a few years off, and then a small El Nino followed by a small La Nina. So if we were to run this again, we maybe would change that a little bit. But the idea here is that we wanted something pretty regular to just allow us to subset across events pretty clearly. And so to get into some of these results, the first big question was to try to understand how these different possible warming patterns in the tropical Pacific influenced hydroclimate trends. And so on the top, I have the trends across the entire simulation, across all members from the EP, or excuse me, from the EP and the no EP. And there's a lot going on here. I have both precip and sea level pressure, or surface level pressure, excuse me. But here are the differences. Again, these are really dominated by differences over that tropical Pacific region that we're directly modifying. But still trying to play around with colors to make them stand out, but we identified 6 regions over land where there was a really coherent difference in trend, as well as generally we also had like literature of people that have been studying hydroclimate trends in those regions. And so this allowed us to look at more interesting statistics and variability of how these trends were emerging. And so one thing we started with is just how these trends were emerging seasonally. Were these primarily changes during the wet seasons? And if so, how? And so just to talk through this figure, I'm now looking at the California region, which we call the US West Coast. And so the first histogram is just the occurrence of precipitation events, where we're seeing a shift in intensity of rainfall between these two different scenarios. The next figure is the time series, both the raw monthly time series of precipitation as well as a smoothed one. And so in this case, you can see that we have pretty similar trends on average across that region, as you can see averaging out the slate wetting and the slate drying. But what's interesting, even if the first two panels don't show much of a difference by eye, we see quite a big difference in how the seasonality of precipitation is changing in the last figure here. And so first, the gray bars show this seasonal cycle in our control simulation of precipitation in the, these are all NDJ-FM seasons. Oh no, sorry, this is just the seasonal cycle here. I'm about to go to winter. But this is the seasonal cycle in this region. And you can see here that there's obviously not much of a change when it's not raining, but we have a real difference in timing of precipitation. So when there's the more La Nina-like pattern or the no pattern in this figure, we see a much earlier timing of precipitation. And when we get that Eastern Pacific warming, rain is much later. I'm not going to go through all 6, but another really interesting region we looked at was the Central Amazon, which is quite directly affected by the tropical Pacific through the Walker circulation. Here we see quite a difference in trends. So when we have Eastern Pacific warming, we see much more intense drying as expected just by a shift in the Walker circulation. So that's shown really clearly in the middle figure. And this is the result of drying in every single month of the year, as opposed to in the more La Nina-like pattern, we actually get a kind of enhanced seasonal cycle. And so again, this is, I guess I haven't said this yet, but this is, we're currently under review of our just descriptive paper. And as soon as that is through, this will be out for you all to look at on Glade. So we've just kind of, in general, presented a bunch of interesting statistics, but I think there's a lot of science that we can do now that they're out there. And classic NCAR computer asking me to update Chrome. But we also really wanted to look at extreme seasonal events. I mean, we've heard in the news about California, both flooding and droughts. Seasonal droughts can lead to a lot of impacts. So we were curious if there's things hiding beneath some of these long-term trends. And so this was an all-in-one figure that if I'd had more time for this presentation, I would have broken it down a little bit more. But what we have here on top is the extreme precipitation probability in our EP experiment and the extreme precipitation probability in the no EP experiment. And for both of these maps, wherever you see a cool color, that means that there's enhanced rates of wet extremes during the winter time in that experiment. So that is in the California region under this EP scenario, we see a greater risk of a wet winter. And by wet, I mean upper 2.5%, so like super wet winter compared to our control simulation. Likewise, everywhere that's red, we see increased risk of a pretty extreme seasonal drought. And so we looked at this for El Nino years and for La Nina years and neutral years. And the first thing to notice is that most of these, or the strongest signals are during El Nino years. And differencing these, we're able to see how changes in extremes might vary depending on the future warming scenario we get. And so these, again, on top, we have how do the rate of dry extremes or seasonal droughts change between the experiments. And this is the change in wet extremes or extreme wet seasons between the experiments. And so the red here is when the EP or more El Nino-like pattern has more extremes, and blue is when the La Nina-like pattern has more extremes. And so just to highlight, up top, we see that the EP scenario leads to much more dry extremes in the Amazon, suggesting that that trend is not necessarily only driven by some sort of long-term trend, but we're actually just seeing a lot of really intense El Nino impacts every few years. Likewise, we're seeing that the EP experiment showed a lot less or somewhat less drying, and that might be just because of extreme wet seasons due to El Nino. So even though we don't see as bad mean impacts, we might actually have worse extreme impacts because we're getting these intense El Nino rain seasons that could cause serious flooding and landslides. And so the last thing we did is just break out some of these distributions to really show what type of shift we're talking about. And so here's that last half of the century in the West Coast for a 4-month season, and showing that We don't really see much of a change in La Nina between the two experiments on the seasonal distribution of precipitation, but we see this really big shift towards these wet extremes. And just to talk about how extreme these are are anomalies relative to our control. And those two gray lines show the 95% confidence interval of our control. So we're looking at almost half of our distribution being in the upper 2.5% in this scenario. So these are pretty huge signals. But then we also don't really see that in the total or neutral years. So we're seeing kind of not much impact when you're looking at long-term trends, but these really intense El Nino wet seasons in this one scenario. Likewise, in the Amazon, we see really intense El Nino drying and nothing really in the La Nina. And this was pretty a common consistent pattern between these regions we looked at. Pretty dramatic differences in the El Nino impacts in these regions, and not much difference in neutral and La Nina years. This is again just showing there was not as dramatic of a shift in the total. And basically this whole bump over here in the total distribution you see here is all from those extreme El Nino years. And so to summarize, we ran this global warming scenario with and without this enhanced Eastern Pacific warming that had been seen in the CMIP models. This was intentionally heavy-handed to really just get a sense of the possible epistemic uncertainty in future hydroclimate due to this discrepancy we're seeing between our models and the observations. And we see some interesting difference both in the mean states. So drying was really intensified and narrowed towards the tropics. Particularly the Central America and the Amazon were really affected and had really different outcomes depending on the scenario. And I think something that's really interesting that is tricky to look at in these studies, but is important, is once ENSO's in play, looking at trends becomes a little bit messy. So like we might be seeing some sort of long-term patterns, but understanding in regions that are really connected to the tropical Pacific, how are those connections changing? Are we seeing mean changes due to the changes in these connections? And really trying to untangle that. And I think we did a start here, but there's a lot more to do. And so as I mentioned, these experiments will be made public as soon as we survive review. If you got this paper, please be nice. It's been like a few years now. That is Ula's email. She might share it with you earlier if you want to look at it. She's, I know, really excited to get these experiments out to the public. So happy to take any questions, but I really direct you to her. So thanks and happy to take any questions.
Have a question?
Okay. Yeah, the results for the Amazon are really intriguing. I'm wondering if the couple models do that. Are you thinking of looking at if it's a robust feature in, not in Amy brands, just in the CMIP models themselves, if you select them by the patterns or something, if you see there too?
Yeah, that'd be interesting. You might be able to capture at least some of it. The future pattern we picked for the like more linear pattern is definitely not captured in the future, but we could definitely look at the more linear kind and see if you see that, because it's pretty striking. I don't know if anyone here has looked at things like that or seen.
I haven't seen it.
Yeah.
Back in the day, I look at the teleconnections, but in the extratropics, but I never saw that feature in the Amazon.
Yeah, just even in the trend, it's pretty dramatic, the difference.
Makes sense.
Yeah, thanks. Well, so I know a shortcoming of this is because we're running this AMIP, we don't get any of the expected feedbacks to the ocean. And in particular, the Indian Ocean is hanging out. So we're not really getting a full Walker circulation response. We're getting an artificial Walker shift potentially. And that might be modulated by allowing the Atlantic and Indian Oceans to adjust. So that could be a good way to check it.
Thank you.
Thank you.
Okay. Last speaker in this session is Nicola. She's on that. Yeah. Okay.
You have to start really high.
Hi. Hey, Misola, you can share your screen.
Cool.
Yeah, you can share your screen now. Can you hear us?
Yeah, sure. Does that work?
You can share your screen. Yes. Okay, and now full screen. Yeah.
Is that full screen? No.
Not yet.
Ugh. Why not? Sorry.
No problem.
Does not want to go full screen. Let's try the PDF.
Yeah, that's good.
Okay, you can see the full screen now. Excellent. Cool. Okay, great. Sorry about that. Cool. So I guess I'm the last talk of the day, and don't worry, it's not going to be too stressful. I'm going to spend a little bit of time just presenting a new multi-model large ensemble archive and how we've created the archive, what you can use it for, and that we've applied the climate variability and diagnostics package to it, and you can kind of go and click through it and look at all of the plots that come out of it. And I'd like to acknowledge all of my co-authors here who have been kind of vital in getting this all up and running. Okay. So hopefully you can see a different slide now and the online is working. So what I'm going to talk about is the MMLEA version 2, the multi-model large ensemble archive, which is a new version of, I guess the original large ensemble archive that's been updated to have 18 models and 15 variables and is now on a common grid. And so the archive is currently available on Glade, and so you can see the link here, and it's going to be available very soon on the Research Data Archive. And we have a website, so you can check everything out on there. So as I just mentioned, we've now got 18 models. This consists of both CMIP5 and CMIP6 models and 15 variables, including some new things such as extreme indices, so maximum temperature, minimum daily temperature, and extreme rainfall, some circulation indexes, and some ocean variables. And this is all now on a common grid, so it's really easy to intercompare models. Okay. And so I've just directly taken this slide from the one Isla showed, I think, yesterday, on the newish climate variability and diagnostics package that Adam has been really key in releasing. And you can see here, as previously mentioned, that this new version of the package has some really cool new features, such as detrending options. So you can now kind of detrend both your model and your observations using various methods, and then use that to both compare the internal climate variability, or you can not detrend and look at kind of how it evolves into the future. And so what we've done is we've kind of used this CVDP version 6 and applied it to our new archive of model data, and then we've put that up on the website, so you can really kind of go and click through and look at all of the different models and what they look like before you download the data and use it. And I'm going to show some of those plots here today. But before I show plots straight out of the CVDP, I want to talk a tiny bit about why we might want to use large ensembles to compare with observations and for model evaluation. And so here you can see two plots on my screen. This is the Nino 3.4 standard deviation in observations in the orange lines, and two different model simulations on the left and the right. And you can see here that the left model kind of looks more like observations in March, April, May, June, but has too much variance in the other months, particularly the months where ENSO peaks. Whereas the second model seems to have the right kind of variance in October, November, December, January, but not in the March, April, May, June. And actually, these two models are the same model. These are the Access ESM large ensemble, and they're exactly the same model, but run with slightly different initial conditions. And so this kind of can show us that we can get quite different answers by looking at different members of the same large ensemble. And so that's why it's really nice to be able to use a large ensemble to compare to observations to see really whether the observations sit within the model spread. Okay. And so I'm going to spend the rest of this talk kind of just showing some of the plots that come out of the CVDP applied to this large ensemble archive and what we can do with it. And so here you can see a table that comes out of the CVDP, and that is online. And this shows all of those large ensembles that I mentioned for different metrics such as ENSO patterns, ENSO Hofmollers, PDV, the SAM, standard deviations in SST and rainfall. And here what you can see is an RMS difference between the model and an observational product. And what's really cool about this version of the package is you can see this metric for the ensemble mean, but you can also see it for the 10th and the 90th percentile across the ensemble. So you can kind of see how variable this metric is across different ensemble members. And you know, you can stare at this plot for ages. You can see a few things. There are some metrics that are better or worse than others. For example, you know, the PDV typically has a very low RMS error shown in that pink column, whereas the ENSO sea level pressure particularly has a high. You can see that some metrics are more variable across the ensemble than others. For example, the SST standard deviation, which is the third from the right, is not very different between ensemble members. But if you look at the ENSO spatial pattern on the far left, you can see you can get quite different results from different ensemble members. And this is just one metric of model evaluation. We can also look at pattern correlations, which is shown in this figure here. So now we can see a pattern correlation of each ensemble member for each of the large ensembles with observations across a bunch of different metrics. And I think this is really cool because you can really see how different a different member is for your different metric. And so again, if you look at the top left for the ENSO TAS or surface air temperature spatial pattern in DJF, you can see, you know, across a single model, you might have a 0.6 or a 0.8 pattern correlation with observation. So if you accidentally pick the member that was at 0.6, you might conclude the model's not that great, but if you accidentally pick the member at 0.8, you might conclude it's quite good. I will note that we looked into whether this is related to ensemble size, but it doesn't really seem to be. If you look at the top left plot here, CSM2, which has 100 members, has a very similar spread to, say, Access, which is the top one, the Australian model, which only has 40 members. So this seems to be more related to the model's own internal variability rather than the number of ensemble members we have. We can look at different metrics using this correlation comparison. And I'm not going to go through the whole plot here, but you can see that some metrics have a lot more spread than others. For example, the SAM on the top right, if you look at the x-axis, we're looking at anything from a 0.9 to a 0.98 correlation. So maybe it doesn't matter so much which ensemble member you use compared to something that is much more variable, like, for example, the NAO on the top left. Maybe you can get something from a 0.7 to a 0.9. So it really depends on what metric you're looking at. Okay. And so what we then did is we split up the 18 models into 3 sets of models, because if you apply the CVDP to all 18 models, you get so many little figures that you can't see anything. And then we compared them for a bunch of different metrics, although you can access any of the groups of models online. And so, for example, one of the things that you can do is you can just look at a simple global mean surface temperature analysis where you compare your large ensemble to observations. So your large ensemble here is shown in the blue line and the observations are shown in the gray line. And here you can see a few things. The 2 Canadian models warm much more than the observations. You can see the 2 CESM models, as people in the room there might be happy, look quite good compared to observations. And you can see the 2 Australian models look quite good in terms of their warming, but there's quite some differences going on in the kind of 1980 to 2000 period that those 2 models are not capturing. We can look at other metrics such as Pacific decadal variability. So this is a different set of models here, and here you can see on the left the ensemble mean PDV after it's been detrended. So the ensemble mean's been removed, that cool new thing that the CBDP can do. You can see in the second column error SST, so the observed product. In the third column, you can see the difference. And a really cool thing that you can see on the right is where the observations sit within the ensemble. And so if the observations really agree well with the ensemble, you'd expect these maps to be white, which you can see they're not. But you can see that there are really different biases in the PDV in different models, as you can see in kind of the right 2 columns. We can also look at things like spectra. So here I show the third set of models. This is the ENSO power spectra in the observed period. For the E3SM, GFDL models and IPSL. And you can kind of see whether the peaks sit similar to the observations in the gray line. You can see both E3SM models kind of have a shifted peak compared to observations, whereas maybe the 2 GFDL models in the second row maybe look a little bit more similar in terms of the peak. Maybe the GFDL CM3 is shifted a bit right, but they have a much stronger peak compared to observations, meaning they're potentially more phase locked and kind of more regular than they should be compared to the observed product. If we look at the bottom 2 models, you can see on the left GFDL sphere, which I think currently looks like it's capturing the ENSO frequency the best of all the models. And then the IPSL, which has a similar bias to the E3SM models on the top. Cool. Okay, and then I'm going to show you just a couple more plots. So to kind of highlight all the things we can do with the CBDP and what the models look like. Here you can see the La Nina rainfall. So this is rainfall related to La Nina in the models for the September, October, November period. And here we have one of the sets of models on the left, again, error 5 now in the second column, the difference again in the third, and the rank on the right. And I guess some of the things that kind of pop out to me here are biases in the tropical Pacific that are really consistent across the models that you can see in the third column, where you can see there's too much rainfall kind of in the far western Pacific and model biases in the intertropical convergence zone. And really, I guess what I'm trying to highlight here is that we can really compare the different models with both each other and observations and really get an idea of what they're doing and what they look like in comparison to the real world. Okay. And so the last 2 things I want to talk about don't come from the CBDP. They come from, I guess, the model output itself and things that we can do with it, I guess, by just computing and plotting the data ourselves. And here I'm using kind of output from the CBDP that's already calculated future warming trends for me, but I want to compare, in this case, the models to the multi-model mean. And so here we can ask the question, does our future warming trend in an individual model, how does that compare to the mean across all of the ensembles? Okay. And so on the left, you can see for a subset of models, the future warming trend, which kind of looks like in all models what we might expect. There's more warming in the northern hemisphere than the southern hemisphere. There's more warming over the land than the oceans. In the second column, you can see that multi-ensemble mean, and this is not just across the models on the left, this is across the whole archive, so all 18 models. Again, in the third column, you can see the difference, and on the right, you can see the rank. And I think there's some really interesting things that we can pull out here. So for example, the GFDL ESM2M model, which is the one that's really blue in the rank on the right, is blue everywhere. So it really is warming less than the multi-ensemble mean, and by quite a lot. If you look at GFDL CM3 in the top and GFDL SPEAR in the third row, you can see that they warm similarly to the multi-ensemble mean. I think one of the really interesting things you can pull out is the two E3SM models, which are the the fourth and the fifth rows. So they're the two with the kind of greenish patterns on the far right. And here you can see that those two models warm more than the multi-ensemble mean, but just in the high latitudes. And so that means that if a model is warming more than the multi-ensemble mean, it's not necessarily warming at the same rate more everywhere. And I think it's really interesting that these models particularly have more warming, but just in those high latitude regions. Whereas if you look at the bottom model, which is the IPSL model, you can see it warms less, but only in the tropics. So this is kind of an interesting way to decompose how the models compare to the multi-model mean we see in a lot of CMIP results, but also to see that it's not consistent across the globe, that there are regional differences in how the models compare to each other. Okay. And then the last plot I'm going to show looks at one of these extreme indices, which is new to the multi-model large ensemble archive, and this is the TXX. So this is the daily max temperature, but presented as like a monthly value. And here you can see a different set of models. And here I've just picked all the models that have a future scenario that's consistent. So this is the SSP 370 future scenario. And you can see the historical daily max temperatures on the left. You can see the change in the second column. You can see the multi-ensemble mean change in the third column. And then the difference between that model's change and the multi-ensemble mean change in the right. And this tells us a little bit about kind of extreme temperatures and what we might expect to see in the future. And you can see that E3SM V1 pops out really clearly as having a much stronger change than most of the models. And we're not really sure why at this point. It's just kind of a new result that we just found. Okay. So that brings me to the end of this talk, and I just want to highlight a few things. And you can see on the QR codes on the right, you can access the preprint of the model description paper, but you can also just go to the website and see what's available. The multi-model large ensemble archive version 2 is available on Glade and is about to be available publicly through the Research Data Archive. We've got 18 models and 15 variables, and it took a lot of work to put it together, and I'm hoping it will be useful to people, so please use it. We've applied the recent version of the CBDP version 6 to it, and you can actually just click through the output on that website and look at the different models without having to kind of do any analysis, which will hopefully be a really easy first pass way to look into all of the models in this archive. I think large ensembles are really needed for model evaluation because you can look at different members and get a quite different result for a lot of the modes of variability and variable quantities that we're really interested in. And this archive can really be used to do a whole bunch of things. You can compare models to observations. You can compare models to each other or the ensemble mean. You can use it for a variety of scientific questions. So yeah, so I'll just end on, yeah, please use the archive, and thanks for letting me chat about it.
Did you hear that, Nicola?
No,
The
I hear
question was,
you.
are you gonna add the Mixiclip runs, the CSM1 high resolution simulations?
I haven't planned to. We could, but I don't know if you'd want them regridded to a 2.5 degree grid.
I mean, I think they have interesting differences in terms of like the
Mhm.
Southern Ocean and tropical Pacific trends that would still be valuable as only 10 members. Yeah, Steve.
Well, I was gonna ask if you've got metrics on Pacific trends, to this the metrics that Rob showed in his paper.
You hear that?
You can look at I guess we've just got what's in the CVDP. I don't know if Adam's there and can answer that.
I mean, you're 3.4.
Yeah, but you can calculate them. And also, Spear's in there. So
That's true. Yeah.
Seems like we should it might turn up something that's interesting, right? Even though that you're averaging it down, obviously you wouldn't do that as your normal analysis of that, but in the context of all the other models.
Yeah, but yeah, we could consider adding it. The paper's under review, so we've got time in the revisions or even after that to add additional things. I guess send me an email with the link and I'll take a look.
That's good. I think Adam has run the CVDP on the ensemble, but I guess not on the regridded version of it.
I ran it on the Fred regridded it on to 1 degree. So that's 2.5 degrees.
I ask, are there any plans to do this with LESF with the single forcing runs? Okay. No.
No, if somebody wants to volunteer to help, yeah, very happy to help facilitate it. But I guess putting this together has been a kind of big amount of work, and we're hoping that to just get it out there at the moment and get people to use what we've already done. Yeah. So
I think there is an effort with less of MET on the BADC. The working groups are putting all the regridded and kind of, maybe I don't know if they're regridding, but picking out indices and things and putting them all in a common repository. Yeah, so it's not exactly the same, but it's kind of similar.
Yeah, the web interface, I think.
Okay, yeah, and I don't think they're doing that. Any other questions? I had a quick one about the regridding. What were the extremes? Are you regridding half? Are you computing those metrics and then regridding, or regridding and then computing those metrics?
regridding and then computing the metrics. Yeah.
All right.
And we haven't tested how much that changes things typically. So, yeah.
Thanks. So that was our last talk of the day. We have some time now for discussion, if there's any discussion to be had. So we did our kind of summary of the working group on sheet yesterday. So I don't know if people managed to see that. I don't know if anyone has any questions or comments on what was discussed there or anything else related to working group activities. I guess I have one question if no one has anything they want to discuss.
I can throw something just if you. Maybe it's a question for Steve. How are we thinking about the simulation of ENSO in the high-res model? That is not so great. What should we do about that? Are we hoping that in CSM3 high-res is going to be fixed and we're going to have like a high-res model with a good ENSO? Are you guys thinking about that? Is it a priority?
What's the issue with the high-res ENSO?
It's not oscillatory enough. It's too weak. It's many metrics. It's unrealistic.
Well, I don't think it's going to be addressed in CSM1, right? And the CSM3 high-res doesn't exist yet. So it's a bit premature.
It's a non-issue.
Maybe I'll just add to that. It is an issue. Obviously, it's not very realistic, but
thank you.
I have seen that too, but I have noticed that it still produces realistic teleconnections to places like the U.S. West Coast. So the variability associated with those, with ENSO in the model, remotely forced seems to be realistic, even if the INSO is not.
Yeah, perhaps the patterns are okay, right?
Yeah.
I'm thinking more of the dynamics.
Yeah,
the
it could be getting the right
evolution
answer for the
and-
wrong reasons, for sure.
And I mean, I think it's a big issue if you want to use CSM1 or any CSM high res for prediction. It probably will inherit the same problems, right? Because ENSO is too weak because too much mesoscale mixing and it seems it's revealing compensating errors in ENSO simulation in low res models, and there's something going on there, and I don't think it's going to be magically fixed in any CSM X in the future, if they have any.
The CSM1 highlights the INSO and variance is close as well.
It's too weak.
It's weak.
Yeah, if the observed values are from 0.6 to 0.8.
But Pingchang paper seem like they are very close to vision.
Yeah, I don't know what they did. I mean, we should look at the diagnostics in the CBDB. The runs on the Mesaclip,
Do you remember? I have not.
they don't look great.
Shall I bring them up?
Yeah, because I'm thinking of Ping's paper and I thought INSO looked pretty
Yeah,
good.
it looks pretty good.
I don't know what they did.
Is that the PI
That was
control?
PI control, yeah.
Yeah, maybe the PI
You said
control.
that.
Are you talking about the 10th degree ocean?
Yeah, the Mesaclip. Yeah.
Okay, because there's quarter degree coupled to 1 and quarter degree coupled to
No,
10.
yeah, and that's a good point. In the catalyst runs with the 1 degree ocean, ENSO looks like in the 1 degree full CSM1. And that was shown in a bunch of papers that having eddies, mesoscale eddies, perhaps tropical instability waves mix too much cold water from below the thermocline and they act as a negative feedback on ENSO. Which is probably realistic. I think it's revealing a compensating error in the low res model. We're missing a positive feedback.
The low res, they always have INSO variability too large compared to.
Little WebEx.
Yeah, but now it's too weak. It went the other side. Yeah. You can also Google Mesaclip. It's gonna take you to the website.
I don't know that Fred put the newest comparisons up on the Mesaclip website yet, but the ones that I sent you via email, I can.
Okay.
I would too. As soon as I get this paper.
I don't know, maybe this is important, but I'm, I think for me it's important. This is climate variability, and it's ENSO.
Yeah, I'm trying to get to when I think the systems are still not, what was that?
No, that they are.
Yeah, it seems hard to believe that the time would be spent to develop or tune CSM1.
No, but my point is that CSM2 high res, CSM3 high res, CSM4 high res, if they have mesoscale eddies, will inherit this structural error.
So we need to think of ways to tune CSM.
So when you guys run CSM3 high res, it probably.
Right now, the other thing for CSM3 is we have different oceans. And that is maybe something different.
Again, I think it's telling us something is going on when you have mesoscale eddies that mix too much cold water. And then my hypothesis is that the high res model, well, no, the Variance feedback is too weak in models, but because you don't have this negative feedback, then you're fine. But once you have this negative feedback, then your positive feedback is not strong enough. And we know that from CMIP models, that the Variance feedback is too weak. But perhaps we were just happy with that, but now we're not.
I guess once we have the CSM3 hierarchy, we will learn from what they had for CSM1 hierarchy and try to improve.
Yeah.
Definitely.
Maybe I'm getting too far ahead, but if you want to use a high res model to do seasonal prediction, you have to live with this.
As Dave yesterday said, we're going to have a high res CSM3 in a year time.
Okay.
Yeah, perfect.
So we're going to talk about this next year.
Do you want to chime in about the ENSO skill?
Yeah, I was just gonna say that we've been talking about using the initialized prediction framework to to help in the model tuning process. That's a new thing. We've not done that. And I don't know if it makes sense, but we might be at a place where we have the capability to do that. And it's much cheaper than, rerunning centennial scale. Couple of runs with, every.
Or perhaps maybe the way to think about this is, should we document this issue with the high-res models, and someone should write a paper? Right? I mean, it could be a community effort to document this issue with the high-res model and figure out why, in Bing's paper, it looks okay, but then you come to the 10-member ensemble and it doesn't look okay. It doesn't produce enough extreme events. So then you don't get the 2-year La Nina, you don't get all that autocorrelation function that I showed, that CSM, that the low-res models do okay.
Is that true in high-res models as well?
I don't know. It's a good question. The problem is that the high-res models don't have long enough controls. The controls have drift, and few of them have eddies. They're not that high res. But yeah, it would be nice to check maybe if it's a robust feature of all high-res models that this is a robust mechanism making it so too weak. Yeah, this is useful to think about it.
So I could want to.
What?
I could want to here. You do it.
Okay. I gather that people think it's important. Okay.
Yeah.
Okay.
Yeah, might as well. Yeah, you can start figuring out how we do it now. Then we'll be ready.
Maybe we got to present next year.
I could pull things up off the terminal. I can't pull it up off the web style. So I could show you. Oh, man, but.
Right, it works. I mean, you could also just tell us if Pedro's right.
Yeah, exactly. But yeah, prove me wrong.
If he's wrong, you might have to show the flaws.
That's low res.
Oh, was that a
You
wow?
Show it. Are you on the meeting?
Now I'm second guessing myself, but.
Sure.
While I was doing that, are there any other thoughts?
So, do you have access to the internet there? No.
Yeah.
But I used a high-res model in a paper to find a reviewer that hated the CSM1 low-res. So I have a figure in the paper.
Okay.
You wanna?
Where?
It's called Extreme El Nino. And it's in Nature with my last name and Kaustap Tirumalai. It's hard to spell.
Oh, yeah. Future increases in.
That one. If you can access the supplementary figures. Oh no, it's in the reviews. It's in the reviews. But the reviews are public now. Yeah. I can look. If this is a good idea. You go to the review. Yeah.
Yeah, it worked. Nice. It doesn't always, but it does enough. I did it.
Ah, the supplementary information, yeah.
Go to supplementary information.
I'm a fan of it. I don't think I'll ever.
That will include in the review.
Change my mind.
You know?
Oh, no, yeah.
Well, it's just I was trying to connect to EduRoom.
It's not a supplementary figure. It's in the reviews.
Yeah, it's in the supplementary.
Now you have to like.
Exactly.
You can see it.
The Copilot is
Okay.
cursor.
So this is pages and pages. When you see a figure.
It's like everything's in the very
Well, there, that's what. That's the figure. So, and this figure is also useful because. No, can you go?
So you use the high rise, that's so longer to.
Yeah, it almost has no period. It's, so that figure, so green is the CSM1 large ensemble, multiple realizations, all of the same length, like observations. And red is the high res CSM1, only 3 realizations. And here I think I'm using the control. So this is an issue in the control, not even in the historical runs. So these are 70-year chunks, I think. Yeah. And you can see that the standard deviation in those 3 different realizations, the red lines on the plot to the right, are outside the distribution of the CSM1 low res large ensemble and the observations, pretty far outside the distribution. And the line load correlation function is also clearly unrealistic, or the red ones are very different from black one and from the green ones. So I think we went the other side in terms of ENSO. We went from 2 active to oscillatory to 2 inactive to non-oscillatory. Yeah, I'll write a bit. I can use that.
Yeah, I think like we can also see in the low res model, it can look like that and pre-industrial, and then it looks better. So it's, I feel like it's possible there's tuning that could happen.
Yeah.
Okay, I think we need to finish up. I just wanted to ask one question about large ensembles. It's going to be very expensive and kind of probably impossible to really run a big large ensemble with CSM3. And then there's also many other things going on, like lots of perturbed parameter work, there's machine learning work, there's high resolution work. Whatever, I guess if we were constrained in resources and all we could do was say run a smaller set of experiments exploring those different avenues versus running one large ensemble the way everyone normally does, which would you choose? Okay, so like maybe show of hands of who would like a large ensemble that's done in the way that all the previous large ensembles have been done, if that was the only thing.
Yeah, that's a good question.
This doesn't help, it's like half and
Is it something that machine learning could do for you?
Yeah.
Yeah, I guess if we had that capability, that would be a way to fill in the gaps, and there's steps towards that. The other option is just using that computing time for other things, like maybe running 10 members of perturbed parameters or some high res. Basically, we had the working group resources saving what we could after some of the basic experiments. For our whole allocation, it was like 4 members. So that kind of tells you where we're at with resources when it comes to CSM3 and our limited ability to run large ensembles.
Did you write that into the CSL?
Yeah, we wrote 4 members to contribute to whatever kind of combined effort there might be. But it seems like there's still people I guess my thinking is like, do we already kind of know what we would know from it, like initial condition large ensembles from all the ones that have been before, or do we feel like we would really need that again for the new model? I think I could argue it either way. I know it's 50-50 show of hands. Yes, that's
How
true.
small would your large ensemble, like, I mean, what's the minimum number, right? There's, Claire did this, right?
Yeah.
Yeah.
Like, is it 40 or am I getting that
It
wrong?
depends on what metric you're looking at.
Yeah, okay.
I feel like I'm having
For some
to-
things, they
I
can't.
feel like we had this conversation
Yeah,
last
okay.
winter. Yeah.
Well, Nicola showed that spread of, you know, the ensemble, you know, for one of those metrics, right? So
Yeah.
it could be, we could pick our most important metrics and then use that number.
Yeah. Or do you just kind of, but I think you could also argue that we just know that that's the spread from all the large ensembles that have gone before. I don't know, it's tricky. But yeah, I think figuring out what we care about and what would be the minimum ensemble size is the question to answer when we're thinking about what to do. All right, it's almost 5, so we should probably wrap up unless there's any final points. Anyone?
Nicola raised her hand.
Oh, Nicola? Oh, Julie?
I guess.
Oh,
Yeah, go Nicola.
oh, sorry. I was only going to say you could run the CVDP with the old ensemble mean, for example, as your instead of observations, and then like your 5 members of the new model and see how consistent it is, and then see if you can use the old ensemble to get some of the statistics of the spread even, you know, to estimate it. I think there are ways you could use a smaller ensemble and compare with the old larger ensemble to learn smart things without having to run a whole new large ensemble.
Yeah,
Just a
I
thought.
think the same with
Yeah.
sampling of the pre-industrial control, like, yeah, I think those kind of approaches will help. Yeah, I think that hasn't been fully decided yet.
And tease
whether-
out the
Yeah.
force response a bit more, because that'll be quite different.
Yeah. Yeah, so there's many things that we could do with a very expensive model.
Yeah. And you're gonna have interactive stratospheric chemistry as well, like everything is gonna be quite different. So it'd be nice to
Yeah.
maybe hold one of those fixed or something.
Yeah. Yeah. All right, we have to finish up at 5, so let's leave it there. Thank you all for coming and for all of the discussion and all the great talks. And we'll, yeah, see you at the summer meeting, but probably see most of you before that.